Research interests include several aspects of image processing, computer vision, and pattern recognition. And he has been an associated editor for the IEEE transactions on image processing since December 2021. Professor Thiago, Silveira, and Professor Claudio Jung, the floor is yours, so please get started.
So, good morning, everyone. Thank you for the presentation, Manuel, for the introduction, actually. Okay, so here we have some QR codes, and you can check our websites. And here we have our first spherical image, where, wait a minute, here, me and Professor Claudio appear. And we will discuss a little bit more on this kind of signals throughout this talk, okay? So here we have just an agenda. It's divided, the presentation is divided in two parts, though we will have a full-time presentation. We will not break the presentation in two. First, we get an introduction on this subject. So we were asking ourselves, what are 360-degree images? Where do they apply? If they, we want to know if they differ from traditional images and what is the impact of this difference, if it exists. Then we move for the spherical image model, and we will understand how can we model a spherical camera and understand mathematically how the spherical image is formed. Then we will talk about acquisition devices and representation formats. Specifically, we will deep in catadioptric, holodioptric, and fisheye-based systems. And we will talk about a bit on some of the most representative formats. Then we move for the main challenges of spherical images. We will understand what we call here the FOV dilemma. Then we understand what are the challenges in the rectangular format and other representations. We'll talk a little bit on visual distortions and benchmarking, and then we will move to three selected applications that are gravity alignment, layout estimation, and depth estimation. And then we'll close this talk with final remarks. Okay, so first of all, we need to understand what are actually 360-degree images, and I think that the most straightforward way to think about them is to think about a Christmas ball. So if we look at a Christmas ball, we will see ourselves and most of the content, the context around us. And as we move around this Christmas ball, we will see more and more information. So of course, our eyes are seeing what the Christmas ball reflects. But if we think we are the Christmas ball, we will see everything around us. So everything that's on the surface of this Christmas ball is some kind of an intuition of the spherical image. Okay. Well, we will exchange words as synonyms, and to be clear enough here, we add this bullet. So we will call 360-degree images as unidirectional images, spherical images, and panoramic images as well. Okay. What's the main characteristic of a spherical image? Well, its main characteristic is that any spherical image stores the information from the whole scene where it was captured. So everything in the scene is represented in one single image, and this image is what we call a non-directional image. Why should we pay attention on spherical imaging, and why we are having this talk now? So 360-degree vision is becoming very popular nowadays, as we have affordable devices for capturing and visualizing this kind of signal. So we will see next that we have some kind of devices for capturing, and some of these devices were invented decades ago, but now we have a more interesting device, let's say, that we have widespread for the community. 360-degree media approximate what we call the planoptic function, which is a utopic function, utopic imaging model, or an ideal imaging model, where we can capture all the scene information from every position in the world coordinate system a long time. So 360-degree media capture the complete scene information a long time if we're talking about videos, but of course we cannot capture this information from any position. So we have to position, to locate the camera in the different parts of the world to capture this different data. Okay. So where 360-degree images apply, and we can think that actually it can be applied to every visual computing task. Of course, we have some of these applications in mind that we look at the application and say, oh, this is a classic application where 360-degree images can be applied. Some of them are robot navigation, so we can understand that a robot that sees everything can navigate in the scene with a much more safety and do what it is meant to do. Also, we can think about surveillance. So we have one camera that doesn't need to choose where to look at, but it sees everything all the time. We can also think about autonomous driving systems, and we can, again, imagine that seeing everything can be, important to this driving system, as it will not do what it should not do. And one of the most common applications are in area of AR, augmented reality, mixed reality, and virtual reality, where the users use this kind of device for visualization. And here we have some immersive experiences in places captured with spherical images. Of course, we can think about many other applications, and we'll discuss some of downstream tasks in this talk later. So the first question that appears when we think a little bit more on spherical images is how it is defined and how it differs from what we will call here traditional images, or those images that were modeled as pinhole from pinhole cameras. So the first thing we need to rewrite here for you is what we saw, that camera sees everything. We will now call it as the camera has what we say full field of view. So it sees everything, so we have a full field of view, and we call it FOV. Here we have a regular camera capture. And here we have a spherical image capture from the same scene in the same position. And we see that, well, these two images are not similar. This regular camera has a narrow field of view and captures a portion of the scene, and the spherical camera has a full field of view and it captures everything in the scene and maps it to a sphere. So the data acquired from a camera, a spherical camera, is mapped or is represented on the unit sphere. And one thing we need to state here is that 360-degree images are not 3D images. So this is a misunderstanding that commonly appears when you're talking first time on spherical images. This will be more clear as we move on the presentation. And the question is, how can we process spherical signals once we are not representing our signals on the plane as those traditional images? Before we move to the processing, we should first understand how a spherical image is captured, actually. So we have here what we call the spherical imaging model, and it bases on what we know as central projection and spherical projection. So central projection is also applied or also considered in pinhole imaging. And the basic idea is that everything in the world is projected to a plane in the pinhole case or an sphere in the spherical case that is centered on, you know, a 3D point on those world coordinates. The spherical imaging model abstracts the cameras as a sphere that sees the surrounding 3D world. Okay, so it goes in the same vein as we saw before. But the spherical model actually understands a spherical camera as a unit sphere. Okay, and everything in the world is projected to the surface of that sphere using central and spherical projections together. Unlike the pinhole imaging case, we have only the extrinsic parameters. So we have only 6 degrees of freedom, 3 degrees of freedom for the translation of the camera, and other 3 degrees of freedom for the rotation of the camera. So it's actually a sphere that can translate and can rotate around itself. So let's understand this concept in baby steps. First of all, let us define what we call a 3D world coordinate system. And, well, it's arbitrary. You can define this world system whatever you want. First of all, we need to define its center, okay, or its origin. And then we can think about the other points in the world as somehow parameterized by this world coordinate system. Okay, so we have here an example of an X 3D point or world point. Okay, then we can think on our camera as a unit sphere, and we can think that this sphere can rotate, as we talked before. Okay, if we assume that this camera is aligned to that world coordinate system and centered at this world coordinate system, we have this simple formula for projection. So basically, this 3D world point is projected as an image point that we call here on the surface of the sphere, and it has like a unit norm. Okay. Basically, we divide this vector by its norm. Okay. Well, we know that the camera may not or might not be centered at this world coordinate system, and actually might not be rotated or aligned to this world coordinate system. So we need a more complex, not so much, equation to describe these imaged points as function of the camera rotation and the camera center. Okay. Well, just for record, we will use this translation vector notation that some kind of induces the center of the camera. Okay. In terms of representation, we see that this camera is aligned to and centered at the world coordinate system, whereas this other camera is not. Okay. Well, just one thing that we need to understand here is that what we image here, what we record here, is actually the color or the intensity of this world point, right? And this can be done for, you know, every point in the 3D world. And once we have this spherical image, okay, we lost the explicit information of the 3D world, right? As in the pinhole case or so. So understood what is a spherical image. We also understood a bit of how the image is acquired, and at least in the in theory. And now we need to understand how we can acquire it physically with a device. And once we acquire this image, how we can represent this image. Okay, so these two topics are discussed now. And first thing we need to state here is that there is no sensor that sees the whole scene. So we have this spherical imaging model that says everything in the scene is imaged to the surface of the sphere, and the surface of the sphere should be like a sensor, right? But we cannot physically design this sensor. So what we do? What can we do? We use actually regular planar silicon sensors, right, from regular cameras, and adopt optical solutions to project the all-around information to that sensor or some sensors, not only one. Okay. What are these optical components? Mainly lenses and mirrors. Okay, we can use both or some of them in different cases. And then, well, we have a small coverage of the scene by a combination of a planar sensor and well, an optical component. This is mapped to a part of the sphere by software, and then we can think on our spherical imaging on the sphere, actually. Okay. Well, we will review some capturing systems that are called catadioptric, polydioptric, and dual fisheye based devices for acquisition. So here we have some examples, but they are most based on this dual fisheye system. The first capturing system that we discuss here is the catadioptric system, and we have a regular camera here, so a regular sensor, a regular camera, and also not very special lens. What we use here for capturing the whole scene information is a mirror, a convex mirror. Okay, so we face this convex mirror to the camera sensor, and this camera can capture all the horizontal information with this combination of devices. One problem of this system, the kaleidoscopic capturing system, is that it doesn't cover the full field of view. So it covers the full horizontal field of view, or in other words, it covers the 360-degree field of view in horizontally, but it cannot cover the full 180 field of view, vertical field of view, because we have, well, the mirror and also the camera. So we cannot see throughout the mirror nor below the camera, right? Two other problems now of this kind of capturing device is that they are bulky, so we need well, a complex system here, and fragile because we have those mirrors. And well, it's not actually being used in current research or current industry, but in fact, this kind of sensor was used when this big omnidirectional imaging area emerged, like 20, 30 years ago. Well, once we do not cover the full field of view and we have this kind of occlusion, the mirror and camera or sensor occlusions, we can actually map the information that we can capture in a cylindrical form, and this will be, well, a different model of omnidirectional camera. Okay, that's not actually omnidirectional. Well, another system for capturing omnidirectional images is what we call a polydioptric system. And it is actually a collection of cameras that point outwards from the rig. So they are organized in a rig and point outwards. These cameras are actually regular cameras, as in the previous slide. And they have common lenses as well, maybe a wide FOV lens, a wider FOV lens than normal. But yeah, they are regular cameras. The main idea here is that each camera captures a narrow field of view image, so a common image, and these all these images can be combined using what we call the stitching or a stitching algorithm or a mosaicing algorithm that, you know, stitches those images together. And then we can cover the full field of view if you want. This kind of device is also bulky, and they are expensive because, well, we need lots of cameras. Here we represented these cameras, or this rig, as a collection of 6 cameras, maybe. But we can extrapolate this idea and have like 20 or 30 cameras. As much as we want. One of the advantages of using this capturing system is that they produce high resolution images, or they can produce high resolution images if you have, you know, good cameras capturing the scene. And also we can represent only part of the scene if you want. If it's not mandatory that we cover the full sphere, we can have a circular we can capture only the horizontal field of view if you want, or the full scene. Okay. Well, and then we have what we call dual fisheye-based capturing systems. And the idea of this capturing system is that we have only 2 cameras, each camera with a wide field of view lens. And this lens is actually called what we know as fisheye lenses. And each lens or each camera captures an spherical image. So it covers a bit more of 180 degrees in field of view. And this overlapping region that is covered by one camera and the opposite camera is used for stitching as well, as in the previous system. Okay. The main advantages of this kind of device is that they are portable and they are cheap. So we are talking about 2,000 reais. It's not too much, and you know, you can put in your pocket and walk away, and then you take a picture, put your pocket again, and that's it. The big problem of this kind of device is, well, as expected, they are not so high resolution devices, so they produce what we call here user-ended images. It's like 3K, 3.5K by 6K pixels. It seems a lot for regular images, but it's not too much when we're talking about full field of view coverage. Okay. Well, so we saw that there is no spherical sensor. We have some kind of combinations of lenses and mirrors or so. And once we capture the images, we map them to the sphere. And what happens now? Okay, we have a spherical image mapped to the sphere. How we represent this image, and how do we store this image, and how we process this image? Well, we are aware of different mappings, like sphere to plane mappings, and most of you might know some of these mappings. They are different here. We have some different kind of mappings. Some circular, other with a complex shape here, or, you know, not so familiar. Each mapping has, it preserves some properties when mapping the information from the sphere to the plane, and vice versa. And, well, they all introduce distortions. We can't go from the sphere to the plane without introducing distortions. They are not in the same space, right? So we need to know if representing the sphere on the plane is a good choice we can do, or if it's not. And we need to understand that this mapping will introduce some kind of distortion. Maybe we need to handle these distortions. Okay. Well, there is one mapping that I did not show you in the previous slide that we call, like in Portuguese, mapa mundi, or world map. This mapping function is actually called the rectangular projection of the sphere, and it is the standard sphere to the plane mapping function or representation. Okay, so we may agree that the Earth is rounded. Okay, it's a globe, and we commonly see the Earth, the world map, as a 2D planar projection. So what we learned many years ago in the school is that the poles they seem to be much bigger than they actually are. If we have the sphere representation of the Earth in our hands, we can move the sphere and see, oh, okay, the south pole is not so big as I thought it was. So the equirectangular projection is actually known as a latitude longitude mapping, and it is actually very used or widely used in the scientific community and industry as well. So it's not we know the Earth as this kind of 2D mapping because it has some properties that are amazing for some kind of applications. So the sphere to plane mapping and the inverse mapping, the plane to sphere mapping, are both straightforward using the RP representation, but we have this irregular sampling on when we sample the sphere irregularly and map it to a regular grid representation in plane. So this induces what we discussed before. The poles are highly oversampled. Okay. Well, just to understand a bit more of what this equirectangular projection is, we can go back and see the imaged point here. It's a vector that has unit norm, so it lies on the surface of the sphere, and we can actually rewrite this point, okay, this point position, this pixel position, this image position, image information position, in spherical coordinates. So instead of using Cartesian coordinates like x, y, and z axis, like depending on these axes, we can actually rewrite this this point as this equation here. So if we pay attention of this equation, we will see that this kind of mapping is straightforward, and that these points that lie on the surface of the sphere can be represented using only two-angle information, so two-angle coordinates. Okay, so they depend on theta and phi, and we know that the spherical camera has, or as it's modeled, has a unit norm, so the R variable here is 1. So then my idea here is to switch our representation. Instead of using 3D Cartesian coordinates, we switch it to spherical coordinates. Okay. Well, we have shown this, mapping from this X point, but we have one point for every information in the 3D world. So we have a lot of these points, and we actually can map all the scene information in a regular 2D map. This 2D map has like a 0 to p limit in one dimension, and 0 pi limit in the other dimension. Well, it's a continuous domain, and we need to discretize this domain and form our image. And this is done using this formula here, assuming that we have H pixels in height and W pixels in width. Okay, so we can map this whole scene information in a discrete matrix that stores all the scene information. And here we have a rectangular representation of that spherical image that was represented on the sphere itself that we saw before. Okay. Well, we know that the rectangular projection has some distortions, and these distortions are induced by this irregular sampling that we mentioned before. And this irregular sampling is proportional to sine of phi. So we can like see what this distortion means when we understand the portion of area on the sphere that is mapped to the plane, and we can compare these portions of area in this planar representation. And although it's not so clearly to most of you, I think, we know that as we are in the equator region, we have like a unit sampling, and as we move to the poles, we have a high oversampling, and then each pixel contributes to a small portion of area on the sphere, but a large portion of area on this planar representation. Okay. Well, we talked about the rectangular projection. That is one of these many choices we could use to represent the sphere to one planar representation, to one plane only. But it has some advantages. So it's straightforward, as you saw, and it's regular. We saw before that many other mappings can be used, but some of them are like a butterfly, or others are circular, and we would prefer not to manipulate this kind of shapes when you are dealing with discrete data. Okay. Well, we can actually map the sphere not to one plane, but to many planes. And the most common multiplanar sphere-to-plane representation is what we call the cube map projection. It's actually widely used in computer graphics, I think. And the basic idea here is that we can take our sphere, our spherical image, represented on the sphere, of course, and put it into I don't know, a cube that is tight enough to that sphere. Okay, and map each of these each portion of the sphere to one face of this cube. Okay, well, just for record, the cube map projection is also known as a skybox map. So each face of this cube will actually represent a portion of the sphere with 9 degrees, with FOV of 9 degrees. Okay, so the basic idea here is that we will squeeze that cube until it touches the sphere, and we use that middle point on each face to draw a plane, and then we project that part of the sphere to that plane. Okay, so this is what we call tangent plane projection. Well, the basic idea is is the one that I just mentioned to you. Here we have some kind of animation. So we start from this sphere representation, and the cube is empty by now. Then we project part of its information to the one face, then the other part to the other face, then the other part to the other face, and then we have this cube map projection, this cube map representation. So what's the main advantage of using this kind of representation? The main advantage is that we have a little bit less distortion. So if you compare it with net rectangular projection, we see that, well, it's well behaved on the cube and not so well behaved on one plane as in the rectangular projection. What is the main disadvantage of this kind of representation? Well, we have, although we have presented here as one single image, we have actually 6 images to process, and these images are somehow connected, and you need to understand how these connections occur, and well, depending on what we want to do, we need to somehow be aware of these connections and introduce some kind of processing in this connection, in the three plane connections, for example. So the cube map projection has this interplane dependence. We can extend this idea to many planes. So we do not need to use only 6 planes, as in the cube map projection, but we can use some polyhedra approximations of the sphere. And here we have like a nicosahedron that we call a nicosphere when it's when it matches or almost matches the sphere. But we have other kind of subdivisions here too, and these all can be used to represent the spherical information. The main idea of this kind of mood plane representation is to mitigate even more those distortions that we saw before, and well, it moves much more intricate. The connections between the faces are much more intricate as earlier, but it actually reduces the distortion. As I mentioned before, these kind of representations are based on successive subdivisions of a polyhedra, and we have as initial polyhedron like an icosahedron or an octahedron or so. Let's move on to the main challenges. Before, I just need to recap with you what we just saw. So we understood what are spherical images, then we understood the basics of the spherical imaging acquisition, actually. Then we talked about the devices, and then we talked about the representations we can use. Well, we have some challenges, of course, and we'll discuss some of them in the next few slides. So the first thing you may perceive is that we have a dilemma here. So we need to somehow trade off between context and distortion. So here we have a regular camera capture, as I showed you before. Here we have an rectangular representation of the same scene in the same position. And here we have one face of the cube map representation, also from the same scene in the same position. What we can see here is that, well, the smaller the FOV, the smaller the FOV, the field of view, well, the less the contextual information. So I don't know what we have behind this or you know, out of these areas imaged. But we have also less distortions. So as we increase the field of view, we increase the contextual information, and we also increase these distortions, regardless of the representation. So we are talking about the rectangular projection here, but we could use some of those other mappings that we mentioned before. And the question is, are those distortions a problem? And if they are a problem, how can we handle those distortions? Well, we can go back and think about the classic image processing. And in the classic image processing, we assume that every pixel has some regular sampling, you know, in horizontal and vertical directions. And we can use some kind of filter that it's actually it doesn't need to tackle any kind of sampling problem, sampling issue. So it assumes that the sampling is uniform. And as we move to those other mappings here, we have these distortions that are actually induced by the field of view, adopted in that case. So we need to be aware of this, and maybe we need to tackle these problems in the future. Well, we will start our discussion on challenges here by recapping that the rectangular projection is the standard planar representation of 360-degree images. And as we saw in the previous slide, it has the full context, the full field of view, the full context, and a lot of distortions. And we also need to understand that the current image processing is made of, well, CNNs. Although we will focus on this kind of discussion here, we can extrapolate these ideas to perform like classical or traditional image processing based on some other kind of filtering and things like that. Okay. So when we talk about CNNs, we need to know now, or we need to remember that the kernels are the CNN kernels are by default regular. So they are like 3 by 3 or 5 by 5 or 7 by 7. And when we apply this kind of kernels, convolutional kernels, to our images, they cover uneven parts of the sphere. So if we are processing, if we are sliding a kernel window on the center of our rectangular image, we will cover one portion of the sphere if we, you know, map this kind of processing to the sphere. But if you have the same kernel on the poles, we are covering actually a much smaller part of the area the sphere. So if you apply this kind of filters without proper treatment, we will have this uneven coverage, and we will end in like weighting the information in different, with different weights. We are weighting it uneven also. So an ideal kernel should adjust its support to address these ERP, these rectangular projections, which are at the end this kind of non-uniform sampling that we know how it behaves. It's proportional to sine of phi. So we need to adjust the support of the kernel to where it's been applied in the moment. Okay, in that moment. Here we have in this red image here, the upper image, we have a regular kernel represented in red. Okay, it's larger than usual, but it's larger to visualization purposes only. And here we have a kernel that addresses DRP properties represented in blue. So let's think that this image here is an rectangular image. Here we have a convolutional kernel or a filter kernel, any filter kernel. Here it's aware of the distortion. Here it's not aware of the distortion. Here it's aware of the distortions. Well, I don't know if you can see from there, but we have like a a belly here, but they are pretty similar to me, and this adaptation is worth or not. Well, we have here a kernel centered on the equator line, so it should not be so affected by the distortions, by the non-uniform sampling. But as we move to the North Pole, for example, we should adjust this kernel in this way. So this kernel is not anymore square, nor even close to square. Yeah, it has a complex shape that takes into account the spherical deformations induced by the rectangular mapping. So these regular filters are spatial. The regular filters are spatially invariant, have spatially invariant support that we are showing in the upper part of the image, and we need to make the or to force they to take these ERP properties into account. So one of them is this kind of adjustment as we move to the poles, and the other property that rectangular images have is that they are circularly connected. So if we are moving our kernel to the right, and then we touch the lateral board here, what we do in classic convolution, for example, is to perform padding, zero padding, or extrapolate information there and compute the convolution as it was not a problem. And that's it. But if we move to the ideal kernel in the rectangular image processing, we need to make some kind of padding as well, but copy the information from the other board. Okay, so we need to perform this kind of circular padding. Okay. Well, as I mentioned, the circularity issue can be solved by padding. So we can perform the padding manually and then process the information, and that's it. Or you can use some kind of module in operation. But adapting the kernels is a bit more tricky, because we have now kernel sampling points that need to be spread depending on the kernel position. Fortunately, we have some works that do this and perform this kind of adaptation and deliver this framework to further processing. And here we highlight what they call the dilated convolutions, distortion-aware convolutions, and deformable convolutions. The main idea of these three approaches is that the one that we just mentioned before, that is to spread those sampling points when computing the convolution over that ideal region or kernel support region. Okay. These approaches also perform this kind of treatment naturally, so we do not need to explicitly pad information here. We can just use these approaches to process the rectangular image. Okay. Let me think about what I was going to say. Well, I remember. Well, that's it. So we can use regular filtering in rectangular images, but they are not like correct from the theoretical point of view, and they will be weighting the regions of the sphere in different intensities. But we can address this problem using these three approaches and probably many others that employ similar ideas. We also have some kind of challenges when we process other representations. And I'm depicting you here, or I'm depicting the cube map issue here, where we have the central face, for example, and we can some kind of consider the information from the other faces when we are processing this particular face. So we can actually, instead of projecting the surface of the sphere to one face of 90 degrees, we can project it to a surface, a face of the cube that is a bit larger. So we can project like 92 degrees. Of course, it will introduce a bit more of distortion, but we have now an overlapping region that could be used to solve this kind of interplane issues. Okay, the same concept that I'm showing you here in the cube map case can be applied to the other multiplanar representations like the icosphere, as I mentioned before, noting that the triangles from that other representation will have, of course, other boundary conditions to be treated, but the idea of padding can be adopted as well. We mentioned some kind of mapping from the sphere to one or more planes as a possible solution. And in fact, as I mentioned before, the rectangular projection is the standard representation of the spherical images. And why we project the sphere to the plane and not use another representation for it. The main idea is that we can use some old tools to process full field of view images with small or no, if we are like agnostic, treatments. So if we project, if we represent the spherical image on the plane, we can tackle it as an image and process this as an image, ideally taking into account this distortion or this kind of multi-plane dependencies. Okay, but one thing that we did not mention is that this spherical image can be actually represented in the graph, so in a spherical graph. Where each pixel is a node in this graph, and the adjacencies between pixels are encoded as edges. So if we represent this spherical image on a graph, we don't have any kind of topological issue, and we can perform graph signal processing without needing or with no need to tackle like special conditions. Actually can use graph neural networks and approaches like that to perform much of this signal processing. One problem of adopting any kind of treatment for spherical imaging processing is that, well, we have GPUs, and these GPUs are some kind of focused on tensor processing, where the information is kind of regular, and any kind of adaptation that need to map to deviate from that regular processing will introduce some kind of slowness. Okay, so these non-convolutional operations are, after all, demanding. Okay, non-conventional convolutional operations. Well, actually, there are some works that make some kind of comparisons, and they say, well, it's not worth to use deformable convolutions, for instance, because at the end, our results with or without this kind of treatment were comparable. So, but the training time, the inference time, some kind of processing are much slower, and it's not worth. I think that's an open question, but we have some kind of works that are in this direction. Well, besides the sphere-to-plane issues, sphere-to-plane mapping issues that we mentioned before, we have other issues as well. Like from a dual fisheye camera, we have actually one capture like this one, where we have two hemispherical images. And when we move to this equirectangular representation, we have some kind of loss of information, right? Here we have an overlapping region. I'm not sure if it's clear to you, but for example, we have the stairs here in both images, and at the end we have one stair on. Okay. when we do this kind of processing, we will introduce some, or we miss some information. And when we move from the rectangular representation to the cube map, we will miss some other information. And when we move to the cube map to the rectangular map, we will miss information again. So we need to have a linear path here when we are coming from one representation and going to another. So it's one thing that we need to keep in mind when we are processing spherical images. When we have those multi-camera representations like polydioptric and dual fisheye based systems, we need to stitch the different images together. And when we do this, when we perform this stitching operation, we will sometimes have these stitching lines. I'm not sure if they are visible to you, but sometimes we have different lighting in one view and another view, and it's not like equalized when we have the full image represented. So these stitching lines, they will appear in the same position, like here and here. All my images captured with the same camera and without further processing. And we can think that maybe these stitching lines will bias some kind of training or so on. Okay. Well, the objects have variable appearance depending on where they are in the image. I don't think this example is good enough, but we can think that me and Claudio are not in the same position. So let's think that I'm closer to the camera. I will have some kind of distortions that Claudio has not. So Claudio is in the equator line, far from the camera. If I'm here, like on the side of, very close to the camera, I'll have like a head that covers most of the North Pole, and maybe my hand will cover most of the South Pole. So this is one thing that we need to pay attention when we are working with spherical images, especially in, I don't know, detection tasks where we don't have like a fixed appearance model for the objects. Okay, and another problem that may occur is that if we don't, if we get our camera and hold this camera like upright, we will have some kind of image similar to this one, where the horizon is aligned to the equator line. But if we tilt our camera in some direction, we'll have a sinusoidal behavior in our horizon. And this thing, this appearance will be so strange that maybe we cannot understand the image in the first moment. And this kind of misorientation of the camera can be, or can preclude further processing. So this is one of the tasks we selected for discussing a little bit more, and Claudio will probably present this part in a few minutes. Another big challenge that we face in spherical image processing is the lack of benchmarks. So we know that there are many data sets for regular images and different applications. So we have annotations for detection, we have annotations for segmentation, we have annotation for, I don't know, whatever we want. We have additional data like depth, we have infrared, MAPIs. We have lots of data when we are dealing with regular images, but this is not the case, unfortunately, for the spherical area. So we have like a very new area, and we don't have any textbook, for example. We don't have big data sets. We don't have sufficient annotation for many tasks, and it's still a challenge to get data for training like a deep learning model, and also it's a challenge when we are comparing methods. So there is no there is no consensus that the metric A is better than another metric, and it's complicated to compare different methods in different applications using spherical images. We hope this change in the next few years, and the area can be better explored. So now I think Claudio will follow this presentation, and we will discuss next 3 selected applications that appear in this field. So, Claudio.
So, thank you, Thiago. Maybe I'll just share the screen. Okay, just a moment. Let me just find the share screen button. Share screen. Okay, can you all see the screen now?
Yeah.
Good. So, hello everybody. Good morning. Actually, it's middle of the morning now. Thiago mentioned several aspects regarding capture, representation, and processing of spherical images. And as you could see, basically any application that involves pinhole images can be extended to spherical images as well. So if you think virtually any application like object classification, image classification, object detection, segmentation, all those applications that are typically explored by pinhole cameras can be extended to panoramas. Maybe the transition might not be straightforward, but they can be. In this presentation, we selected applications that mostly benefit from the full field of view of spherical cameras. And as Thiago mentioned, we will focus on 3 main applications, and hopefully I'll be able to convince you that spherical images are suitable for these applications. So the 3 applications are gravity alignment. So this name might sound weird for those of you who are not used to this naming in spherical images. But as Thiago mentioned, basically the idea is to align the image, the spherical image, the equator of the spherical image with the horizon in the real plane. So this is usually important when you have still images that you want to have aligned panoramas. And if you have video sequences, you have a kind of stabilization of the panorama. The other application is layout and depth estimation. Actually, they are very related applications. And basically, layout means recovering geometric structure of a typically indoor room or scene. And although you can try to do this kind of application with pinhole cameras, you must have several captures to cover the 360 field of view, and you have to stitch them. And in theory, all this information is encoded in a panorama, in a single panorama. And if you can get either the layout or the 3D per pixel 3D information of the scene, you can have an idea of the 3D structure of the object, and you can do it. You can export this information for like metaverse navigation, AR, MR, VR experience with head-mounted display. You can perform view interpolation and generate stereo pairs and provide a real 3D visualization of the scene with a degree of freedom in the head. Of course, for self-driving vehicles or robot navigation, it's very important to have 3D information, depth information for either detecting obstacles or SLAM in robotics. And the first application that I'm gonna briefly describe here is gravity alignment. Just to clarify, the goal here is not to get into details of different approaches that handle each of these applications. As Thiago mentioned, given a spherical image, you can represent it as a ERP, which is typically called a panorama, cube map. You can have icosahedral representations, and I'm not gonna get into the details of the representation, but the problem itself. And for each representation, if you're going to the deep learning pipeline, you need a backbone, and this backbone might use conventional CNNs, might use spherical adaptations, might use attention models, right? So it's a kind of plug and play of several different components. The input, which is usually we do not have control. I mean, you get the image. I don't know which kind of camera was used to capture it, but you have control on the representation and, of course, on the technique itself. So basically, as Thiago mentioned, a 360 image basically is a projection of the scene onto the sphere. So if you don't consider sampling issues, these images, like the analogic spherical images, where you don't have sampling, they have 3 degrees of freedom. You can rotate it around the center of the sphere, and still you have exactly the same representation. So any capture of a spherical image can be rotated or de-rotated to a standardized capture setup. And when we talk about gravity alignment, basically we want to align the equator line of the panorama to the sphere, the spherical projection, with the ground plane. So if you have an unconstrained capture setup where you can have rotations, the goal of gravity alignment is to basically de-rotate, to estimate the rotation angle, and then rotate this image back to this standardized canonical point of view, right? And as an additional motivation, as we're going to see later, if you have applications such as layout estimation, that you get into a room and you put a spherical camera. Usually this spherical camera is already placed so that it produces a gravity-aligned panorama. And these kind of constraints are usually explored by methods that try to perform layout decimation. So if you have an unconstrained capture setup, you can use the derotation as a pre-processing step for other applications. One small detail is that in theory, any rotation on the sphere can generate any two captures that differ only by rotations can be warped into another by just rotating the panorama. In practical applications, this is not true, because when you have any kind of representation, so I assume that the ERP is the default representation here, as we are seeing here. Since you have sampling issues and the poles are much more densely sampled than the equator line, if you rotate an image so that the equator turns into the pole and vice versa, you're going to switch which region. Some regions are going to be upsampled and other regions are going to be downsampled. So there are some interpolation issues that must be also taken into account when rotating a panorama. So basically, that's the visual representation of an aligned image. Probably the image in the bottom is going to be very hard to understand for people who are not used to seeing spherical images. It's highly distorted. But the first scene, the top scene, is probably more plausible for understanding. So you can see a classroom, you can see the blackboard right in the middle, you can see the desks, of course you can see the floor, you can see the floor on the bottom and the ceiling on the top. If you have a rotated panorama, rotated capture, all these informations are messed up, right? So the main goal of gravity alignment is to warp the bottom image, to rotate it, to find the rotation angle, and generate the top image from the bottom one. And basically, the second image can be viewed as a rotated version of the first one, and you want to derotate it. And there are several strategies for doing that. You can basically perform feature matching, and if you know that the gravity is aligning all the images, you can reduce the possible number of matches and poses. And this is related to depth estimation, as we are going to see later. If you just have one capture, what can you do? The idea is that you can handle the gravity alignment problem as a learning problem. So basically, you have in the training set, you have either a pair of panoramas, one in the upright position, which means it's already gravity aligned, and you can artificially generate rotated versions. So if you have a set of images that are already gravity aligned, you can generate a set of artificially rotated images and then generate pairs of rotated and derotated images from which you can estimate the rotation angle. So basically, that's the core of these strategies that use single panoramas for gravity alignment. And basically, the problem is to find the upright vector, which is equivalent to finding the rotation matrix that can transform the first image, the rotated image, into the gravity aligned one. And there are several technical details on how to encode the rotation and how to encode the angular information of the rotation, which might be kind of a small detail, but they do have impact on the design network, specifically when you talk about angular information, because you have the circularity issue. I mean, a rotation close to 0 degrees is very similar visually to a rotation close to 360 degrees. And if you, depending on how you design the loss function to train your network, if you use direct L1 or L2 norms, of course, that 0 degrees is very different from 360. And you can tackle this problem as a classification problem. I mean, you have a set of predefined upright vectors, and you want to see which one the image better adheres to, or a regression where you directly regress the regression angle, the upright vector. So here we have some examples of different upright alignment or gravity alignment methods. And the input image are the ones on the top, and the upright corrected images are the ones in the bottom. I mean, these are mostly nice results. I mean, you can probably recognize the scenes from the bottom views. From the top views, not that much, particularly the first two ones where the angular distortion is very high, and it's not easy to recognize what the scene is showing us. For me in particular, the second one is very hard to understand what's going on from the rotated version. So the second application that I'm going to talk a little bit about now is layout estimation. So although 360 images, they do represent the whole field of view, the 360 field of view, these images, they do not provide depth information, right? So the main goal of layout estimation is basically to recover a simplified 3D representation of the scene. So when we talk about layout estimation, we are typically talking about indoor captures, and more than that, in kind of structured environments. So many papers and applications related to layout estimation, they are related to virtual tours of houses and real estate agencies. And the idea is that you can get into a room, you take a single capture with a spherical camera, and then you can recover basically the walls, the ceilings, and the floor, and generate a 3D view from the environment. So what kind of information is required? Basically, what you want to find lines that connect orthogonal walls or walls and floors and ceilings, which relate to joints and corners in the image. So you can see the red dots on the top images are the corners that connect the four walls in the scene to both the ceiling and the floor. And as you can see, these lines that relate to the connections between the walls and floors / ceilings, they are straight in the real world, in the 3D world, but when you project to panoramas, they are curved, as you can see here. So different layout estimation methods, they handle different geometries. So some constraints are, the first one basically is a top-down view from a typical room. This is very common in houses. This is a cuboid. Basically, you have a cuboid representation of the scene. The second representation here is a Manhattan room, a Manhattan layout, in which you don't need to have a cuboid, but if you take a top-down view, basically all the connections are orthogonal. And there is the Atlanta assumption that basically you have walls that are orthogonal to the plane, which is usual in most applications, but you can have like curved walls. You don't need to have either cuboids or orthogonal connections between the walls. And of course, that if you have a cuboid assumption in your model and you run the inference in another room that violates this hypothesis, the results are going to be nonsense. On the other hand, if you have a very generic model, such as the Atlanta model, and you run it on a cuboid, it should work. But usually, if you have a model that's too generic for a given application, the results are going to be worse than those that are designed for that particular kind of layout. So before deep learning, there were some approaches that try to do a single layout estimation from a single panorama, and basically they were based on primitive extraction. So geometric primitives are lines, are corners, and which is what we expect in a typical layout. And nowadays, in the past, say 5 years, that's not what I wanted to say yet. Still in older methods, the ERP representation was the most popular, in particular because you have a single planar image that represents the full field of view. If you have cuboid representations, then actually you have a set of 6 planar images, and you have to deal with the connections between the faces of the cube, right? And as I was mentioning before, some methods, they regress the room walls, ceilings, and walls, and the joints between the connections, the walls and the floor and ceiling. And other methods, they basically, they recover the lines that connect, that comprise the connection between the walls and other walls and ceilings, walls and floors. So of course, if you have all these lines here, all the connections, you can get the corners. And if you have the corners in an ordered way, you can get the connections. I mean, this corner must be connected to this corner, and this must be a straight line in the panorama, and so on. So basically, it's a question on how what kind of information you want to obtain from the image. So here we show some results that try to provide different information that in the end generate the full layout. So an example from 37, it's an approach that basically wants to obtain the corners of the junctions between the walls and ceilings, so different planes that make the structure. This is a more generic example based on Manhattan worlds. So basically, you can get all the lines that connect the corners in the layout. This is another example of layout estimation in which you explicitly define the region that relates to the ceiling, to the ground plane, and to the walls. And finally, just all these methods, they usually they are able to generate the 3D representation as in the rightmost images, but they have different assumptions on the layout, and of course they vary based on the kind of backbone that is used, of course the parameters that must be regressed, and so on. So basically, that's the final goal of any layout estimation approach. And as you can see here, it's important to have an input image that is roughly aligned with the equator line, because we expect the ceiling to be close to the North Pole and the floor around the South Pole. And all the walls should be around the equator. If you rotate these images in an arbitrary angle and run these methods, the results are going to be usually very bad. Some methods explicitly assume a gravity-aligned image. Some approaches, they say that it's good to have it, but if you have a very strong angular distortions, the results are very bad. So still going further into the granularity of the application, of course, that layout estimation provides some kind of information about the 3D structure of the scene. But basically, it provides information about the walls, the structure of the environment. If you are in my room, you can see in the background, this is a kind of kettle to warm water. This is not going to be captured by a layout estimation method because it's not part of the layout, it's an object. So layout estimation methods, they provide a rough representation of the 3D scene, and they are restricted for indoor environments. The goal for depth estimation methods is to obtain typically a dense map where you want to know the depth of each pixel in a panorama. So, if you have that information, of course, you have a much richer description of the scene, geometric description of the scene, right? As you can see in this example here, you can see all the chairs. These chairs, they are not important for layout estimation, but of course, they do matter for depth estimation approaches. And you can have methods that explore a single image, a pair of images, which is the classical stereo setup, or multi-view. So, what do you need to estimate depth information? For those of you who are familiar with the basics of computer vision, you know that if you have a stereo capture with a calibrated camera, you can have the disparity and the depth of each point that overlaps into the field of view of the two captures as the human eyes, right? And I'm not getting to the mathematical details, but basically you can have all the theory behind the epipolar geometry. And when you deal with panoramas, the main difference is that you don't need to deal with intrinsic parameters. So basically, you just need to recover the extrinsic parameters which relate to rotation and translation of the camera. So basically, the core concept in 2D depth estimation with spherical cameras is to estimate the essential matrix from which you can recover the pose, and given the pose and correspondences, you can estimate that. If the cameras provide some kind of alignment, as in the gravity issue that the gravity alignment problem that I mentioned before, then you know that the displacement must be in a certain direction, and then you can explore these constraints to improve the matching process, which is required to refine the pose and get the correspondences for depth estimation. And typically, you can perform sparse correspondence matching, then you're going to have a sparse depth match, or a sparse depth map, or you can have a dense feature matching algorithm that will provide you dense correspondences, and then you can have a dense map. Right? So this is an example. Basically, it's actually it's a joint work by me and Thiago, and it's not based on deep learning. It's based on classical vision tools. The idea is that you have several captures of an indoor scene, and basically you perform an initial alignment of the images. You perform sparse matching for pose estimation, and then refine it with optical flow, which provides dense correspondences. Right, and there are small details like adaptations of traditional visual models to deal with the spherical setup. And in the literature, you see that single view methods are becoming more popular. And one main reason is that, okay, you need just one view. If you need just one view, why getting more views? And again, the core idea is that you have a deep learning approach in which you have the input image, the RGB image, and you have a depth map that will be used to train the model so that when the network sees a new scene, it will be able to generate a depth map that hopefully is coherent with what is expected in real life. So the idea is that when you have talking about convolutional networks, you have the support of the kernel, and it implicitly increases when you perform pooling operations, which means that you, as you go down in the network and you decrease the spatial resolution of the layers, a same kernel, say 3 by 3, it actually has a larger effect on the original domain of the image, and you see more context. So that's actually the rationale for using deep neural networks for getting depth maps from single panoramas. Still, there are some approaches that use cube maps, some approaches that use ERP representations, some methods that kind of use both representations, but still ERP is the most common because you have a single image, planar image, and that's all you need to generate, to go back to the sphere and to process the depth map. So I'm showing some examples of different single panorama depth estimation approaches here. They are rendered in different color maps because they were extracted from the original papers. But overall, you can see what's going on. I mean, if you represent here the gray value as the depth, you can see that the beds, the beds, they vary the depth, of course, but you can see that the wall is farther from the camera than the beds. You can see that this door here in particular is the farthermost object in the scene, and it correctly is marked as a brighter region, right? This is basically a similar example, but with a different color map, as well as the third example. And here you have a kind of layout estimation obtained from the depth map. As you can see, it's very noisy here, which is actually expected because the depth map is going to have noise. It's going to contain noise. So if your final goal is to get only the layout, it's pointless to get the point-by-point depth estimates and then just project it to a top-down view. You're going to probably introduce distortions that are not plausible in the model, such as these curved walls here. So I think that Thiago can join me here in the end, in the final remarks.
I'm here.
Hi, Thiago. What can we conclude? Maybe Thiago can get back to the presentation.
Okay.
Oh, yeah. Oh, I'll just pass forward the slide and you can talk a little bit.
So I think the main conclusions that we can get here is that, panoramas are popular, and as Claudio mentioned, virtually any application can benefit from it. There are some issues that we discussed in the main challenges section. So we need to think about some decisions we made when we were thinking about traditional or pinhole-based image processing, and maybe we can or we should adjust those algorithms to explore the correct geometry of those signals. And one final issue that we can recap here is that well, we still need some data sets, and we still need some metrics to evaluate different methods. And without this kind of resources, we cannot advance these areas. I mean, with the same precision or with the same the same I don't know. We need to have those benchmarks to advance the area with success. So I think that's much more to come. And this talk was meant to introduce this topic to those which were not aware of spherical images. But of course, we have a long path to come. I don't know.
So, yeah, so just I'm going to show the references. So probably this talk is being recorded. I'm not sure if the slides are going to be made available, but well, just slowly go through the references. And of course, you can see there are several references from the past, I don't know, 3-4 years. And if you take a look at the image and image processing and vision conference such as ICIP, CVPR, ICCV, CCV, you're going to see several papers that either present a new method or a new data set for panoramas. So I think this concludes the presentation. Thank you all for the patience and for attending. And now I think that Claudio can, or Manuel can take over.
Yeah, so thank you, Thiago and Claudio, for the nice comprehensive tutorial. Very nice. We have time for a few questions, so I would like to encourage the audience to come by the microphone and ask questions. For the moment, we have a brief question here from Bruno Borges. Is asking what is the format that you can save those 360-degree videos?
Thiago? Okay.
What is the format we can save? Actually, the camera will probably capture those images using one of the capturing systems that we discussed before. So the camera will save in the device itself, like two spherical images, for instance. But we can export these images to the format we want, like cube map or a rectangular or so.
Yeah, but it's an MPEG is what?
Oh, okay. Yeah, probably for the images we have JPEG, and for the videos we probably have AVI maybe, or MPEG. I don't know. I'm not sure. It probably depends on the company that produces the device.
Okay, so while people get ready to go to the microphone and ask questions, I'll ask a few questions of mine. So one issue, an important issue that Claudio pointed out is this thing that he called gravity alignment. One observation is that if cameras had some sensors like say geomagnetic field sensors or maybe accelerometers, this could be easily solved by saving this information as part of the metadata of the image. Is that already available or not?
Yes, some cameras do have it already.
Okay, so then you can export this. Great.
Exactly.
So
yeah.
Another thing that I mean, you guys mentioned is are the issues regarding convolution. I mean, you have to perform circular convolution. The density of the sampling varies across the image, and so on. And then at some point, Thiago pointed out that performing convolution on graphs, I mean, using graph CNNs is probably at this moment the most general solution to this issue. Is that correct? And then what are the implications in terms of performance for applying neural networks to spherical or spherical image, 360-degree images?
Yeah, so performing graph spherical processing is not, it doesn't depend on the topology of the signal, so we do not need to explicitly tackle those sampling issues and the circularity problem. There are some solutions. I remember one that aims to recover the upright vector from the images. I'm not sure if we reviewed some solutions for the other two applications. I'm not sure if Claudio remembers.
Yeah, but my question is, I mean, how hard is the performance sort of affected? Because you have to do this on a graph. You can't just perform regular, convolution, linear convolution as you do in regular images using CNNs.
Okay, so maybe Thiago, I'll just make a brief comment here. There are like pros and cons for that. One nice property of exploring graph convolutions is that you can resample the sphere and you don't need to have the oversampling on the poles, right? I mean, you can, in theory, the pole collapses to a single point, but it's represented as a line in the ERP image. And if you move to graphs, you can resample it and you have less samples, right? On the other hand, please, anybody in the audience, correct me if I'm wrong, because I'm not aware of the state of the art, the advances in graph convolutions or other kind of graph neural networks, but they're still considerably lower than convolutional networks, traditional networks. So this is a kind of trade-off, right? And if you see the applications, some papers, they do say, okay, you can use networks that are specific for spherical images, such as, and then they mention dilated convolutions, deformable convolutions, or even graphs. But in the end, they say, but we use the planar network here. So I don't have a concrete answer to your question. And actually, in my personal opinion, it's an even more generic question of choosing a given backbone for a problem. Maybe it works better for this data set, but it doesn't work as well in the other data set. So I think I'm raising more questions than answers here. But I'm not sure if Manuel's satisfied, but...
No, I'm fine, thanks. Yeah, so how about, I mean, have you guys or the community working with 360-degree image have thought about maybe considering performing 1D convolution, I mean, 2-pass 1D columns and rows, or rows and columns? Because by doing this, when you're dealing with the equator, you could use some kernel size, 1D convolution along the lines, and then as you go towards the poles, then you could be keep increasing maybe linearly the size of the kernel. Would that help somehow? First of all, is this convolution separable, right?
Yeah, so actually there are some approaches that kind of do that. I mean, they do a convolution. Maybe actually it's they basically collapse the panorama into a line, because along each, let's say, along each row, no, not sorry, along each column of the ERP, the sampling is roughly constant. The main problem is along the rows. So basically, they collapse this the 2D image into a line, and then they propagate the information along the lines using, I don't know, recurrent networks or attention, right? But this idea of having deformable kernels, we actually have used that, but not to train the model, but to filter a panorama. So the idea is exactly that. You can adjust the bandwidth of the filter depending on the height on the row index. But separable convolution, Thiago, have you seen that? Some papers that do explore explicitly separable convolutions?
No.
That might be actually an interesting point to investigate. So there is one thing that actually we are doing right now is to perform different convolutions in parallel. So for the same image, you convolve the input image with the same kernel with different dilation parameters, and then you combine this information depending on the latitude of the image, depending on the row index of the image. I'm not sure if that's clear, but
okay,
it's kind of in the line of what Manuel said. But basically, that's done in parallel. I mean, you do all the convolutions in a same batch, so you have several supports, and then you combine this information later. Instead of having one kernel for each line, you have all the kernels for all the lines. And actually, the filter is the same. You just change the dilation factor, right? It's not a different kernel for each line, which is actually an issue, right? Because you don't, maybe having one different filter, one different kernel for each line might not be the best idea, since you want the filters to be related somehow. You just want to change the support. So you can do something like that by doing dilated convolutions.
Okay, we have reached our time limit here. I would like to thank again Professors Thiago Silveira and Claudio Jung for the nice presentation. And I would like to invite the audience to join me and thank them for their work.
Thank you.
Thank you.
You.
Okay, yes. Guys. Thanks for having us here.
Yes, and I hope the audience can continue the conference and see you soon in the next session. Bye-bye.
Okay. Bye-bye.
So. Good morning again, everyone. We are going now to the third poster session, and we invite to join us here Alexandre Soares. I'm not sure if he's here. Okay, he's coming. Chandra Cortes. Okay. And actually Leonardo Luis and Andrea Baus. And yeah, Andrea Baus. Okay. So we divided this poster session in two parts. First, 4 authors present their work now, and then we open a period to questions, and then we proceed to the other 3 works, and then open to questions again. Okay, so I would like to remember the presenters that the yellow the yellow seats that we have here are also broadcasting to the audience. Okay. So I don't know, Dennis, you want to make some consideration or?
No, just to welcome everyone. Thank you for joining DPVSA. And I think, like Thiago said, we have all the authors here for the first batch, I guess. Then we will open to some questions. Thank you for joining us. If you want to join with the chat, please be free to ask your question there, or you can come to the orange pulpit there to ask your questions once we get over with the first batch. Thank you for joining, and I think we can start with Alexandre.
Yeah.
Everyone, is everybody seeing me and hearing me well?
Yeah.
Okay.
Yeah.
You can share your screen if you want.
Are you guys seeing my screen?
Yeah.
Yes?
No, I'm not.
I'm
Still
sorry.
not yet.
I'm going to share right now.
Okay.
Are you guys seeing?
Yeah.
Okay. The PowerPoint presentation. Okay. Hi, everyone. My name is Alexandre, and the other authors are Guilherme Ocker, and my mentors Matheus Grelich and Jonathan Tisca, and we'd like to present you our latest work called Event Detection in Therapy Sessions for Children with Autism. Just to jumpstart our discussion, this is a one-liner proposal of our project. Why do we want to detect events in therapy sessions? It's easy to assist in clinical and therapeutic decisions, reducing analysis time for a therapist. So we'll just keep that in mind while I introduce you to the context. Our motivation is autism. Autism spectrum disorder, or ASD, it's considered a complex developmental disorder affecting people of all ages, limiting their social and cognitive skills, and affects not only the people diagnosed with this disorder, but their family and the society as a whole. And the number of children diagnosed is rising worldwide every day, so early diagnosis helps a lot in early treatment. There are many types of techniques of accompaniment and treatment: physical treatment, nutritional treatment, and medical treatment. But observational techniques that materialize themselves as therapy sessions are often used to measure success. That's where therapists can watch closely the progress of the patient, take annotations, and intervene as needed. These therapy sessions generate qualitative and quantitative data that a lot of the times go unnoticed, like data if the patient responds to a certain stimulus, or how many responses happened. Did the patient engage in person-to-person interaction? Did the patient progress in relation to past sessions? With these questions, a problem arises. Is it possible to remember or even keep track of all these things happening in a session? Certainly, it is not. But a possible and simple solution is to just video record these sessions and manually extract data from them, manually annotate data. But this lacks standardization. One professional have a way to annotate things and another professional another. And this lacks standardization for future queries in a structured database. We propose a system that is capable of handle large amount of session videos, store them and retrieving them from the database, and filter relevant scenes according to a collegiate of ASD professionals, scenes where a child is interacting with a caretaker, the therapist, or another object in the room, and assist in clinical and therapeutic decisions throughout interactive searches from the database and statistical reports. Our dataset is composed mainly of our dataset is composed of videos of ASD therapy sessions that mainly features a toddler, a caretaker, and an interactive teddy bear called Plus Me. This teddy bear is the result of an Italian project that we made a partnership with that studies the impact of this experimental interactive toy that outputs lights and sounds that the child can play with. Our framework is divided in three main parts. The object detection part, made with the YOLO v5 deep learning model, outputs bounding boxes around the three main actors of the scene. The second part is the closeness detector, that based on the intersections, the overlaps of the bounding boxes, we can say how close the actors are one from another. And with this, we can make predictions about this overlapping based on a threshold, if they are in fact interacting or not. Right here, we can see that the child, the toddler, is interacting with the plus me. So this is a true positive. And right here for the caretaker and the plus me, this is a false positive. So we have to take into consideration when we are creating our confusion matrix to evaluate our system. And the last part is the construction of a timeline where we point out where exactly is happening those interactions to a pair of interaction class. Right here in this timeline, we're having an interaction between toddler and plus me. In our interface, we can query a toddler name and a session date to generate statistical results like the number of interactions that happened in that session, a maximum time of interaction, and so on. And this is a result for one single session. And we can plot a line plot for all the results in increasing date time sessions. Right here, we can see an increasing trend for total time of interactions between toddler and caretaker, and then other statistics as well. So we can see this graphic is due to toddler plus me pair of interaction and caretaker and plus me. Our results show a high quality in detecting the three main actors with the YOLO v5 deep learning model. And the event detection that predicts the interaction based on the threshold of overlapping features an almost zero number of false negatives. That's really cool because it means a high recall. That's important for us. And results for analysis time, also with this threshold equals 0, features a reduction of time up to 51% for one type of interaction. And just for example, if we increase even further this threshold to 60% of overlapping, we can get even further reductions of time needed to analysis. But this has a drawback, because if we increase the threshold, we have a penalty in false negatives increases. That's it. Thank you very much. If you have any questions, you can ask me in the Q&A session or contact any of us throughout our emails.
So, thank you, Alexandre, for this nice talk. I think we can move to the next presenter, which is Chandler, for this. Please.
Oi, estão me ouvindo?
Yeah.
Tá, vou apresentar o trabalho. Tá. Tá conseguindo
Yeah, we
olhar
can see your presentation full screen.
tá, não estou conseguindo maximizar o perdão. Tá, consigo olhar minha tela?
Yeah, it's I will switch to português. Tá grande o suficiente para a gente ler. Eu acho que tu pode passar os slides com a seta do teclado aí.
Tá.
Para direita e esquerda.
Tá. Eu sou o Chandler e hoje vou apresentar o trabalho Foreground Detection, base no nosso Space Track. É um passo fundamental para o análise e compreensão de vídeos é poder separar o foreground, que são todos os objetos em movimento na cena, e o background, a parte estática da cena. Ele é fundamental porque essa primeira etapa para gerar aplicações de alto nível, tais como vigilância visual, substituição de background. E é crítico porque nessa etapa uma detecção errada do foreground vai gerar baixo performance nas aplicações. Um estudo do comportamento dos animais através de seus deslocamentos em torno, uma vigilância de pessoas na piscina, e agora, ultimamente, nas aplicações, nas plataformas de meeting, group, eles têm essa aplicação de poder trocar o background. Mas fazer essa tarefa em tempo real e que esteja robusto a diferentes fatores presentes no background é um problema bastante desafiador. Nesta cena, nesta imagem, temos duas cenas. Uma que a variação da iluminação da cena está mudando no tempo, e outra onde temos que o background é dinâmico. Então, por isso, nós propomos um modelo que seja online, robusto, baseado no algoritmo de rastreamento do espaço robusto para a detecção do foreground. Nós empleamos o algoritmo RPCA com ruído complexo para estimar o espaço inicial, e, além disso, proponemos um algoritmo chamado Foreground Estimation para ter uma melhor estimação do foreground. O algoritmo de rastreamento do espaço robusto, ele é uma versão online do RPCA depois da inicialização. O RPCA, o algoritmo, ele é uma versão robusta do algoritmo de análise de componentes principais, não? Que é uma técnica amplamente utilizada e conhecida para a redução de dimensionalidade. Então, o RCT tem como objetivo decompor ou separar o décimo frame de um vídeo em dois componentes, background e foreground. Nesta imagem, o décimo frame vai ser representado por o vetor YT de dimensão N. Então, mediante o algoritmo RCT, eu posso descompor em duas partes. A primeira parte, que vai ser o background, vai ser representado por um vetor LT. Ele tem as seguintes propriedades. A primeira, que ele se vai encontrar em um seu espaço de menor dimensão, mas esse seu espaço pode mudar no tempo. E isso gera duas coisas. A primeira, que o seu espaço seja de menor dimensão, quer dizer que eu posso representar o background com uma quantidade muito menor de fatores ou componentes em comparação de YT. E, além disso, que o seu espaço vai mudando com o tempo, gera que o background seja robusto aos diferentes fatores que estão presentes no cenário, tipo mudança da iluminação, background dinâmico, objetos que ficam parados, quietos em um período largo e podem gerar problemas na estimação. E, em outro lado, temos o componente de foreground, representado por XDT. Então, aqui temos um diagrama do funcionamento do algoritmo RCT. O algoritmo RCT, ele inicializa na estimação do seu espaço inicial, mediante o algoritmo AltoProj. Depois, para achar o foreground, fazer a detecção, ele utiliza o algoritmo Project Comprehensive, que tem como entrada o décimo frame, não? E o seu espaço em um tempo T-1. Ele consegue obter este foreground e depois, mediante uma comparação da frame no tempo T, com o foreground podemos obter o background. Logo, esses background vão ser utilizados para a atualização do seu espaço mediante o algoritmo RCT. O algoritmo RCT vai dar como saída o seu espaço atualizado no tempo T, e simplesmente nós vamos reemplaçar neste seu espaço em tempo T-1, e assim vamos conseguir obter, mediante o algoritmo RCT, o foreground, background e a atualização do seu espaço em cada tempo. Baseado nesse enfoque, nós propomos um algoritmo chamado Foreground Detection, baseado em Robust Space Tracking, onde temos a mesma estrutura, mas nós propomos duas mudanças. Não? Na primeira é que a estimação do seu espaço inicial vai ser trocada por o algoritmo MOB-RPCA, que ele tem uma melhor estimação, uma melhor performance na estimação do seu espaço inicial, e além propomos o algoritmo FISC, que tem os mesmos parâmetros de entrada, mas tem um trabalho diferente. Não? Ele pega o décimo frame e ele calcula o foreground, mas esse foreground tem elementos que erroneamente foram detectados como foreground. Depois nós desenvolvemos um filtro para tentar remover a maior parte de elementos erroneamente classificados e assim obter um foreground mais próximo ao do real. E depois continuamos com o mesmo processo do RCT. Obtemos o background, depois fazemos a atualização do seu espaço. Baseado nisso, fazemos alguns experimentos, nesse caso, para avaliar a performance do algoritmo e alguns algoritmos de comparação. Né? Nós utilizamos a métrica F-Mission. Nessa tabela, temos os métodos e o banco de dados, né, que tem 9 sequências de vídeos com diferentes condições, e nós obtivemos o F-Mission mais alto promédio em cada sequência de vídeo. Além disso, nesta imagem estou mostrando os foregrounds detectados por os algoritmos do estado de arte, e na última coluna são os foregrounds detectados por nosso algoritmo. Né? E aqui podemos apreciar que eles estão um pouco mais perto ao ground truth da base de dados. E, como conclusão, nós podemos demonstrar que nossos foregrounds detectados por nosso método estão mais perto do ground truth que os outros, e isso foi validado porque nós obtivemos o F-Mission com maior valor. Assim, nós podemos garantir que nosso método tem bom performance na detecção do foreground que os métodos do estado de arte. Essas aqui são nossas referências e muito obrigado pela atenção.
So thank you, Chandler, for the presentation. We ask now to Leonardo to present his poster.
Estão me ouvindo?
Sim.
Show. Deixa eu ver aqui para compartilhar a tela, então. Estão vendo a minha tela?
Sim, estamos vendo.
Show. Então vamos lá. Olá, pessoal. Meu nome é Leonardo Luiz Herrero e hoje eu vou apresentar o trabalho intitulado Automated Methodology to Describe Mobile Signal Coverage on Highways. A case study considering data uncertainty. Introduzindo, então, o trabalho, sabe-se que atualmente a infraestrutura de rede móvel ela carece de melhorias tanto na velocidade da conexão quanto na disponibilidade de sinal em diferentes áreas. Pensando nisso, o projeto de lei 1721 de 2019, ele vem para buscar disponibilizar a internet móvel em no mínimo 60% dos trajetos das rodovias federais. E as operadoras móveis, elas até chegam a disponibilizar para os seus usuários mapas de cobertura. Porém, quando nós vamos para a prática, nem sempre ocorre aquilo que diz o mapa, que é mostrado lá. E, além disso, também ainda não tem formas claras de verificar como é que está, ao longo de um trajeto, a disponibilidade do sinal. Pensando nisso, então, nós pensamos em um problema de pesquisa. O nosso problema de pesquisa envolve avaliar a disponibilidade do sinal móvel em rodovias, em conjunto à incerteza dessa informação, utilizando ainda formas automatizadas para a coleta de dados. Aqui nas figuras eu ilustro alguns dos desafios de pesquisa que foram enfrentados inicialmente na nossa pesquisa. Então, na figura 1, temos o problema da sobreposição de dados, então, onde conforme nós vamos plotando os dados no nosso mapa e conforme vamos aumentando a quantidade de amostras, as mesmas vão se sobrepondo, então, sendo aqui necessária alguma forma de plotagem, de agregação de dados. E na figura 2 pode-se ver o problema da distribuição desigual dos dados. Então, onde em vias menos utilizadas, eu vou ter uma quantidade menor de dados, se comparado com as vias com maior tráfego de veículos. E aí que vem a necessidade de considerar a incerteza da informação em locais onde eu tenho uma quantidade menor de amostras de dados. A nossa metodologia, então, proposta, a ideia é que seja uma metodologia automatizada que permita a avaliação da disponibilidade do sinal móvel em estradas. Utilizamos em nossa análise dados básicos como a latitude, longitude, a data daquela informação e sinal, que é um valor booleano. E complementamos esses dados com o uso de APIs para a obtenção do tipo e do nome da via. E depois disso, então, realizamos a filtragem dos dados, a remoção de ruídos, e por último é realizada uma agregação espaço-temporal dos dados e a geração de mapas com o cálculo da disponibilidade e da incerteza do sinal. Aqui na figura mais acima eu ilustro a questão da agregação dos dados em quadrantes, então a figura azul aqui ilustra uma estrada, e os quadrados aos quais ela depois vai ser dividida, vai ser segmentada. Então, todos os dados que pertencerem a um determinado trecho da via vão sendo segmentados nesses quadrados para que assim nós possamos fazer a extração de dados estatísticos de sinal. E mais abaixo aqui na figura também tem a nossa metodologia ilustrada. Delimitação do problema, então, os dados utilizados foram todos fornecidos de maneira anônima por uma plataforma de rastreamento veicular, então são todos dados de dispositivos IoT do mundo real, vamos dizer assim, e compõem registros de veículos rastreados dos anos de 2017 a 2020. Os atributos são o ID Object, que é uma referência a um dispositivo, anonimizado, claro, latitude, longitude, a data e a hora da informação, e online. Esse campo online ele é um campo binário, onde ele vai indicar, se for é sinal, quer dizer que naquela latitude, longitude, naquele momento, o equipamento tinha sinal para realizar a transmissão da informação, e se for 0, é sinal que ele não tinha sinal, que ele armazenou essa informação em memória e transmitiu posteriormente quando ele tinha sinal. Para a geração do dataset, então, nós definimos como regra a utilização de dados de rodovia somente do Rio Grande do Sul e tirando as vias menores. Então, tiramos ruas e avenidas para deixar somente BR, RS, vias de mais alto nível. E também delimitamos o estado do Rio Grande do Sul para que era onde tinha um conjunto maior de dados, mais completo das rodovias em si, apesar de ter dados do Brasil inteiro. No final, totalizaram um pouco mais de 27 milhões de registros, de um total de 861 dispositivos diferentes utilizados nas análises. Para os nossos experimentos, nós utilizamos a linguagem R para a filtragem dos dados, geração dos resultados em mapas. E os dispositivos que foram utilizados, todos eles operam na rede 2G da Vivo. Eles utilizam o chip MT2503 da MediaTek. Então, delimitamos ali o nosso trabalho também a uma análise sobre o sinal 2G. Começando então pelos nossos resultados iniciais, foram gerados mapas. O primeiro é a análise da distribuição espacial dos dados. Aqui foi aplicada uma função logarítmica para gerar essa imagem, onde a cor roxa, puxando para o azul, indica baixa quantidade de amostras e a amarela indica uma maior quantidade de amostras. Então, dá para ter mais atenção aqui a região noroeste do estado, que é a sede da empresa que forneceu os dados, que tem um maior conjunto de dados. E depois algumas rodovias e a região metropolitana aqui que possuem maior dados, e a rodovia de ligação ao Porto de Rio Grande. Aqui nós utilizamos um delta de 5 km, então quer dizer que cada um desses quadrados possui 5 por 5 km, e todas as amostras são agregadas dentro desses quadrados. Depois, então, foi avaliada a disponibilidade e a incerteza do sinal, que era o grande objetivo do trabalho. Aqui foi definido como regra que quadrantes com menos de 5 amostras, com menos de 30 amostras, são considerados como com alta incerteza sobre o resultado. Então, locais, quadrantes que tivessem abaixo disso vão ser considerados como com alta incerteza. E os outros, então, vai sendo avaliado de acordo com a quantidade de amostras. Aqui o nosso mapa gerado, então, vocês podem ver que ele possui duas escalas, uma da disponibilidade de sinal e o outro da incerteza. Na disponibilidade do sinal, a cor azul indica uma alta disponibilidade de sinal e vermelho uma baixa disponibilidade de sinal. E na incerteza é uma escala de transparência de cores, então as cores mais sólidas indicam uma alta incerteza, então o mapa ele acaba evidenciando os pontos onde tem uma maior incerteza sobre o resultado, e as cores mais opacas, mais transparentes, indicam uma alta certeza sobre o resultado. E aqui, sim, já conseguimos tirar algumas análises da qualidade do sinal. Então, pegando, por exemplo, regiões mais da região noroeste, norte, pode-se ver que grande parte das rodovias elas oscilam entre uma disponibilidade média até ruim de sinal, e pegando regiões, por exemplo, como a metropolitana, aí você já tem uma disponibilidade de sinal muito maior. O que é plausível, né, dada pela população aí, região noroeste, norte do estado aí possuem geralmente cidades menores. Então, as rodovias aí, geralmente, elas vão ter sinal mais quando cruza pela cidade. Quando está longe, ainda não vai ter tanta disponibilidade de sinal. Como conclusões, então, a nossa metodologia ela se mostrou bastante prática, eficiente e flexível, onde com dados bastante simples e em poucos minutos nós conseguimos gerar mapas de disponibilidade do sinal 2G. Porém, outros tipos de sinal também podem ser utilizados nessa metodologia. Basta utilizar dados que sejam provenientes de outras redes, por exemplo, 3G, 4G ou até mesmo a 5G. E ao contrário de outros trabalhos, a nossa metodologia ela traz também a avaliação sobre a incerteza dos dados. Quando se trabalha com dados de crowdsourcing, de diversas fontes, aí, a incerteza ela acaba sendo bastante necessária, porque justamente você não vai ter uma distribuição igual dos dados. Então, fazer essa avaliação é algo bastante interessante, importante nos trabalhos. E, claro, também trazemos aí resultados sob o ponto de vista de dispositivos IoT do mundo real. Então, como os dispositivos IoT estão conseguindo sinal na verdade, aí, na realidade mesmo. Com trabalhos futuros, nós pretendemos nos aprofundar no cálculo da incerteza e também explorar a divisão das vias em segmentos. Ou ainda também a agregação de dados por regiões de similaridade para assim ter uma visão mais macro do serviço de cobertura. Então, talvez até trabalhar com segmentação da via e analisar em diferentes segmentos da via, ao invés do uso de quadrantes, como está se comportando o sinal, por exemplo, a cada quilômetro, ou a cada 10 quilômetros aí, para que até o próprio usuário possa saber, ah, não, nessa região, estou entrando agora em um trecho que está baixo de sinal, ou não, o próximo trecho ali na frente tem uma qualidade de sinal melhor. E, claro, nos aprofundar no uso das imagens aí para fazer essa representação. Aqui eu trago as principais referências utilizadas no nosso trabalho. E meu muito obrigado pela atenção de todos aí. Depois fico aberto a questionamentos.
Obrigado, Leonardo, pela excelente apresentação. I'm going to ask to Andrea to present her work. I'm also going to ask the presenters to try to fit their talk in 5 minutes, okay? So we will not extrapolate the time. So, Andrea.
Okay, can you hear me?
Yeah.
And can you see my presentation?
Yeah, we'll see.
Okay, hello, my name is Andrea Macaribaus, and I'm going to present the first part of this project that consists in the development of a modular device for automated and reliable mapping of nuclear facilities. The main objective of my work is to perform an accurate radiological mapping in the nuclear facilities under dismantling. But what is dismantling? I didn't know before coming here what was dismantling. So I'm going to explain very briefly what is. It's when a nuclear power plant, it has to be deactivated. So you have to guarantee that there is no more radioactivity in this facility, in these nuclear facilities. And to do this, you perform the radiological mapping. That is, you do a geometric representation of this facility and you localize the radioactivity values that are present in this facility to localize if there is a contamination, if you have to clean something that's contaminated, and so on. So nowadays, this work of radiological mapping is performed manually by the radiation protection operators, that they go to the nuclear facilities, they take the values of the radiation monitors, and they note by hand in matrices like here in these figures. However, as you can see, there is many drawbacks in this method, like as it's more prone to human errors, it may be exhaustive for the operators and also exposes these operators to a possible contaminated environment. So there is some technologies proposed in the industry and literature that combines the radioactivity monitors to algorithms, to Islam algorithms. The speech just before now talked a little bit about the Islam, just briefly. And they are a kind of algorithm that allow me to reconstruct the environment while I'm localizing the sensor in this environment at the same time. However, the solutions proposed in the literature, they are are usually bucket, as you can see in the figure. They are not adapted to all the radioactivity contaminators monitors, and also they require post-processing. So in this project, we proposed the development of a modular device for online 3D reconstruction and radioactivity measurements localization. For this, I'm working this first part of this project that consists in the development of an embedded SLAM device. That is, I want to choose a SLAM algorithm to perform embedded implementation of this algorithm. So I'll have a small device that it can be coupled to no matter what measuring instruments. And then at the end of this project, we obtain the radioactivity imaging integration, the 3D visualizing of the radioactive source, and so on. So some questions arose in this point, like which SLAM algorithm is the most suited to reconstruct nuclear facilities, and also which electronic architecture is the most suited to embed this algorithm. And for deal with these two questions, I started by performing to identify the state of the art of visual SLAM algorithms. I limited my research to visual SLAM algorithms since they are embeddable, and also they are compact, the size of the sensor. And these are the algorithms that I studied, and they can be based on the use of a monocular camera or more than one monocular camera. The camera combined with the natural measurement unit, the combine of the camera and depth sensor. Then I studied all these algorithms and identified four main criteria to observe in my scene that directly affect the performance of these algorithms. They are textures. For example, there are algorithms that they are based in the observations of the corners. So if there is no corner in my scene, I will not be capable to do the reconstruction. The size of the reconstructed environment, if there is the reflective surfaces, and if there is brightness variation. Then, based on these four criteria, I visited several nuclear facilities and I characterized them concerning this criteria. And then I could compare, do a comparison based on the return of the literature of my algorithms. And then I selected 5 main algorithms that in theory would have a good performance in reconstructing nuclear facilities. Here, this figure summarizes my conclusions. Just to explain a little bit this figure, I'll take here this algorithm and SLAM. It's an algorithm that's robust to brightness variations. That is a characteristic that I encounter in nuclear facilities. It's an algorithm that's robust to reflective or transparent surface. It's an algorithm that is robust to lack of textures. That's I encounter this condition frequently in nuclear facilities. However, it's not an algorithm robust to big size facilities that I may also encounter in nuclear facilities under dismantling. Then I implemented these algorithms. Thanks God, most of them are open source. And however, I could not compare them because there is no public data set that's representative enough of my nuclear facilities that has the same characteristics or that shares the same procedures followed by the nuclear operators. So, solution, I constructed my own data set. And to construct my own data set of nuclear facilities, I had before to conceive a first prototype of my compact device here. That's just a first prototype. That's why it's huge like this. And I developed this hardware integrated system based on 2 monocular cameras in the stereo configuration. Inertial measurement unit, this orange point like here. A LiDAR. I'll not use the LiDAR at the end, but it will enrich my data set, and all this was mounted in a radioactivity contamination monitor here, a surface radioactivity monitor of alpha and beta contamination. Now, I'm benchmarking my algorithms, and I'm using some criteria that considers the algorithmic level, like the algorithm's complexity, and also the user level as the initialization process. For example, the OrbSlam that I didn't select here, the OrbSlam 3, it requires, for example, some aggressive movements to initialize the systems, and that's not practical for the operators to do in real life. And then after I benchmark these algorithms, I may adapt the chosen algorithm for some electronic architecture, and then define the most suitable electronic architecture to embed this algorithm. Thank you very much for your attention. Don't hesitate to ask me questions in Portuguese, because I'm from Brazil. And that's all. Thank you.
Thank you, Andrea, for your nice presentation. So I think we can move to the questions for the first 4 posters presented here. I think it's better if we concentrate the questions for for one single author than the other. Okay. So from the audience, do you have some question for the first poster presented?
I have one question. So if anyone, if no one has, Alexandre, congratulations on your work. I just want if you could explain a little bit about how many videos you use during your training, and if they are a part of a public data set, or can you explain a little bit about this?
The Italian project called PlusMe released a series of preview videos around 30 seconds each that showed the toddlers playing with the PlusMe interactive toy, and together they compose an 8-minute video that we used as just a sample of this 80-minute videos. We use 819 frames. But we use the 80 videos. We sample 100 videos each, 100 frames each. I'm sorry. We use for training for 400 frames, for validation 200 frames, and for test 200 frames. And though each 100 frames for one separate video. So yes, we can say that this is a public data set because they showed in their main page of the PlusMe website.
Okay, thank you so much. Congratulations again on your work.
Thank you.
Thiago, I think we can move to the next author, Shander. Do you guys have any questions? Second work, foreground detection based on subspace tracking.
I see some in the audience. Okay. If anyone has, I can ask my question. So from the results you presented, Shander, it seems that your foreground segmentation produces like a bubble around the foreground. Yeah, you don't have noise scattered on the map, on the foreground map, but you have some extension in your foreground objects. Could you explain why it happens?
Eu posso falar em português?
Sure.
Yes, sure, no problem.
Tá. Bom, nessa parte, nós utilizamos um algoritmo chamado detecção de falência. Então, pegamos o foreground estimado, mas esse foreground tem elementos que não foram parte dele, né? Então, utilizamos um algoritmo de saliência e ele pega o foreground e começa a remover os demais elementos. Mas o problema é isso, que ele pega um pouco demais, né? Ele pega um pouco demais, então nós estamos trabalhando nessa parte para tentar remover essa parte demais, não, nas bordas. Tá, esse geralmente está acontecendo, né? Mas já achamos o problema, identificamos e agora estamos trabalhando nisso para ter uma melhor performance, né? E eu acho que melhorando isso também vamos ter um melhor F-mission, né? Já que, tipo, para detecção ao foreground simplesmente são a identificação de objetos em movimento, né? Só isso. Então, mas não tem uma métrica para avaliar. Nesse caso, nós estamos usando a métrica F-mission para avaliar a performance na segmentação, na verdade. Né?
Tá legal. Obrigado pela explicação. Parabéns pelo teu trabalho de novo.
Obrigado.
So we can move next to the next work. So it's from Leonardo, methodology to describe the mobile signal coverage on roads. Do you guys have any questions for Leonardo? Please feel free to ask. If you want to ask in typing in the chat, we can read. No one? I will ask a question. So, Leonardo, do you have an idea how can you validate your approach? You can speak in Portuguese, no problem. You can answer in Portuguese.
Português, please.
Então, tu terias tu pensaste em alguma forma de validar, assim, os teus dados, de algum jeito?
Validar, você diz, de ter estatísticas que mostrem?
Assim, penso mais uma forma geral, assim, de exatamente como tu mostrar, assim, porque tu nos mostrou ali os mapas e tudo, né, mas como exatamente tu poderia mostrar, digamos, que teu trabalho tá bom, por exemplo, comparando com algum outro trabalho ou algo do gênero.
Sim.
Se vocês pensarem em alguma coisa assim.
Nós, no caso, estamos utilizando como referência os trabalhos aí existe um projeto da União Europeia, a MORO, e eles utilizam dados, ali até estava nas minhas referências, mas eles utilizam dados coletados em trens para avaliar ao longo da rota e como é que é feito essa qualidade do sinal. Nós estamos utilizando esses trabalhos bem como base, assim, para nós ter uma noção de como ter, de fato, essa validação ali. Então, a ideia agora, o que foi apresentado é bem o nosso início do trabalho, mas a ideia, assim, é aprofundar nesse sentido para nós ter aí formas de mostrar que realmente é aquilo que está acontecendo na realidade.
Não, perfeito. Parabéns pelo trabalho, Leonardo. Muito bom. Obrigado.
Obrigado.
So moving next to the work of Andrea, a modular device for automated and reliable mapping of nuclear facilities. Do you have any questions? Please feel free to ask for Andrea.
If anyone has, if I can ask a question. So, you reviewed some works on Visual Islam that use only one camera and construct the scene from that, or a camera plus IMU, or the camera plus a depth sensor like LiDAR, but could not you like combine them, all the sensors?
All the sensors, yes, I could. However, I cannot use the depth sensor. Actually, I did not select the depth sensors, and because actually it's not robust to the reflexive surface that I encounter in the nuclear facilities, because a lot of nuclear facilities under dismantling, they have a lot of equipment to manipulate the source, and they are based on metal, and the depth sensors, as it's based on the return of the light, it doesn't work. And also there is another procedure followed here in France for the dismantling environments, that when an environment is contaminated, they put some sort of transparent surface around. So I cannot reconstruct, like that's why I also don't use LiDAR. Like here in the top, in the top of my poster, you can see a LiDAR reconstruction, but it's an exception of nuclear facilities that I took to do this reconstruction. So like I mostly use the camera, stereo camera, and the inertial measurement unit actually. But I could combine them, yes.
Okay. Yeah, I think we are rushing the time, so I think we can move to the next block of presentations, right? Thank you.
Thank you for all the authors for the first block. And I think we can start calling the next 3 works we have. So we start with Luis Javier Ontanon with the work Pseudo-Random Bit Generator based on a hyper-chaotic system.
I'm not seeing Luis, maybe. Luis Javier.
Is Luis Javier here? We also have Maria Luiz Pinheiro from UFSC with the work Brazilian Beaches on Dune Status.
Yeah, she's here. Okay, thank you.
Okay, and we'll go in the last one will be Rafael Basileu Sanchez Ferreira from UFPA. The creation of a virtual scenario for generating synthetic data sets for use in agriculture.
Okay, if you have authors from the posters of Rafael and Luis Javier that are not the ones that we called, they can join us as well. So I think we can play the videos from those posters that we don't have the authors here. So I will share my screen now, and we will proceed with the order predefined.
Okay.
So 1 second, please. Can you see the screen and the video and the audio?
We cannot hear the audio.
Can I do it? I'm not sure. No?
No, still not hearing the audio. Maybe we can ask Maria Luiz, which is present, to go first and try to solve these technical issues. Is it okay, Maria Luiz? Can you present?
Sure, no problem.
Okay, thank you. So whenever you want to start.
My screen is visible?
Yes.
Oh, thank you. So, greetings to all. My name is Maria Luiz Pinheiro, and I'm going to present the work entitled Brazilian Beats and Dune Status, 2 Decades of Detection Using Machine Learning. This work is also presented by the Federal University of Santa Catarina. Introduction. The Mapemas project was a pioneer in the automated detection of coastal features on the Brazilian coastal zone, BCZ, analyzing from 1985 to 2018. So the mainly proposal of this work is to classify Brazil's beaches and dunes, BED, presence over a 35-year time series, so from 1985 to 2019. Aiming with this to improve the Mapemas project coastal cover classification with a methodology executed totally inside the Google Earth Engine project. Here we have a summarization of the methodology. In blue, we have the mosaics generation steps. In green, we have the pre-processing steps. In yellow, the classification and post-processing steps. In red, the accuracy assessment steps. And in coral and indicative that all the results achieved with this work must be freely available on the internet. So for the creation of the annual mosaics, we utilized Landsats, the satellite Landsats, collection 1 tier 1 top of atmosphere data. The image we utilized to produce annual cloud-free composites using for this the median reducer and the BKA band, also known as the quality assessment band. After the preparation, the mosaics were subsetted according to the geographical or geological likeness of beaches and dunes presence. After this, we decided that the mainly classifier utilized would be the random forest classifier. Utilizing for this, the K-mean algorithm has a pre-processing steps for the creation of the first instance of the label or the mask that is utilized to train the random forest. Actually, this approach of using the random forest is considered a state-of-the-art approach in the remote sensing. And for this, we utilize the default parameters for this classifier as defined in the Google Earth Engine library with 100 trees at most. And here we have a summarization table of all the attributes and parameters. So for random forest, we utilized approximately 1,000 samples per class per year per geographical region with 9 attributes between spectral bands like green, red, near, SWE 1 and SWE 2, and indexes like NDVI, EVI, MENDWI, and NDCI, aiming with these 2 targets, beaches and dunes and non-beaches and dunes. And in figure 1, we can see, summarization of the big steps. So 1A, we have a mosaic example, 1B, the clusterization process, and 1C, the final results of the random forest. As a post-processing steps, we applied spatial temporal filters to fill in possible no data values, remove the salt and pepper effects, and non-permitted class transitions. And with this, we defined 10 pixels or about 1 hectare as a minimal mapping unity, utilizing also a 3-year window for concordance agreements. And in terms of accuracy assessment, we executed a map-to-map agreement to evaluate the rates of concordances and disagreements between the results obtained here and the map biomas collection 4.1. The analysis was done on the year 1985 and 2018 from both datasets, and the statistical results can be seen in this GitHub link. So in summarization, graph 1 presents the statistical achievements of this work. The gray bars represents the total amount of beaches and dunes in area in kilometers square in all the Brazilian coastal zone, and the lines indicates the same approach, but in terms of geographical regions. So in light green, we have the area in the north region, in the dark green, we have for the southeast region, in yellow, the south region, and in blue, the northeast region. Overall, it's very visible that over this time span, we have a reduction in the presence of this type of land cover. In fact, in absolute terms, about 741 kilometers squared were lost from this time span, mainly in the south region, who lost approximately 450 kilometers squared, and the southeast region, who lost approximately 136 kilometers squared. The main drivers, especially, says that attributed to this expansion of urban industrial structures over the Brazilian coastal zone and natural processes, such as the micro-tidal system in the North region and the vegetation regrowth on top of dunes in the South region. Finally, we assessed that we achieved a higher quality in the recognition of this type of land cover, with reducing noise in this process. However, the mosaics could be improved by taking in account the micro-tidal mechanisms, mainly in the North region, and the phenological variation in the dune top vegetation, in the South region. The last could be achieved possibly by field studies or experts analysis. And here I'm presenting all the reference for this particular person. Thank you.
Thank you, Maria Luiz, for your presentation. Well, let's try to first let's see if the authors are here now. I don't know. Luis Javier, oh, sorry. Yeah, Luis Javier Antanon is here. And Rafael Basileu Sanchez Ferreira. Okay, so I think we can try again broadcasting the video.
I'll try to share here again, Thiago. Let me just a second. Okay. Can you see my screen? YouTube with YouTube video? Okay.
No, we are seeing metaverse.
Ah, okay. So
I'm seeing myself.
okay, just a second. Now I think. Okay. Can you see now? Okay, let's check the audio.
It's working, but it's too.
We need to increase the volume, maybe. Can you hear, Thiago?
I'm not sure if the audio is being broadcasted.
Based on an
yeah. Yeah,
Okay.
if you can increase the volume and put it in flow.
Okay. Okay. I'll start then.
Greetings. My name is Luis Javier Antañón, and on behalf of my coworkers, I present the work entitled "Random Bit Generator Based on an Hyperchaotic System." As an introduction to the work, let me begin by saying that there are two ways in which nonlinear dynamics may be obtained. The first one is generated by using the multiplication of the states. These nonlinearities sometimes result in strange attractors, as in the common examples of Rosler and Lorentz chaotic dynamical systems. The second way is using piecewise linear functions that change values regarding some specific conditions, as it happens for the nonlinear function in Chua's chaotic system. In this last case, strange attractors can also be generated by the solution of the system. Therefore, in this work, we propose a nonlinear system composed of a linear matrix A and a piecewise commutational vector B. The system will present 4 degrees of freedom. The reason for these dimensions is that it is known that chaotic systems need at least 3 degrees of freedom to be generated, but at higher dimensions, a richer behavior called hyperchaos can be obtained. The coefficients of the linear matrix are represented here. And the form of the affine vector will be changing due to its control law regarding the position of the x1 state. It can be appreciated that for each value of B, the solution of the system will be changing. The switching control law can be adjusted depending on the number of domains or divisions that one needs. For example, 2, 3, 4, 5, or more domains. And depending on the number of domains introduced into the system, an equilibrium point will emerge in the center of each scroll. Here, we are depicting the solution of each corresponding switching law of the. Now, why would this be important for encryption or pseudo-random generators? The response to this lies in the sensitivity to the initial conditions that chaotic system presents. We will take advantage of this intrinsic property to build a stream cipher encryption method. The pseudo-random bit generator is designed as follows. A key will be created from the solution of the 4 state trajectories of the hyperchaotic system, resulting in a double precision floating point of 10 to the 14 8-bit sequence. The stream cipher process is given by the following equations, where C and P correspond to the pixels in the cipher and plane images, respectively. Here, we depict the encryption process. On the left-hand side, the plane image. In the center is the result of the encrypted image, and on the right-hand side, the decrypted image. To prove the effectiveness of the algorithm, here we present some statistical analysis. First, on the left is the histogram of the number of pixels regarding the grayscale of the plane image, and in the right, histogram of the encrypted images depicted uniformly. We present a pixel correlation analysis of the different encrypted images. Volume was calculated with the cipher images generated from a pseudo-random bit generator with systems presented a different number of scrolls. In the first column for the plane image, we can see highly correlated pixels, meaning that the pixels are very similar in the grayscale. However, when the number of scroll increments, the pixel correlation decreases significantly. Finally, the results for the entropy of the image cipher with a different number of scrolls measuring the randomness of the texture of the image, where it can be appreciated that the encryption presents a high entropy when the number of the scroll increases in the pseudo-random number bit generator. To conclude this presentation, we can remark on the following. The piecewise linear systems can generate complex hyperchaotic multi-scroll trajectories which are suitable for pseudo-random number generators. An important characteristic of this type of system is that for each equilibrium point, a scroll emerges in the graphical solution. And the number of scrolls contributes significantly to the encryption process of the grayscale images. Thank you for your time.
So, I'm not sure if Rafael is here. If he's not, we can share the video as well, his video as well. Okay, Dennis, could you please play?
Yes, let's check if it's all right again.
Olá, me chamo Rafael Ferreira.
Can you hear? Okay, starting now.
Olá, me chamo Rafael Ferreira e sou o primeiro autor do curso de Create Infra Virtual e Cenário Inglês, Data 7, Use e Agricultura. Os outros autores são o Conhecimento, Wanda Clotal, Eric Pina e Aldemar Clotal. Pois bem, nosso trabalho é sobre criar um cenário virtual para a geração de datasets sintéticos de agricultura. Como vocês sabem, ela é uma atividade fundamental para a sobrevivência. Logo, novas tecnologias para melhorar a qualidade e a quantidade de pesquisas pesquisadas uma após outra. E na fronteira científica, está o uso de inteligência artificial, ou IA, por meio de drones ou veículos terrestres, por exemplo, para analisar e, se precisar, intervir na plantação. Entre o uso de IA, podemos citar o monitoramento da qualidade das plantas, o uso e a quantidade de fertilizantes necessários e a análise de ervas daninhas, que essas ervas elas competem com a planta plantada desejada milho, cana-de-açúcar ou soja, por nutrientes do solo. A tecnologia que nós utilizamos na fazenda atualmente se chama Smart Farm. Há várias vantagens em usar IA na plantação, entre elas podemos citar monitoramento remotamente de grandes faixas de terra e economia de tempo, trabalho e recursos financeiros. Mais precisamente, além disso, nós também podemos usar IA para identificar ervas daninhas na plantação com base em uma foto, por exemplo. A gente pode utilizar a técnica chamada de segmentação semântica, nós podemos utilizar uma inteligência artificial treinada para isso, e tem como objetivo, em uma foto, classificar cada pixel em uma classe. Então, por exemplo, uma foto de uma plantação, como nós temos no pôster, o que é erva daninha e o que não é, ou o que pode ser erva daninha, o que é solo e o que é planta. Entretanto, para se treinar e testar uma general desse tipo, é preciso de dados para compor um dataset robusto e grande. Esse dataset, em momento, seria feito a partir de fotografias, por exemplo, de uma fazenda que tem uma produção, por exemplo, de açúcar, soja ou de milho, como estado, infestada de ervas daninhas. Essas ervas daninhas têm que ser catalogadas com essa quantidade, por exemplo, e elas têm que ser em uma foto separada, o que é uma erva daninha e o que não é, para poder a máquina aprender. Entretanto, para fazer isso na vida real, nós precisaríamos de muitos recursos, como câmeras, drones, ajudariam muito, recursos humanos, terra, fazenda, e recursos financeiros que, às vezes, nem sempre pesquisadores e empresas que querem criar uma rede assim possuem. Então, o objetivo do nosso trabalho foi gerar uma fazenda virtual de cana-de-açúcar fechada por ervas daninhas para capturar fotos e gerar um dataset a ser utilizado em uma rede neural de segmentação semântica. Essa criação foi possível por meio da engine gráfica Unreal Engine 4 e o software de modelagem 3D Blend. A Unreal Engine 4 possui ferramentas para construir um terreno, qual na simulação possui irregularidades no solo para simular o solo de uma fazenda real. Um declive mínimo ali, uma erosão. A textura utilizada no solo nas plantas foram baixadas na internet e o modelo perdido da cana-de-açúcar das ervas daninhas foram feitos no Jung. O preenchimento do solo com as plantas foi sistematizado com a ferramenta Blueprint da Unreal Engine, a qual permite programação por meio de blocos lógicos. As canas nascem de forma reta e as daninhas de forma aleatória, dentro de uma bound box, uma caixa que dentro dela está toda a plantação. E a quantidade de cana que nasce, ela é calculada com base nessa bound box, nessa caixa. E a quantidade de daninhas é calculada em relação à quantidade de cana. No nosso exemplo, nós colocamos uma porcentagem de 13%. Então, após todo o ajuste no cenário, foi utilizado o plugin open source i5 da Microsoft para simular um drone no cenário. Esse drone será responsável por tirar fotos da plantação. O drone tira duas fotos, sendo que uma seria a imagem normal, que a gente captura da real, colorida, com a erva daninha, o solo, o reflexo do solo. E a outra seria o label, que seria uma imagem preto e branco, apenas com o objeto de interesse colorido. No caso, seria a erva daninha. No caso, tem formato de cinza, como pode ser no pôster. Então, roda da seguinte forma. Damos play na simulação e o drone nasce. E por meio de um código feito em Python, esse drone roda a plantação, captura as imagens e em seguida deslocar até outro ponto do mapa de forma aleatória. Após isso, a posição das ervas é randomizada para gerar mais diversidade no dataset. Após isso, outra foto capturada e todo esse algoritmo é rodado diversas vezes até que chegue no limite de fotos. Nosso exemplo, nós fizemos um dataset com 200 fotos. Cada foto com uma qualidade de 2048 por 1024 pixels, como pode ver no post. O código de segmentação semântica com base na IEEE está sendo feito para validar o uso dessas fotos em uma rede neural. Bem, agradeço a todos e tchau, tchau.
Okay, thanks, Dennis, for broadcasting. I think we don't have the authors of those two last posters, so I put here the emails if the audience can wants to ask questions. We have Maria Luis here, so Anyone has questions for Maria Luis? So if anyone does, I can make some questions. So what's the granularity of your data? Do you have samples, I mean, data from 1 year to the other, or for each month scale?
Actually, for the Landsat satellites, it rotates the Earth and takes the same image of a scene that's called with a time slot of approximately 16 days.
Okay.
So each 60 days, the same scene, the same great scene, is imaged again.
Okay.
So approximately we have per year, sometimes less, sometimes more, 23 images. And that is which we do the median reducer of all those images to make a composite.
Okay. And another question that I have here is that you concluded that we have actually a loss of beaches and dunes in general case, right?
Yes.
And they occur because the natural processes and expansion of urban areas, right? Is it possible to further classify, right? Understand what proportion is responsible for this loss in terms of natural expansion or, urban expansion or natural processes? I mean, do you know how much of this loss is due to one or the other?
Well, the dynamics are opposite, because usually the urban expansion is always in the growth time, and the vegetation has a cycle. And even when we are analyzing the satellite images, they represent different spectral signatures. So usually when it's a vegetation on the dune tops, usually is not very close to the ocean, because the classification of dunes is kind of it's separate from the beach sides. So if you analyze just the linear, the coastal line, we could observe the cities. We have already, also in the map biomas and also from IBGE, the vectors of all the cities that are in the Brazilian coastal zone. So it is possible to try to differentiate this. However, these vegetations, they are not like statics. In the south, we have many pine, we have many cultivation of pine trees. So there is kind of a seasonality of this. They are planted, they have, I did research, they have approximately sometimes 5 years, sometimes 10 years, depending on the species. And after they are cut, and another pine trees grows in the place. So it is possible to do this analysis, yes.
Okay. Well, thank you for your answers. Do you have any other question for Maria Luis? So let's thank the speaker. And I think we can end our session. I would like to thank you all for being here and watching these amazing presentations. I don't know, Dennis, you want to talk?
No, just thank again one more time for the speakers, such incredible works, and invite you to join us again at 13:30 p.m. With Simon Niklaus from Adobe, which will be our speaker. And yeah, that's it. Thank you again for joining us.
Thank you.
Hello. I just lost my connection. I'm back now.
I can hear you, yeah.
Okay. Sorry for that. Okay. So welcome everybody. My name is Guilherme Correa. I'm a professor with the Federal University of Pelotas, and it's my pleasure to welcome our guest, our speaker for this afternoon. He is Simon Niklaus. Simon is a research scientist at Adobe Research, where he's working on video processing and novel view synthesis. He received his PhD at Portland State University in 2020, and his dissertation topic covered novel view synthesis in time and space. So, Simon, thanks for joining us here at DPVSA, and the floor is yours now. Feel free to share your slides and talk to us.
Yeah, thanks for the introduction and thank you for having me. Let me make sure this works. Slideshow. Can you see the slide? I hope so. Let me go back and check. Okay, I'll assume that you can see my slides. Where did the slide go? Okay, here we go. All right, let me get started then. My name is Simon. I'm gonna give you an introduction and an overview of my recent work on video frame interpolation. If you would like to learn more about me, you can go to my website, it's niklaus.com. While I'm a research scientist at Adobe, the opinions expressed here are just my own. They don't reflect the opinions of my employer. And with that, let's take it away. So videos, I'm pretty sure you all know that videos are just a sequence of frames. And if you show them in rapid succession, they give you the illusion of a motion picture. And the task of video frame interpolation is, given 2 frames, just figure out what's going on between them and estimate and frame in between 2 frames. And in this illustration, the task would be just doubling the frame rate from 24 to 48 frames per second by hallucinating 1 frame in between each existing frame. But this is not like the only way you would use frame interpolation. You could also, of course, interpolate more than 1 frame at a time to get higher frame rates, or to just do frame rate conversion. So let's say, for example, you had like a 24 frames per second video, which is typical in Hollywood, but you had a 60 hertz screen, then you could do like a conversion from 24 to 60 hertz to match the refresh rate of the video, the frame rate of the video to the refresh rate of the screen that you're viewing it on. And oftentimes, video frame interpolation results are showed as slow motion, or sort of also. Oftentimes, they are showed as slow motion like this. It's probably going to be difficult to express this via my screen share, because the screen share is probably going to drop a few frames here and there. So if you want to see actual results that don't look like there's a few frames missing, I'd recommend you to just go to my website, just click on one of my video frame interpolation papers, and there's usually a video at the bottom that you can just watch, a supplementary video that has video results, and that is probably a better representation. This thing that I just showed here is just coming back to Hollywood. The Hobbit was shot at 48 frames per second instead of 24. And the reason for that being is that Peter Jackson was of the opinion that it just gives you better immersion in the video, because the 48 is more lifelike than 24. And the motion that he makes here is like he's making like a square, because he said that the tests that they did is that the people that watched the Hobbit in 48 frames per second, the test shoot said that there was like a whole cut in the screen and you were able to watch the real life instead of just a video. And there's some research going along with that, where people did EEG measurements of brain waves of like a video, and the higher the frame rate, the more similar the brain waves were to like brain waves as if you looked outside of the window. But I'm not a neuroscientist, so probably better to read that paper if you want to learn more. Anyway, the history of frame interpolation is pretty long. Like if you look at this paper, it's one of the earlier ones. The bottom left, it's probably difficult for you to see. It says 2000. What I find interesting here is that back then we're looking at not pixels. We were just looking at blocks, just like in videos, like video compression. Probably because it's much easier to handle pixels as group of blocks in terms of performance, like efficiency, than individual pixels. Just frame interpolation isn't just limited to like videos necessarily low. Here's just stereo footage. It's from Kitty. Kitty is stereo videos. Like they put two cameras on the top of a car and just drive around. And you can just apply stereo, the video frame interpolation on stereo footage, and you can get no audio synthesis results, which I find fairly interesting that you can just do that. And aside from that, there's also research that looked into using frame interpolation for animation in betweening. So imagine you're making a hand-drawn animation, and hand-drawn animations are really difficult. Like they take lots of time. And wouldn't it be nice if you could just like only draw every other frame? And if you only draw every other frame and then you interpolate the in-between ones, then you just save half the work. That's the wish of this paper. The problem itself for animation in between is pretty challenging because there's lots of flat textures, so it's difficult to know where does which point go to, and also the motion in animation tends to be pretty large, and that's what this paper investigates. There also is research on video frame interpolation in the context of video compression. So the idea here that this paper proposed was, let's say we have two iframes and we want to encode a p frame. Can we maybe just like not encode the p frame at all and just do frame interpolation? And the paper extends this one step further. It's like, okay, let's maybe just encode like a tiny little bit that helps us do the interpolation, and then just do get like this guided interpolation basically. So that's what we see here on the right in this illustration. Is during the compression of the video, for the p frames, we just try to encode like a little bit of information, as little as possible, that helps us with the interpolation. Like for example, if the interpolation is otherwise, like sometimes the interpolation gives you like perfectly fine results, but in challenging cases where motion is large, for example, might not. So this encoded feature, or this encoded vector, might help with these challenging cases. Other applications include creating artistic motion blur. So motion blur is not always like unwanted. Sometimes it's like meant, it's intended. So you can see the bicycle on the left. Like an artist or photographer might want to show the bicycle with motion blur to give the impression, like in a single picture, that there is motion. What you can do is, straight up on the right, if you have like a sequence of a high frame rate sequence, you can just blur them, like average them, and then you get like this motion blur. So, but if you don't have the high frame rate sequence, you could try to do the frame interpolation instead. And another example would be video frame interpolation in the context of event cameras. I'm not sure how many of you have heard about event cameras. They are up and coming, and the idea of event cameras is, instead of just taking a frame every like fixed interval, you just the pixels kind of fire when there's change. It's what is illustrated in the top right, like the camera moved, and therefore like over time, like these pixels fired. So it's a different representation of video, and people are already looking into frame interpolation in that space as well. You might wonder, why don't we just always shoot high frame rate videos? It's because it's like a lot of information, and then also the exposure time of the sensor is low, and that means that there's noise and all these things. So this paper looked into what if we had like one camera shoot at like a high frame rate but a low resolution, and have another camera shoot at like a low frame rate but a high resolution, and then maybe can we combine those to have like a high frame rate, high resolution video. We can also use frame interpolation in the context of rendering. This is, for example, if you think about Pixar, and Pixar, you can find online that they often state that it takes like long CPU, and nowadays I guess also GPU hours to just render a single frame in a video. I don't have it on the top of my head. It's probably way more than seconds, might be minutes, if not even hours. So similar to this animation in between from earlier, what if we don't have to render every single frame? What if we can just render like every other frame and interpolate the missing ones? And in this rendering context, you have also the benefit of you can feed your interpolation algorithm not only the colors, but also depth information, normals, albedo, and also the motion vectors. I mean, if you know the scene geometry and you know the camera moves, you know how the objects in the scene move, you basically have the perfect ground truth optical flow. But then cat is not really optical anymore, it's just like motion vectors. Yeah. Another project that we looked at recently was, what if we just have two similar frames? So when I take pictures, I often take a sequence of frames so that I have like a sequence of frames to choose from. And I can just choose the frame that I like most to share with my friends and family. But that means that I have a lot of similar frames, it's like these ones maybe. And the question is like, can we combine those two into animation with 3D frame interpolation? And the answer is yes, we can do that. So I hope that you can see that animation comes across via the screen share. Some more results on that. So you can get some really nice results just by applying frame interpolation on just pairs of images. The challenge is here, like usually with frame interpolation, the challenge is the higher the motion in terms of pixels, like between two frames, like optical flow essentially, the higher the optical flow magnitude, the more difficult the problem becomes. And that happens if there's lots of motion, or if the resolution is high, or both, or if the camera moves a lot. So using two frames as input and you wanting to like get like an animation like this, it's just like one of the challenging scenarios because there's lots of motion in terms of pixels. If you'd like to see more results of this, it's called Project In Between. We presented it in 2021 at Adobe Max. Adobe Max is like an Adobe conference. But if you just search for Project In Between Adobe Max, you can see the full demo of this. So let's go into my work on frame interpolation. So the first thing I'm gonna present is video frame interpolation with adaptive convolution. This is a paper that I presented like about 5 years ago at CVPR. And just let's go back to the basics. Let's say we have two frames like these two. And these two frames, you can see that things move around, and we can try to estimate, like track these pixels, like, okay, this pixel here on the top right, this pixel here on the top right of the box in this frame, keep my mouse still, is a little bit higher in the next frame. And we could try to estimate this motion, and this is done via optical flow. So you can see the blue means according to the color coding on the top right, we have to color code it because it's a 2D vector. It means it's moving to the top left. And that's exactly what we saw in the image before, or like the animation before, is that the box moved, like the top tip of the box moved to the top left, like a little bit up and left. And what we can do with this information, we can, after the motion estimation, we can do motion compensation. So specifically, we can, if we know how a pixel moves from frame 1 to frame 2, we can try to trace the path across time and interpolate a frame in between. But the issue with that is, what if that it's not a pixel correspondence, but a subpixel correspondence? Because usually you won't find like usually the pixels don't move in integers; they usually move like in floats, and then the correspondence might not always be the ideal. Or even more severe is, what if the pixel is entirely missing in the second frame, which happens if just because of occlusion, like something might occlude a pixel because it moves in front of the pixel. So instead, in this paper, we propose to just treat the problem like this, that let's consider I'm a pixel in the intermediate frame, the one that I want to interpolate. And I know that the information that is me is going to come from a region that is co-centered around my location at I1 and I2. And what I can do is I can just try to find coefficients that I then filter image 1 and image 2 by, and then I get the color information that is me, that pixel in the center. And we call this adaptive convolution. So it's like a spatially varying convolution. So for each pixel in the output, we try to find like the filters for the input. So it's quite a lot of filters, but it works, and it's like a unified framework for motion estimation and compensation. So instead of having 2 steps, it's just 1 step now. And the way we estimate these kernels is using a convolutional neural network. It's what I guess everyone would do nowadays. Back then it was not as clear, but nowadays it is. And to train a neural network, we need training data. So back then we just downloaded Creative Commons licensed videos from online and then just sampled sequences of frames from those, specifically just sequencing free frames to input frames, and then the one in between those free input frames would be the ground truth that we withhold. And then we would train a neural network, and we train it with two loss functions actually. So when we give an input to the neural network and it gives us the kernels, and we apply the kernels, and we get like the output pixel or like the output frame. Then we need to enforce a loss function between the estimated result and the ground truth. So in our case, the withheld center frame in the frame triplet will be sampled from videos. And then we compare those two. And the trick that we did here in this paper was we can apply the filters not only to the color space of the image, we can also apply to the other domains. So for example, we can apply, I guess, like a Laplacian on the image to get like the gradients of the image. And then we can filter those, and then we can compare not only the estimate color and the ground truth color, but also the estimate like Laplacian space and ground truth Laplacian space. And by doing that, you actually get like higher fidelity in the image. So this is with the gradient loss, and then this is without just color loss. So by also working in this Laplacian space, you kind of trick the network to estimate higher fidelity results instead of like slightly blurry ones sometimes. One thing that I find interesting in this paper is that you can actually visualize what kernels were used to interpolate a specific frame, and you find that they will be edge aligned. So here this pixel is like on a diagonal edge from like top left to bottom right, and you can see that reflects in the filters estimated for synthesizing this pixel. So they learn to be edge aware. And you can see also they're like slightly off center. I put my mouth in the center here. And them being off center means that they are compensation for motion. So they are doing motion compensation because they are off center, and they are motion estimation because they're off center, and they do motion compensation by like sampling pixel on the edge. And this pixel, for example, it's not along the edge, but it has motion. So you can see it's also off center, but it doesn't have like this edge aware type of thing, like it's just a single peak. And then this one is also an edge again. You can see like the kernels also are an edge, so it's sampling from an edge again. Right, some results. Because we are doing motion estimation and motion compensation in a single step, unlike these methods at the bottom, you can see actually like here in this region, we are less subject to these types of artifacts. So here in the bottom, we used like a reference algorithm for, like these are all flow-based. So they just estimate up to the flow, and then they do motion compensation using a heuristic algorithm. And we used like a reference algorithm back then, and that reference algorithm apparently introduced these artifacts, whereas ours didn't. If you would like to see more results, I'm not showing more because probably via the screen share, half of the frames will be dropped anyway. You can just go to our website, go to this paper, and look at the supplementary video. The issue with this method is that for each pixel that we want to interpolate, we need to estimate lots of coefficients. So in this visualization alone, it's 5 by 5, 25 times 2, it's 50 coefficients we have to estimate. And 50, like this is usually not enough for a practical application, because you can imagine if like a pixel moves more than, like if I need to get information from something that is more than like 2 pixels away from where I used to be. So basically, if there's like motion that is more than like just a few pixels, I won't be able to copy information from that area. So in other words, like these areas where I sample from to synthesize this pixel, they need to be as large as possible so they can estimate, compensate for large motion. So let's say we have like 10 by 10, which is also still too small. So ideally, we probably want to have 100 by 100. But then you have like 10,000 coefficients for each input image. So it's like 20,000 coefficients. And that becomes intractable pretty easily. So instead, we worked in this paper on video frame interpolation for adaptive separable convolution. and they presented that at ICCV shortly after CDPR. So the idea is, like, again, like these kernels should be as large as possible, but they grow really big. So why don't we just approximate them through separable kernels instead? So it's much more tractable, the problem. And by doing that, it not only gets faster, so you can see on the left, like it gets an order of magnitude faster, just because it's way quicker to estimate these fewer kernels, and also it gets better. I guess just because the network doesn't have to estimate that many kernels anymore. Now we can like do a better job at estimating the few to the left. Interestingly, also is that something more common nowadays as well is initially this previous paper that I showed you, we were limited to estimating 1 pixel at a time because of the number of coefficients involved. So we couldn't just like insert 2 frames and then get all the coefficients and apply those, because those amount of coefficients are just too many. We had to do it like in a, so we call it shift and stitch implementation. I can read the paper for more details, but in the end, you basically had to run the network multiple times in the input image, I think 64 times to get the full output. And during training, we just operated on single pixels. But if you actually estimate full frames, you can then be again, more interesting in terms of loss functions as you do. So on the left, you can see just a color loss function, just L1. You just take the 2 images and you do an L1 loss on those. Whereas on the right, we do a perceptual loss. And the perceptual loss that we're doing here is something that's also well known by now, is you just take features from a pre-trained network. So for example, VGG, and then you compare, instead of the image, you compare like the image in color space, you compare it in feature space. And if you do that, you kind of trick the network into learning more high frequency details. Hypothesis that I have in this regard is that the features might be a little bit more shift invariant. So if the color is like, if the texture that you're estimating is like off by like half a pixel or so, you might get a high penalty with just like an L1 loss. But if you use a feature loss, you might have a little bit of shift invariance. And then if you're producing the correct texture, but you're just off by like half a pixel or a pixel, you're not as penalized as much. Because of the nature of this problem, we also did a user study. We did this in the previous paper as well, but just wanted to emphasize it here that because of this feature loss, interestingly, the quantitative matrix, the qualitative matrix, like if you just like quantitative matrix, if you just look like the PSNR, for example, it's interesting that it tends to be better if you use the L1 loss. So if you just look at PSNR or SSIM, you get better results by using L1 loss. But as viewers, like as humans, we actually prefer the one that is trained with perceptual loss because the high frequency details are there. But those results tend to be worse in terms of PSNR than the L1 trained model. So it's kind of interesting. So since then, I kind of tend to always use 2 result models, like one that is good in quantitative benchmarks and one that is just gives you just better results because it has more high frequency components. So essentially, this paper was taking the adaptive convolution approach. It's called Niklaus et al. We just do separable kernels that improve the results already because it seems to be a simpler problem to track. And because of the perceptual, like because we estimate full frames instead of just like 1 pixel at a time, we can apply a perceptual loss. We revisited this idea recently in 2021. It's just like a pet project of mine. So like after 4 or 5 years, I was like, can we just like improve this a little bit further? Because overall, I like this idea of adaptive convolutions. Since then, they've also been used for many other tasks, for example, for deblurring or denoising, you name it. It's just like this idea of spatially varying kernels to apply to the image is very powerful. So I just wanted to revisit this idea. And on the left, you can see the results from the method we did in 2017. On the right, you can see the results from state of the art from 2021. You can see the flamingo lag is interpolated well with the state of the art in 2021, but with our adaptive step-up convolution approach from 2017. It's not interpreted well. But with subtle improvements to that method from 2017, we can then again get better results. And there is quite a few subtle improvements here and there. I'm just going to talk about one of them, which is the kernel normalization. It's also the one that gives the biggest benefits. You can see plus half a dB is pretty significant. And with these, like quantitatively, you can see like there's this Middlebury benchmark online. It's actually for optical flow estimation, but they also have a frame interpolation section. You can see that from like the 2017 method was like an average rank of 48.9, and then with SEPCOM++, which is these subtle improvements, but overall the same idea, we were able to jump like 40 places. So what are these subtle improvements? Again, I'm just gonna go into one, which is this one, common kernel normalization. So you think about again about what the network needs to do is it needs to estimate these coefficients of these kernels that we then, these spatially varying kernels that we then apply to the input image, input images. And if, like, let's say you estimate that you want to like apply Gaussian blur, you all know that once you estimate the Gaussian kernel, you need to normalize it such that all the coefficients sum up to 1. And the reason why you do it is because you don't want to make the image brighter or darker. And for the initial approach for these adaptive convolutions for frame interpolation, we just let the network estimate the coefficients and let the network figure it out. But the network had to learn that it needs to estimate coefficients that together sum up to 1. And instead, what we're doing here is we just take the kernels and we just divide by the kernel, like sum of kernels, to normalize it implicitly. And by doing that, you get like a significant improvements in terms of quality. So like on the top right, you can see the loss during training alone is like, it's nice to see that the loss all of a sudden gets much better already. The other tricks, they're all just like details, and I don't want to go into too many details in this talk, so feel free to just look at the paper. But let's go back to the formulation of adaptive convolutions. I mentioned earlier already, you want these patches that you filter to be as big as possible because you want to be able to account for as large motion as possible. And I also mentioned already that the larger the resolution of a video, usually the larger the motion in terms of pixels. So if you like double the, like if you have the same content, you double the resolution, then all the optical flow vectors will be twice as large, and that will make the problem more difficult. So ultimately, this problem formulation is like really interesting because it combines motion estimation, compensation into a single step. But the issue with it is that you are kind of limited with the amount of motion you can handle. You can just like, let's say you have like 500 pixels motion, which might be happening in 4K footage or 8K footage. Then these patches need to be like 500 pixels too, and that just seems to be like I don't think we can approach that. So while this works well, for like many cases, for like the future, like for 4K video, 8K video, for footage, lots of motion, this is kind of limiting. So we looked into a different approach instead. We'll call it context-aware synthesis for video frame interpolation. So a common pipeline for video frame interpolation is, again, this motion estimation and motion compensation. So you can do flow estimation and you can do spatial warping. You can do it just taking one frame or one optical flow estimate. You can estimate the optical flow from frame 1 to frame 2. Then you can scale it by a factor of t, let's say 0.5, because you want to have like halfway, the frame halfway between frame 1 and 2. And then you warp this. And like one algorithm for warping, you can, for example, read the Middlebury optical flow benchmark paper. They present one of these algorithms that does exactly that, and you can synthesize the intermediate frame. You can step it up a notch. You can estimate the flow in both directions, like from frame 1 to frame 2, from frame 2 from frame 1. And then you can warp both of them, and you can do some kind of blending combination of them. Nowadays, this blending step, you would typically do this with a new network. Like if you have two results that might be good in certain areas, whereas in others You could try to just combine the best of the two, and you can try to learn that using neural network. So now here's the novelty of our paper. If you do this in color space, what stops you from doing that in feature space as well? So let me explain. If you have a neural network that tries to combine these two color frames, you are not giving it as much information as you could. So if you warp a pixel to get these two frames here, the warp pixels will miss information about the context that they were in. So for example, you don't know anymore whether a pixel was on an edge or not. But that information might be useful to you if you're trying to synthesize the result by combining those two intermediate results. Because then if you know that initially this pixel was on an edge, it should still be on an edge. And that information is gone if you just do it in color space. Because, for example, for random, like you might have like inaccurate optical flow, and you might warp the pixel wrong and might no longer be looking like it's on an edge. But if you also like extract a feature space from the input image and you warp the two, then you not only have the color of the pixel, but you also have like what was the pixel surrounded by before it was warped. And that information tends to improve results quite a bit. For training data sets, you can see that there's now a difference. Now I'm making a reference. Video frame interpolation has become more and more popular. And with this popularity nowadays, there also is a standard benchmark standard training data set from a friend of mine, Tianfan. And Tianfan basically sampled Vimeo and extracted, together with his intern, extracted frames from Vimeo, from like this video platform, from Creative Commons licensed videos, as far as I remember, and just sampled triplets from those videos and made those publicly available. So nowadays, most people that do frame interpolation use a standard benchmark data set. And that just makes things more comparable, because otherwise, if I present you an algorithm with better results, but I don't use this data set, then you might argue it's like, hey, you might only get better results because your training data is better than the training data that was used for these other methods. Nowadays, I don't have this in my presentation, but nowadays there's also other data sets. For example, I think it's called the paper is called XVFI. I forgot what the data set was called, but they collected like high resolution, high frame rate videos. So they took a camera like Blackmagic has those, for example, where you get high resolution and high frame rates, and they went out around and captured videos using those. So there's also other data sets nowadays. So going again through the history of these different approaches, you can see with each improvement, like if each extension of this pipeline, from the naive approach to estimating both, warping both frames, blending them, to using neural networks to combine intermediate frames, to also using the context, you can see it gets better significantly. Like, I mean, this is from the most naive to the one approach to the one we have proposed. It's like 2.9 dB. That's like huge, really significant difference. You can also look at standard benchmark data sets. Again, this is the Middlebury benchmark, and you can see we improve, like we get better average across the board. The nice thing about these optical flow-based approaches is that you usually get arbitrary time frame interpolation for free. So another issue with this adaptive convolution approach is you don't really have control over what is the intermediate time that you want to interpolate at. If you just make a slow motion, it doesn't really matter, because you can just do recursive interpolation. If, let's say you have 2 frames input, you can estimate the one that is halfway in between those 2 frames, and then you can do like divide and conquer, and you like just estimate the result from the first frame to like the one you just interpolated, and between the one that you just interpolated and the second frame. And you can do just this recursively, and then you can estimate many in between frames. But what if you are just interested in like the frame that is at t equals 0.1, because you're doing like a frame rate conversion, for example. You're converting from 24 frames per second to 60, then you can't just estimate the frames that are halfway in between input frames. You have to do something else. But with optical flow, the nice thing is you just scale your flow by different amounts, and then you usually get this attribute for free. You can interpolate more than one frame easily and at arbitrary time steps. Coming back to this pipeline, I simplified this a little bit. There's this spatial warping, and spatial warping is not always easy. So there's two types of warping usually. There's backwards warping and there's forwards warping. Other names for these operations are gathering and splitting. So for backwards warping, that's called gathering. You just look at where a pixel points to, and you then copy the pixels, the information from the target where that points to backwards to the origin. And that is easy-ish to differentiate. You have to make it differentiable to be able to plug it into a deep learning network pipeline. For deep learning, you have to have like the gradients, because otherwise it doesn't work. And computing gradients for a bilinear backwards warping is fairly straightforward. So you can read the spatial transformers network, for example. It does the math for you. Forward warping, it's not as clear, and also there is ambiguities. So if two pixels map to the same location, like if two things split to the same location, for example, because of occlusion, like let's say you have like static background, so the motion of that is 0, and you have a moving object in the foreground. So let's say a foreground object moves in front of a background pixel, then like you will copy the original pixel, like the background, to this location, and you will copy the object that's moving to that location. So you have a conflict there that needs to resolve because of the occlusions. And that makes the problem challenging. So when we worked on this context-aware synthesis network for video frame interpolation, we didn't yet know how to make the spatial warping fully differentiable. So basically, we were able to train this half here, but we weren't able to train this half. And that's really what you want, though. You really want to be able to train the optical flow estimator in combination with the synthesis. Like you want to estimate motion that works well with your compensation of the motion. And you don't want to just like, what are good features? We couldn't answer what are good features or what is a good context to extract from the input image that then gives you information that is beneficial for motion compensation. So in this paper, we tried a few different like off-the-shelf like filter banks, and we just found one that worked well. But like, why can't we just also like learn that filter bank? Why do we have to like predefine it? And the answers to those things is because of spatial warping, we did not differentiate it. So in this paper, we looked at how can we make this step differentiable? How can we then, like if we make it differentiable, how can we train this pipeline end to end, basically? So idea, motion estimation, motion compensation, we looked at this before, but the step is not easily differentiable. So what we can do is we can start with a basic operation, which we call summation splitting. So we take every pixel and we just split it to the target, and if multiple things split to the same location, we just take the sum of it. So we don't address the ambiguity at all. Just like, okay, two things map to the same location, let's take the sum of it. And that's why you can see things get brighter here, because there's more than one pixel. So because we just take the addition of the color values, it will just get white, because it's like 2 times like something gray is going to be something white, 2 times something greenish, it's going to be something white in the end if you add enough of it, because it just gets out of the bounds of the color range. And we also show to do the gradient of this, how to compute the gradient of this. So we can implement this in a deep learning framework, given an image or 2 images, given one image, sorry, given an image and the corresponding flow, we can create the results you see on the right in a fully differentiable manner. But what does that bring us? I mean, I don't want my image to look like that. I don't want these white speckles. It's not looking good. But we can use this summation splitting operator, and this is just abbreviated by the sigma operator here. This is summation splitting. And what we can do here is, for example, we can just not only split the image with summation splitting, but also split once. So basically now we have like the splitted image, and we have a splitted image where we take the sum of the like how often does a pixel contribute to this pixel? Like how often did that happen? And then if we normalize, if we divide by that, if we divide by the splatted color and by the splatted, like how often did we splat to like this cut, like this pixel, and we divide by it, then get average splitting. So like now at least like it looks, you don't have these white outliers anymore, but you're not resolving the ambiguity. You can see that the car in the foreground is occluding the background, but it's not just occluding it, it's taking the average. So we need to be able to find a way to integrate like an importance mask. So let's say for this importance mask, we just take the depth of the image. This is what you would do in rendering. The depth is just like how far is a pixel away from the camera. We know that the car is closer to the camera than the background. Let's just say that if we had depth, which we won't estimate here, there's a paper that actually does this, but this is it's called a depth over frame interpolation. But here we'll talk about how we compute this importance metric later on again. But let's say we have like this importance metric that tells us a pixel is more important than another pixel, therefore it should be drawn in front of the other pixel. We could just try to linearly weight the entire thing. Just instead of here, like instead of splitting just once for the normalization, we could multiply our image by the importance, like the more important the pixel is, and like basically the more closer the camera is, for example, the higher we value it. And so let's say the foreground, let's say the car pixel here has like an importance of 10, and the background pixel might have an importance of 1. Then the predominant color will be of the foreground of the car, and it will ideally occlude the background. You can see it does it a little bit, but not perfectly. You can probably try to find better parameters, like you can change your important metric scale a little bit to get it look better. But the issue with this linear splatting is that you're not shift invariant to the metric. So let's say you had like this important metric, like let's say 1 and 10 again, like the car is 10, background is 1, and let's say you just add 1,000 to it. So then it's 1,001 and 1,010, and then if you take that as the importance metric, then they're going to be averaged again. So this linear splatting metric is not shift invariant. And then this is our contribution here. We basically take ideas from softmax, the softmax operator, and here's the math. In the end, if you would just take exp of the importance metric and you multiply with that, you have this nice property that if you add a constant to the importance metric z, then it just removes itself. It just disappears again. So like now we have like an important, like a way to forward warp pixels to splat pixels in a differential manner. While also like we have to incorporate like some metric to disambiguate pixels, and we integrate it in a way that where the metric is like shift invariant, we can like add a bias to that metric and it doesn't matter. And we can take this framework, we can take the same thing as before, we take the image and input images, we estimate the optical flow, we estimate a feature pyramid now. So previously we estimated context, or we extracted context, and the context was just at one level. But now, because we can backpropagate through an entire thing, we can be more flexible in what we're extracting. We just say, like, let's just extract a feature pyramid. Let's do this warping in the splatting in a feature pyramid. And then we have warp feature pyramids, and then we can have a synthesis network combine the warp feature pyramids. So in comparison to this context-aware synthesis from before, we can just extend the context to like a context pyramid, like a feature level pyramid. So we do the warping not only like in the original resolution, but also multiple resolutions. And because it's differentiable, we can train the feature extractor and the image synthesis network end to end. And maybe even more importantly, we can also fine tune the optical flow estimator. So what does it bring us? First, let's look at the different alternatives of splatting. So you can see here the softmax splatting performs best in all quantitative benchmarks, better than the other alternatives. kind of expected, but also verified through this experiment. And then because we can do this differentiable splatting, we can do a feature pyramid and like extract context, a context feature pyramid. Instead of just estimating one level, we can extract multiple levels with warping in multiple levels. And as it turns out, that improves the results. Basically, the more levels you extract, the more features, the more information you extract from the input images before you warp them, the more information the synthesis network will have that combines these warp results to the actual interpolation result. And we can do this because it's different, like the splatting is differentiable. And then lastly, we tried different flow networks just to extract the flow from. But what is important here, you can see here this bump of like half a dB between flow PWCnet and PWCnet FT is when we fine tune the flow network end to end as well. So we can, in the deep learning setting, we can backpropagate our gradients through the splatting operator with the image differentiable all the way to the optical flow estimator, and we can train the optical flow estimator jointly with the rest of the system. We can estimate optical flow that is tailored to the specific task. And there's also a paper on task-oriented flow estimation if you want to learn more about like this idea of flow that is trained specific purpose, and then it makes usually the flow better, the optical flow works better that way. When we released this paper, we actually made quite a big bump over all other methods. So we published this paper in 2020, and it took quite a while for other papers to outperform this method. And even nowadays, it's one of the baseline methods that people compare to. Like they usually compare to our adaptive convolution stuff, just because it's not flow-based. And then they compare to the softmax studying stuff, just because it works really well. Yeah. And coming back to loss functions again, I really find loss function interesting. Just showing this example to show you that on the left, we have a network trained on a Laplacian loss and that we proposed. And you can see there's a little blur here in this area, for example, whereas if we train on a feature loss, it's more high fidelity results. So I would prefer the right ones for like an actual application, whereas the best ones give us better results for like usual metrics like PSNR and SSIM. But Richard Sang released like a paper a while ago where they work on a perceptual similarity metric called LPIPS. And it's interesting that LPIPS gives us a better score on this image that I would prefer the human to than this image. So typically what people are doing often nowadays is they compare on PSNR and LPIPS. So PSNR is like, okay, if I train my network with a like color loss, like a knife color loss, like Laplacian loss or one loss, then usually I get good metrics for PSNR. If I use the feature loss, then usually I get good LPIP scores. And you can also just train on LPIPs. Back then, we just trained on just the VGG feature loss again. All right. Since then, I joined Adobe, and at Adobe, we have lots of video products. So as a research scientist, I was like, how can I make my work on frame interpolation more practical? Let me actually go back. I should have added a slide. Let's go back to this pipeline here. Well, this works well. It's kind of limiting still for, let's say, for example, for fake 4K frame interpolation. So why is this limiting for 4K frame interpolation? Well, you have to estimate the optical flow at a 4K resolution, and that takes time. And then you need to apply, like you have to extract the feature pyramids at a 4K resolution, which takes time. And then you need to do the image synthesis at a 4K resolution, which takes time. I mean, running a neural network at a 4K resolution, like that's not something that people typically really do. I mean, if you look at applications for neural networks, they're usually like working on like a megapixel image, not 4K footage. And not only do we need to work on like 4K footage for frame interpolation, if you work with videos, you have to do that like 30 times per second. So let's say you have like a task where you estimate depth from an image. You just do that once, and you usually do that on a low resolution as well. Whereas for frame interpolation, we need to do this several times per second for like, because videos have like many frames we need to interpolate between. and we needed to be able to do it in 4K. So if you look at this, essentially what we can't do is any of the stuff that is here at the bottom. We can't do this if we want to be able to do this fast. We can't extract feature pyramids, and we can't use an image synthesis network to combine results. Just like even just like this image synthesis network, running a network on a 4K resolution, that's just slow. It's too slow to do that 60 times per second to have like the hopes of being real-time frame interpolation. So this is the idea that we explored in this paper. How can we do this better? How can we do frame interpolation that is fast, yet still good? And please forgive me that the color switched from gray to white. I haven't had time to make slides in my usual color scheme. That's why this is white instead of dark background now. So what we were able to achieve, and I'll direct your attention to the right side first, is we were able to come up with a method that works well. You can see it's performing better than all other methods in this X-test 2K benchmark. So it's a 2K resolution benchmark, and we do so in order of magnitude faster than the rest. And on the left, you can see that our method is particularly useful for interpolating multiple frames at a time. And you'll see in a second why. So if we interpolate 1 frame at a time, between 2 frames, or 3 frames, or 7 frames, or 15 frames, so this would be basically the slow motion scenario. When you want to create a slow motion video, you create like 15 frames in between 2 given frames. And you can see ours is like maybe 2 orders of magnitude even faster than the competition when doing the specific setting. So how can we achieve this? How can we be really good while also being really fast? Just some quality result again, some qualitative result again. Here in this example, this is a 2K frame, and there's this pole that is subject to large motion. Because it's 2K, it's like the motion magnitude is large in terms of pixels. So therefore, like soft splat, the method I just showed you, and also the method that proposes this data set, this X-test data set, and tries to perform extreme media frame interpolation. Extreme meaning on high resolution also fades in the result, because ours does it, it doesn't, and we do so in order of magnitude faster. So how can we do this? Well, we can't get rid of optical flow, so let's keep that in the loop. But we can do something smarter here. So this refers to figure 5, and this refers to equation 5. Equation 5 doesn't have any parameters in it, just like an equation. And then this blue box has just 7 trained parameters. So what is this blue box? So what we're doing is basically saying, well, we can involve a new network in like the image synthesis part, in the motion compensation part. Let's go back to the roots. Let's come up with a heuristic warping algorithm that performs the warping of the input images based on optical flow, and then gets us the interpolation result. But let's be smart about it. Like, let's try to think about all the things that are involved in this warping algorithm, and let's have all the parameters involved in this algorithm be learned. Like, instead of me sitting down and trying to tune all these hyperparameters of this specific algorithm, there's 7 hyperparameters involved in this warping algorithm. Let's just train those. Let's learn those parameters. So it's like going back to the roots of like kind of come up with a heuristic algorithm for warping, for frame interpolation, trying to integrate all the things that people learned about, or like the people found out about how to do that well, while also training end to end and learning the parameters involved. So the key there is to make this differentiable, like this warping algorithm differentiable, which is not something that previous literature has looked at. Because what happened in the past is we had heuristic warping-based algorithms, people improved them, they improved them manually by hand, but then new networks came around and we just like scrapped all of that, and we just said like, let's take a new network, let's give it the result, ignore all these heuristic algorithms, just to do that. And now we're just going back to the roots, we're integrating these heuristic algorithms, but we're making them differentiable. And by making them differentiable, we can train the system end to end, and we can train the parameters involved, so we can get the best possible parameters. And this is figure 5. This is our heuristic warping algorithm. Basically, we estimate 2 metrics. A merge splatting metric, which tells us basically this is the importance metric, kind of like it tells us how important is the pixel. See here, this are the background pixels. They are dark, so they're not that important, which means that these foreground pixels, like the car pixels, are going to be rendered on top of the background pixels, as it should be, like we're handling occlusions properly. And this down here, the merge metric, is used when we have two, like we warp the first frame and the second frame. We need to merge those two frames, and the merge metric will be used for that. It's like a reliability measure of sorts. Like if a pixel is unreliable in the interpolation result, we should probably not use it in the final result. But in the other frame that we warped, it might be reliable, so therefore we should take that pixel instead. And we made sure that all of that's differentiable, like that is a backwards warping algorithm, it's gathering, it's differentiable. And this is splitting algorithm. I'll just explain to you how that is differentiable. So what are the nitty-gritty details of the heuristic warping algorithm? Let me see whether I can zoom in here without, yeah, I can zoom in without going to the next slide. Well, one thing is that instead of splitting colors directly, we split flows, and then we warp the inverse flows. So you can hear the transition where the rim meets the tire. On the left, if you split colors, we get kind of like these subtle pixel artifacts, whereas if we split flows, like forward split flows, and then we gather the colors instead, that turns out to be a little bit better in terms of like the image clarity. Small difference, but it's there. And then top right here, it's when we split flows, what we can do is we can do a wide split. So usually we split like to 4 pixels. It's called bilinear splitting. But if we split flows, we can also split a little bigger. We can split like a neighborhood of like a 5x5 window. And usually you wouldn't do that with color, because color would get blurry. But if you split flows, if the flows are blurry, it doesn't really matter that much, because you can backward swap the colors and both will be high fidelity again. And that allows us to like close some gaps in the splitting results where the flow diverged. And yeah, this is just an illustration of like this merge metric. So you can see when we warp, like, we get these stray pixels. And we don't want to combine, like we don't want to have that in the final result. So that's why in the merge metric they are low, like they are black. And ideally then the other frame that we warped will be reliable in that area, and we'll just take the information from that area instead. And if you see on the right, if we take any of these things away, if we don't split the flows but we split colors, if you don't split white flow, like the Gaussian split, if we don't do that but do a bilinear split instead, if we don't use, these are like metrics we use to generate this merge metric and the splitting metric, if there's any of those, it gets worse. So all these individual carefully thought out things matter for the final interpolation quality. And the nice thing is, because this is like fully differentiable, we can train the optical flow again. So from this row here, the second row, the third row, we make a bump of almost 2 dB. So because this pipeline is fully differentiable, we can train the optical flow, and we can train optical flow that is optimized for a specific task. And coming back to the narrative that I had earlier, is basically we make this heuristic stuff, like a heuristic warping algorithm, differentiable, and learning the parameters of that as well also improves results quite a bit. So if I just take the warping algorithm from this reference, which is basically that, but the warping itself isn't like the parameters unlearned. If we instead learn those parameters, we can get a pretty big improvement already. And then another improvement by also fine-tuning the optical flow. And then on top of that, there's another trick. We also don't want to learn optical flow estimate optical flow at 4K. So let me step back a bit. We can now do frame interpolation, where the frame synthesis part is just this heuristic warping algorithm. That's great, that's fast. It's basically just copying pixels around in the end. That's why it is so fast. That's why this line here, the green line, is so flat. Because we don't, once we estimate the optical flow, and we can interpolate novel frames in between 2 frames really easily, because we just copy pixels around because of this heuristic warping algorithm. But we still have to run the optical flow, and we don't want to run the optical flow at 4K resolutions for 2 reasons. A, it's slow, In B, if we do that, usually the inputs will kind of be unusual for what the network was trained on. Like the network will be given inputs where the flow is hundreds of pixels potentially, whereas the optical flow estimators usually are trained on datasets where the flow is tens of pixels, so there'll be a domain gap. So what we're doing instead is we are downsampling the input frames to low resolution. We estimate the optic flow in low resolution, which is faster and it's more in the domain of what the network was trained on. And then we have this network called upsample here, where we upsample the estimated low resolution optical flow guided by the two input frames iteratively. So if we downsample the input frames by 4, we basically call this network twice here because each time it upsamples by 2. And now if we do this on small resolutions, like Middlebury is a small resolution data set, if we if you do like half resolution optical flow estimation, do 2x upsampling, the result actually gets quite a bit worse. Same thing for if you do a quarter resolution optical flow estimation and 4x upsampling of the guided upsampling of the flow, it gets also worse. Because Middlebury itself is like it's a 480p resolution, I think. So if the input is small resolution, you shouldn't do this. You should just estimate the flow at the original resolution. But let's look at 2K, for example. 2K, you can see that, let's look at 4K. So let's look at 4K. On a 4K, doing this, like downsampling to half the resolution, actually gives us better results than doing it at the full resolution. Because now we are more in the domain of the optical flow estimator. So like, not only do we get better results, we also do so faster here on the right. So you can see the runtime of the entire thing on like 4K footage is like only half than if we do this system where we do half, we downsample input by 2x and then do the guided upsampling of the flow, we get a 2x runtime improvement. So if you have 4K footage, you get faster results and you get better results if you employ the scheme. Whereas like on 2K, with this specific example, for example, you still get like similar results, like it drops by 0.4 dB, but you're still 2x faster, so you can trade off as well. And because the warping is so fast, I actually implemented it in WebAssembly. So if you go to my web page and you go to this project page for this paper, at the bottom, it's going to let us load a second for the flow. Let me zoom into the page a little bit. If I drag this slider at the bottom, it will perform the frame interpolation in real time. So this is essentially the heuristic warping algorithm. So what we're doing here is we pre-compute the optical flow. So what we're given here is the input images and the estimated optical flow, and we just employ the heuristic warping. And this is just a demo to show you that, like, even in a browser where we run this thing in a single thread and there's like no multi-threading of any sorts, we can do frame interpolation in like real time. All right, let me go back to slides then, and oops. That is it from me. You can see my webpage if you want to look at it. And with that, I'm happy to answer any of your questions. Let me stop the screen share. Stop sharing. I think we still have like 10 minutes left or so for questions.
Can you hear me?
Yes, I can hear you.
Okay, thank you, Simon, very much for your talk. It was a great talk with a lot of interesting works from your previous contributions to the field. So now we have some time for 10 minutes for questions from the audience. Feel free to type your questions on the chat or step forward to the microphone zone in front of the stage if you have any questions. If you prefer, you can also type your question in Portuguese, and I try to translate that to Simon. Do you have any questions from the audience? Well, while they are probably preparing their questions,
but didn't overwhelm them.
Yeah, I have a short question. Actually, you showed in your last slides, in your last works, some efforts to decrease complexity and make possible real-time video interpolation, right? So when we are thinking of video streaming, online video streaming, we are very frequently limited to the computational resources at the receiver side. For example, we don't have GPU on our phone, or we have limited memory, battery constraints as well. So do you think this real-time interpolation that you just showed for us in your website is possible? Is it working for this kind of environment, for very low power environment and limited memory, no GPU, etc.?
I mean, why can we do this here in the first place? Why can I look at your stream without my CPU screaming that it has to process all this video? It's because the video decompression is baked in hardware. Same thing on the phone. I mean, H.264, I guess also H.265 nowadays. There's dedicated hardware on your phone that takes care of that. That's why we can do it. That's why we don't drain our battery, and that's why our phone doesn't heat up while being on a video call. If we had like a hardware that can estimate optical flow, then you can do quite, like, I guess you can do many things with that. Because like, so for this last project that I presented, this flooding-based synthesis, once we have the optical flow, we can do interpolation in real time. So assuming that you would have like a hardware unit that can estimate optical flow for you, then I don't see any issues with that. But getting to the point of baking this hardware, that might take a few more years, if not decades, just because we're still making significant improvement in optical flow estimation. And probably it's going to be difficult for people to agree on one optical flow estimator to bake in hardware and then ship in like millions of devices.
It would need like a change in manufacturing and preparing the processors for making this type of processing available, right?
Yeah, and I mean, you can see that already. NVIDIA nowadays, as far as I know, I'm under the impression of that they're doing that nowadays already, like the newest GPUs, they are shipping hardware accelerated optical flow estimation. There's an SDK news like in the 4000 series. I don't know whether they are actually baked in hardware or whether it's running on the CUDA cores. But like, we might see that happening more often in the future.
Okay, hopefully. Okay, let's see if we have any other question here. Does anyone? Andre Brescia stepped into the microphone, so.
Have you tried training the optical flow at a even lower resolution to see if the upsampling is even more performs even better at higher resolutions compared to no upsampling?
The question was, please correct me if I'm wrong, have I trained optical flow at a high resolution to see whether it would then perform even better than what you're doing at a high resolution?
No, at an even lower resolution, to have even simpler optical flow and then leave more of the complexity to the upsampling module.
Oh, like, so if we try to improve the upsampling, like make the upsampling better, and whether we could get away with like a low resolution flow estimate.
Yes.
It's like a chicken and egg problem. I mean, if you look at optical flow estimation, how it's used to be done, like this variational approach, you defined your optical flow estimation, how would you do it, and then you applied coarse to fine. So every stage in this pipeline was the same. So there was no difference between like optical flow estimation and optical flow upsampling. It was always the same. So in a way, we could do the same thing. We could try to come up with a pipeline that does the same thing at every single stage. But we didn't do this. We did this upsampling instead because to optimize for 4K runtime. So then the idea is, let's like have like a good optical flow estimator at a low resolution, because the pixels scale quadratically, it doesn't take as much time, and then just like spend less time on the upsampling. And so we try to shift our compute budget away from so instead of like doing the same thing at every stage in the pyramid from coarse to fine, We do more at the lower scale because it's less computation demanding, and we do less complex steps. We do this iterative refinement on like the higher resolutions. That's why we separate it like this. But I mean, if you spend more compute budget on the upsampling, on the refinement of the optical flow, then it becomes more towards optical flow estimation again, and will get better. Good question.
Thanks. Is the code for this new splitting work available as well? I was trying to find it the other day and wasn't able.
I'm afraid not. So again, opinion's my own. But since I work for Adobe, and since this might end up in a product, I don't know. It's like definitely like it has capabilities of getting a product, but again, opinion's my own. It's difficult for me to open source this because my employer might not like that.
I
But
figured you might have had an issue with that.
Yeah, I had an intern that I worked with. We published a paper called Many-to-Many Splitting at CVPR. Because his was an internship, he was able to publish the code on GitHub. And the ideas they are similar, where we only do optical flow estimation, only do splatting, no like synthesis. So it's similar in nature, just the technicality, like the technicalities are different.
Yeah. And you also improved a little bit the splitting, right? To fix the mathematical invariance.
Yeah, so we did that. So for the softmax splitting, the issue is the exp in there. Like if you do exp 20, like the numbers get really big. If you do exp 100, it's like probably out of bounds for floating point range. I think it's out of bounds for floating point range, yeah. So we have like a mathematical trick of like not make it out of bounds, and then we call it stable softmax splitting. That is more likely to be released. I just haven't made it a priority yet. So in the future, I think if there's code to be released, I'll release the code for the stable softmax splitting. Just so other people can use it, because the softmax splitting actually has been used for many other applications. For example, for image animation, like Alex Zelinsky, he was taking a single input image and then animating the single input image, for example, with a waterfall, and he was using softmax splitting for that. And there are some other applications for softmax splitting as well. So the utility is pretty big for this stable softmax splitting operator. That's why I would like to release it, just haven't made it a priority yet.
Oh, great. Thanks.
Thank you for the questions.
Okay, do we have any other questions? I don't know if we have time for other questions. I believe so, because we have a break now, but the time is still available, I think. Giovanna, do you want to make a question?
Then thank you so much for having me. If you have any questions that you didn't want to ask here, feel free to shoot me an email. You can go to my personal website, sniklaus.com. I think my email is listed in my resume, and just shoot me an email. I'm happy to answer any questions you may have. And thanks for listening to me. Hope I was able to share some of the joy that I have of video frame interpolation with you. It's definitely getting more popular these days. And then have a good rest of your day. Enjoy the conference.
Okay, thank you very much for your talk and then accepting our invitation. Let's just thank Simon once more. Please press F on your keyboard.
Thank you.
For you. Okay, so thank you. And now Claudio will come here to give us some information about the next session.
Okay, thank you very much, Simon, for the excellent talk, and Guilherme also for chairing the session. We have a break now, and after the break at 3 p.m., we are starting the Pix Force challenge session. They are going to announce the challenge, and then we have you can enjoy your break now. Thanks. então. Essa sessão vai ser em português, tá? Vai ser uma apresentação, então, da empresa Pix Force, né, que tem uma operação aqui em Porto Alegre, no Rio Grande do Sul, Brasil. E a palestra, então, vai ser apresentada aqui pela Bárbara Santana, que é Head de Pessoas na Pix Force, e pelo Matheus Bergman, que é Head de Engenharia. Então, tá com vocês aí a palavra. Obrigado aí por terem aceito o nosso convite.
Show. Muito obrigado aí pelo convite. Iniciando, então, falando um pouco sobre a Pix Force, hoje, quando nós olhamos para grandes empresas, é muito difícil a gente não encontrar um caso em que tem uma pessoa fazendo algum tipo de inspeção visual. O problema é que esse tipo de inspeção, muitas vezes, é alguma coisa repetitiva, pode ser algum... Depois de muito repetir isso, acaba se tornando suscetível a erros, porque a pessoa cansa de estar executando aquela tarefa. Foi pensando, então, nesse problema que surgiu a Pix Force. Nós somos uma empresa de visão computacional e desenvolvemos soluções que buscam justamente captar imagens e vídeos automaticamente e livrar as pessoas desse tipo de situação tediosa, repetitiva, etc. Aqui vocês podem ver alguns dos nossos clientes. A Pix Force foi 5 vezes top 1 pelo ranking da Sim Open Startups e hoje nós somos consideradas a número 1 em inteligência artificial no Brasil. Pensando, então, na metodologia de trabalho da Pix, como nós fizemos para conseguir chegar nessa posição, basicamente, a Pix Force é uma empresa que conhece visão computacional. Então, a gente identifica lugares onde existe demanda por visão computacional, onde existem essas atividades repetitivas, e a partir disso, nós entramos em contato com o cliente. Junto com o cliente, então, existe uma série de conversas no qual a gente busca identificar e entender exatamente qual é a dor desse cliente, qual o problema que ele precisa que a gente solucione. E a partir disso, surge uma série de brainstormings entre nosso time comercial, nosso time de desenvolvimento e nossos contatos dentro do cliente. E assim a gente busca formular alguma ideia, tentar entender como a gente consegue aplicar a visão computacional dentro desse nosso cliente para facilitar, para aliviar essa dor do cliente. Então, juntos, nós criamos a ideia e pensamos em como poderia ser o produto que nós vamos desenvolver. Definido, então, o problema, quando está tudo alinhado, tanto para Pix quanto para a gente entra na parte de desenvolvimento. E nosso desenvolvimento se divide em 3 etapas. Primeiro, a gente faz uma prova de conceito. Nessa prova de conceito, geralmente, a nossa saída é algo bem simples, é um modelo num ambiente relativamente controlado. E o que a gente quer, no final dessa etapa, é validar que realmente visão computacional é capaz de solucionar esse problema, que a gente vai conseguir ter uma classe, alguma métrica que seja suficiente para resolver o problema do cliente. Validado isso, a gente passa para a próxima etapa, que é o projeto piloto. Nesse momento, a gente começa a desenvolver todo o software que existe ao redor desse mecanismo de visão computacional. Sejam sistemas de captura, plataforma web, desktop, dashboards, o que é necessário para isso, de fato, começar a virar um produto, ser algo que possa ser utilizado pelo cliente. E, durante o piloto, a gente vai aparando as arestas, deixando redondinho para ver como realmente a gente consegue desenvolver algo que encaixe no pipeline que o cliente já utiliza. Nessa parte, a gente realmente começa a pensar em escalar, em fazer várias réplicas do nosso sistema. Com certeza, a gente vai aumentar a dataset, melhorar nossos modelos. E, claro, a gente entra naquela fase de observar os nossos modelos, ver se as coisas estão se comportando, se houve alguma mudança na natureza dos nossos dados, que eventualmente a gente precisa atualizar o modelo. Então, toda essa parte aí de avaliar como as coisas estão se comportando em produção. E eu acho que o mais bacana de tudo isso na Pix Force é que acaba sendo uma coisa que é constantemente algo novo, né? Então, os projetos variam muito, mudam os clientes, mudam a realidade, muda o tipo de problema. Às vezes é uma classificação, às vezes é uma detecção, às vezes é uma segmentação, às vezes é uma questão de clustering, às vezes vai ser com deep learning, às vezes não vai ser com machine learning clássico, ou vai ser com visão computacional clássica. Então, existe uma variedade, uma gama muito ampla de formas que a gente pode solucionar esse problema, e a gente tem que estar constantemente se atualizando, buscando acompanhar as novidades que estão surgindo, para que a gente consiga sempre estar entregando o melhor para os nossos clientes. Além dessas soluções personalizadas, nós já temos alguns produtos prontos. Um deles é o Pix Counter, que é uma tecnologia capaz de contar itens a partir de imagens ou vídeos. Aqui nós temos um exemplo de contagem de botijões em um caminhão. Temos também o Pix Quality, que busca fazer o controle de qualidade através de imagens. Então, detectar quando objetos numa linha de produção saíram com algum defeito para avisar o nosso cliente que eventualmente precisa tirar aquele produto da linha de produção dele. Temos também o Deep Track, que é uma solução pensada em correias transportadoras, que essas correias frequentemente sofrem de problemas de superaquecimento e é muito difícil fazer uma inspeção manual, e a nossa solução é, através do uso de drones, fazer uma inspeção automatizada dessas correias, e usando câmeras termais, a gente detecta esses roletes, encontra pontos quentes e mostra, através de uma plataforma web para o cliente, quais os pontos que ele precisa, eventualmente, fazer a substituição de um desses roletes antes que danos maiores ocorram. Bárbara?
Olá, boa tarde. Bom, primeiramente eu quero agradecer o convite, né? Mais uma vez a gente está participando do desafio. Nós já participamos no ano passado, então, e parabenizar também a organização do evento, né? Pela realização. É muito legal a gente estar participando novamente e num contexto de já ter vivido isso antes. E viemos aqui com até uma notícia legal que eu lembrei agora de passar para vocês, que no ano passado nós lançamos um desafio aqui, né? A premiação do pessoal foi vir a fazer o estágio na Pix Force, e uma das pessoas hoje já está sendo efetivada, né, como desenvolvedor na Pix Force, e veio através desse desafio aqui no ano passado. Então, é algo que a gente tem bastante orgulho, né, e sabe que dá bons frutos aqui a participação no evento. Então, muito obrigada novamente aí pelo convite. Eu vou falar um pouquinho da Pix agora como instituição, né, como cultura, e aqui na nossa frase de nosso slogan, né, a gente fala aí que as máquinas, deixar as máquinas trabalhar pela gente, né, que a vida é muito curta. Então, eu acho que isso resume muito bem as coisas que eu vou me aprofundar agora. Pode passar, Bergman. Que fala sobre o nosso objetivo, nossa visão e o que a gente está propondo fazer pelo mundo, né. Então, o nosso propósito é desenvolver o melhor para libertar os humanos de atividades perigosas, tediosas e cansativas através da visão computacional. Então, exemplificando antes, né, ali o Bergman trouxe alguns projetos, com a ideia de mudar as relações de trabalho, né? E existe uma crença de que a tecnologia vem para tirar empregos, e na verdade ela vem para transformar isso, né? Para as pessoas pensarem mais, para desenvolverem muito mais o raciocínio e estarem mais dispostas a desenvolver coisas intelectuais do que propriamente coisas repetitivas, trabalhos cansativos, e que também são trabalhos que trazem mais riscos, né, à saúde e à integridade física das pessoas. E aqui é a nossa visão, né, nós temos uma visão muito grande, né, nós sonhamos grande, isso faz parte também da nossa cultura, do jeito que a gente trabalha. Então, a nossa visão é liderar o mercado de visão computacional até 2024 para a indústria 4.0, né, então, é uma visão muito amplo, assim, mas eu vejo totalmente isso como algo possível diante de todas as conquistas que a gente tem até agora e diante do crescimento que a gente vem vivendo, né? E eu vou contar um pouquinho para vocês depois. Pode passar. Como eu sou da área de pessoas, agora vem uma das coisas que eu mais gosto, né? Que é falar sobre os valores. E os valores, eles não estão dentro de um produto ou dentro de um projeto, eles estão nas pessoas que estão executando aquilo ali. Então, eu mesma, né, quando eu estou contratando alguém, eu trago pessoas que tenham estes valores para continuar crescendo, né, essa cultura da empresa e se disseminando mesmo com o aumento do time. Então, a primeira coisa é foco no cliente. E aqui a gente está falando do quê? De todos esses resultados positivos que a gente tem, né? Pelo 5º ano consecutivo, top 1 na 100 Open. Então, isso só mostra que é a questão de qualidade, né? De comprometimento, de entrega. Então, esse é o nosso compromisso com o cliente e é por isso que a gente vem avançando cada vez mais. A inovação. E eu falo aqui que a inovação não é só em questão de tecnologia, né? A gente inova até nos nossos processos, nos processos de recursos humanos, que é algo que eu tenho feito bastante. A gente mudou a forma de fazer contratações por aqui, a gente trabalha de uma forma muito humanizada, né? A gente busca conhecer as pessoas a fundo, porque acredita que a parte técnica é algo que a gente pode desenvolver. Então, a gente inova de várias formas, né? Então, no dia a dia, nos processos e na tecnologia. A inovação é o nosso DNA por aqui. Confiança nas pessoas, né? Eu sou um caso disso, eu sou um caso de confiança aqui da Pix Force. Então, a gente entra aqui com aquela barrinha, assim, em 100%, né? Quando a gente fala de confiança, as pessoas entram aqui com confiança total. Nós acreditamos muito em cada pessoa que a gente traz para o time, porque aqui a gente trabalha com muita autonomia, com muita liberdade, a gente precisa de pessoas que venham para construir. Então, a gente vem crescendo porque todas essas pessoas que fazem parte do time construíram um pedaço disso, né? Só os fundadores, sozinhos, eles não conseguem construir tudo. Então, eles contam com a gente para que isso aconteça. Então, todo mundo tem essa confiança, essa liberdade de fazer de uma forma autônoma as atividades, né? De confiança até na hora de questão de horários, né? O pessoal trabalha com flexibilidade, trabalha de casa. Então, existe muito essa confiança e a gente vê resultados muito positivos disso, né? As pessoas também se desenvolvem de uma forma mais rápida, né? Profissionalmente falando. E isso eu posso falar de mim e de pessoas que eu já vi acontecer nesse 1 ano e meio que eu tô por aqui. Coragem, então, muito atrelado a isso que eu já falei. Coragem de ousar, de tentar, de fazer, não ter medo de errar, né? Porque se errar, a gente vai estar aprendendo de qualquer forma. Então, se a gente não fizer, a gente não vai estar saindo do lugar e não vai estar aprendendo nada. Então, a gente incentiva as pessoas a terem coragem de fazer, né? De tentar e de fazer coisas novas. O trabalho em equipe é o nosso ponto fortíssimo. Isso é unânime, né? É uma questão que todo mundo reconhece aqui dentro. Então, mesmo estando à distância, né, que é uma realidade atualmente de pessoas aí em vários lugares do Brasil, nós já tivemos pessoas e temos pessoas que fazem parte do time que não estão no Brasil, mas existe essa conexão no dia a dia, né, esse contato entre as pessoas, essa troca, que é muito rica, né, então, é muito acolhedor, existe a gente tem uma das nossas regrinhas, né, da Pix Force é nunca negar ajuda. Então, mesmo que eu não saiba o que é, e isso eu falo quando as pessoas entram, pode estar com uma dúvida lá sobre, sei lá, sobre alguma questão técnica, uma ferramenta. Se tu não sabe para quem perguntar, fala comigo. Eu também não vou saber, mas eu vou te ajudar, a gente vai junto buscar essa solução, né? Então, faz parte da nossa cultura ter essa integração entre as pessoas, e é muito importante que as pessoas que venham para cá tenham essa ideia, né, de trabalho em equipe. E a integridade, que aqui está ligada à questão de ética, né, de compromisso. Então, além de, claro, respeitar cada pessoa, né, as suas limitações, as suas dificuldades. Então, existe muito isso, é inaceitável qualquer tipo, né, de desrespeito, seja ele qual for, e a gente está falando aqui de questões éticas, né, tanto entre nós, tanto com o cliente. Então, isso é algo que está nos nossos valores aqui descrito, mas que eu considero algo básico, né, na sociedade, mas que é importante a gente reforçar, porque de forma alguma nós aceitamos algo que não seja ético ou que seja desrespeitoso com alguém. Pode passar. Aqui eu quero falar das nossas oportunidades, tá? Com certeza vocês conhecem pessoas, né, que estão na busca aí no mercado, ou que estão buscando novas oportunidades, ou que têm essa vontade de ingressar na área que a gente trabalha. Então, nós temos várias oportunidades agora, devido a um grande crescimento que está acontecendo neste momento com a Pix Force. Nós estamos deixando de ser uma startup. Nós estamos nos tornando agora uma empresa, né? Nós mudamos de tamanho, questão fiscal. Nós hoje temos 80 pessoas, estamos próximos de chegar a 100 com o número de vagas que a gente tem aberto, a gente deve passar. Então, até janeiro, acho que a gente vai bater essa marca das 100 pessoas. E isso é muito legal, é muito gratificante de ver, porque quando eu cheguei aqui, há pouco mais de um ano, nós éramos 50. Então, nós estamos dobrando de tamanho em um ano, o que vem acontecendo desde o início, desde os 6 anos aí que a Pix existe, ela praticamente dobra de tamanho a cada ano. Então, dessa vez é uma proporção diferente, nós estamos saindo de 50 para 100. Isso é muito legal de ver, porque tem muitos desafios, né? Nós estamos com vários projetos de P&D, projetos com objetivos muito legais, com coisas super inovadoras, motivadoras, né? O nosso time é muito motivado com os projetos. Então, é muito legal ver isso. E, claro, traz muitos desafios, mas com isso a gente consegue também evoluir internamente, né? Cada um na sua vida profissional. Então, é muito legal ver isso, e aqui eu trouxe para divulgar para vocês, se vocês quiserem depois, eu posso também mandar o link das vagas, para vocês terem uma ideia. Nós estamos hoje buscando PO, pessoa desenvolvedora de mobile, né, tem que ser Flutter, e tem que ser daqui, de Porto Alegre, região, porque essa pessoa vai trabalhar também com drones. E os drones, a gente precisa de um contato presencial algumas vezes. Não tem um fixo, mas é sob demanda. Então, essa pessoa não precisa ter uma experiência muito grande. A gente está aceitando pessoas de nível júnior, tá? Então, se vocês conhecerem alguém ou se interessarem, podem me procurar. Eu estou à disposição. Mas existe essa necessidade de ser da região. As demais vagas, não, tá? Então, a gente também tem vaga de desenvolvedor de visão computacional. Pode passar. Tem para nível de doutorado, nível de mestrado e graduação, tá? Isso é importante, a gente tem um time bem acadêmico, acho legal reforçar isso. Então, nós temos aqui graduados, mestres, doutores, pós-doutores, temos pessoas com muita bagagem acadêmica, né? Isso a gente quer manter, essa é a nossa ideia, né? E isso também é importante por causa dos projetos de P&D. Então, exige, né, tem essa exigência do ensino, e claro, porque isso vai, enfim, tem divulgações, tem artigos publicados, então é bem importante ter o time mais acadêmico, tá? Então, é algo que a gente mantém por vários motivos e tem sido muito rico, né? Estamos fazendo coisas grandiosas aí com o time. Temos também para a área de vendas, né? Que, claro, com o nosso crescimento, a gente precisa essa vaga exclusiva para São Paulo. Nós também temos um espaço no Cubo do Itaú, em São Paulo, então nós estamos em Porto Alegre, mas temos esse espaço lá no Cubo também. Estamos procurando alguém para trabalhar no meu time aí, né? Acredito que estamos encaminhando aí para o final do processo, mas ainda estamos aceitando candidaturas, então, com esse aumento do time, eu preciso de ajuda, né? Então, hoje, o time de RH, no momento, são 3 pessoas, eu e mais 2 pessoas, e agora seremos 4 pessoas aí para atender a demanda tanto de contratação quanto as demandas internas, né? Para atender o time e continuar conseguindo ter contato com todo mundo. E, por último, especialista em sensoriamento remoto, né? Recentemente começou essa semana um estudante do mestrado da UFRGS, que é especialista em sensoriamento remoto, e nós temos mais uma vaga também, e para essa vaga é importante ter o doutorado, tá? Bom, das oportunidades é isso. Pode passar, Bergman. E eu tenho aqui uma dica, um plus, né? Eu sei que todos aqui têm algum contato com o meio profissional, de alguma forma, tem pessoas que ainda não têm, tem pessoas que estão iniciando, então eu trouxe algumas dicas para vocês e eu vou falar um pouquinho sobre elas, sobre o uso do LinkedIn. Hoje é a nossa maior ferramenta de busca de profissionais, de recrutamento, então acho bem legal vocês terem essa noção do outro lado, como funciona, né? Então, primeiro, usar palavras-chave. As palavras-chave, elas são como a gente encontra vocês. E muitas vezes o pessoal não aprofunda muito, né? Então, por exemplo, quando eu vou buscar um desenvolvedor full stack para Pix Force, eu digito lá as palavras Python e Vue.js. Por quê? Eu preciso que seja alguém que tenha experiência nessas duas tecnologias. Então, o que eu faço? Eu faço essa busca. E muitas vezes as pessoas têm um perfil ali sem aprofundar quais são as linguagens, as tecnologias que ela usa. Então, é muito importante ter o uso das palavras-chave no seu perfil. Detalhar ao máximo as experiências, tá? Então, quando você bota ali, eu sou hoje desenvolvedor júnior na empresa X, o que eu faço lá? O que eles fazem? Qual é o produto, o projeto que eu atuo? Né? Qual é o meu papel naquele time? Ter isso descrito vai deixar ainda mais rico o perfil de vocês. Vai ser mais fácil de encontrar também quando a gente precisar de alguém com aquele perfil. Manter atualizado é muito importante, né? É uma forma de vocês estarem aí sempre, enfim, as vagas que vierem serem aderentes àquele perfil que vocês estão atualmente. Conexões estratégicas. Desculpa. Conexões estratégicas, então. Quando eu falo isso, para mim, né, eu faço conexões com pessoas de RH. Pessoas de RH de outras startups, de outras empresas parecidas com a minha. Porque eu consigo abranger até a terceira conexão delas, quando eu faço uma busca. Então, estrategicamente, eu penso nessas pessoas para eu fazer conexão, porque assim eu vou cada vez mais ter pessoas dessa área, né, e candidatos que provavelmente são muito parecidos, os meus e os delas, para eu pesquisar. Para vocês, eu acredito que seja esse mesmo caminho, só que vocês fazem conexões com empresas daquele ramo que vocês querem seguir, daquelas tecnologias que vocês estão se especializando, né, para que vocês sejam vistos com mais facilidade. Porque assim como eu busco, né, se vocês tiverem conexões com essas pessoas, eu também vou encontrar. E fique atento às mensagens recebidas. Eu sei que muitos recebem muitas mensagens e tudo mais. Eu sei que tem uma busca grande aí pelos profissionais de tecnologia no mercado. Eu, particularmente, não mando um número grande de mensagens. Eu busco aprofundar muito a minha busca para que eu mande poucas mensagens e o resultado disso é bem positivo, porque a gente consegue fazer um trabalho mais personalizado. Mas é importante vocês estarem olhando para essas mensagens e não fecharem as portas, né? Responderem, pelo menos, né? Falarem, olha, agradecer, eu acho bem legal, acho que é uma forma muito boa de você criar uma boa imagem também. E quanto mais você responde ali na rede social, também você mais vai ser visto, né? Seu perfil fica mais... você vai estar usando, ele vai estar em movimento. Então, isso também é importante. Pode passar. E aí, aqui, eu trouxe um exemplo de onde ficam as palavras-chave que são importantes. Pode voltar. Foi adiante. As palavras-chave, às vezes a gente usa aqueles... Ali, sabe, embaixo do nome no LinkedIn, a gente usa para botar a nossa função. E ali é um lugar para colocar essas linguagens e ferramentas, tecnologias, pensando no objetivo que vocês querem trabalhar e com que vocês têm mais especialidade. Porque é através dessas palavras aqui que eu consigo encontrar dentro do LinkedIn as pessoas quando eu digito ali esses itens. Então, bem ali embaixo do nome, né, onde é o título da sua função, você pode colocar o título, se você está trabalhando atualmente, mas você também pode, eu acho que mais importante do que isso é colocar quais as suas especialidades. Tá? Então, essa é a minha dica, esse é o meu recado. Eu vou deixar agora com o Bergman para falar sobre o nosso desafio desse ano, mas eu estou à disposição, se vocês tiverem dúvidas, se vocês quiserem me encontrar pelo LinkedIn ou quiserem meu contato, o professor Claudio tem os meus contatos, tá? Então, eu estou à disposição aí para vocês, para nós, esse contato com vocês é muito, muito importante, tá bom? Muito obrigada.
Show de bola. Vamos falar do desafio, então. Vocês já tiveram aí um pequeno spoiler. Mas o grande motivo de nós estarmos aqui hoje é porque nós estamos trazendo para vocês um desafio de contagem de objetos. Então, o objetivo desse desafio é que o candidato crie métodos de contagem para alguns objetos. O que são esses objetos? São 3 objetos que nós escolhemos. O primeiro, placa. O segundo, perfil. E o terceiro, cantoneira. Mais para frente eu vou dar para vocês alguns exemplos de o que são esses objetos com algumas imagens. As soluções envolvidas devem obrigatoriamente contemplar ao menos as opções 1 e 2. Então, o placa e perfil são os mais importantes, e a cantoneira vai ser considerado como um diferencial, como uma pontuação extra na avaliação. Então, falando um pouquinho aí das partes, o escopo das soluções, então, é justamente entregar todas essas questões, essas 3 contagens ali, ou pelo menos 2 delas, né, a 1 e a 2. Olhando aqui os datasets, o que são esses objetos? O primeiro é o perfil. São essas coisas que vocês podem ver aí do lado direito, que tem um formato um pouquinho estranho, mas eles têm sempre o mesmo formato e eles estão um pouquinho encaixados um dentro do outro. Esse dataset de perfil, ele tem um total de 150 imagens. Todas elas estão anotadas. Então, foi anotado ali o polígono ao redor da face da frente, como está mostrado na imagem. O segundo dataset, as placas MDP, também possui 50 imagens, e são essas chapas aí, e a anotação que a gente possui nessas imagens é um pequeno círculo em cada canto das imagens. Demonstra, que descreve a coordenada da imagem que está o objeto, né? E, além disso, nós temos 2 datasets não anotados. O primeiro é o dataset das cantoneiras, então, também com 150 imagens, mas sem anotação. A ideia aqui é que, eventualmente, se use esse formato triangular aí das cantoneiras para conseguir contá-las nas imagens. E também temos um outro dataset das placas MDP, que pode ser usado como uma alternativa àquele dataset anotado, também com 150 imagens, em que a gente tem uma visão lateral ou frontal dessas placas. E aqui todas as placas, então, têm a mesma espessura, e, eventualmente, dá para tirar vantagem disso para conseguir fazer a contagem desses objetos. Então, deixa eu voltar aqui. Basicamente, o escopo da solução é fazer a contagem nesses datasets que eu mostrei. O entregável vai ser o código-fonte, junto com os resultados, e todas as instruções que a gente precisa para conseguir executar. Como quesitos de avaliação, a gente vai avaliar tanto a qualidade do resultado obtido, qualidade do código, e a gente tem um conjunto de imagens que não faz parte desses datasets que nós estamos entregando para vocês, no qual algumas métricas vão ser avaliadas para nós vermos quão bom está a solução de vocês. E, chegando então no cronograma, a gente tem aí a divulgação, que está sendo hoje. As inscrições vão até o dia 20, e no dia 23 mesmo haverá a liberação dos datasets. E vocês têm, então, até o dia 12 para entregarem as soluções. Entre o dia 12 e o dia 14, a gente vai dar uma olhadinha. A apresentação vai ser no dia 16 de dezembro, e após as apresentações, mais detalhes sobre esse desafio vão estar disponíveis no site. Vai ter um documento que vocês podem baixar, vai ser liberado no site daqui a pouquinho. Mas, se tiverem dúvidas, estou aberto.
Obrigado, então, Bárbara, Matheus, pela apresentação. A gente tem um tempo agora para perguntas, dúvidas sobre a empresa, especialmente sobre o desafio, né, também. Acho que deu uma trancada ali no vídeo do Matheus, pelo menos para mim, mas a ideia é que a gente, então, a gente está divulgando hoje, né, o desafio, e aí até dia 23, então, as inscrições, aí eles liberam o dataset, dia 12 de dezembro é o prazo final para enviar as soluções, e dia 16 de dezembro a gente vai ter um evento aí, a gente vai divulgar, então, tudo isso no site, tá direitinho, vai ter um evento de apresentação e divulgação dos premiados. Não sei se podem comentar um pouco sobre a premiação.
Pode ser eu?
Sim, a Bárbara vai comentar, então.
Bom, a premiação, gente, a gente pensa em algo que venha a agregar, né, tanto para a empresa quanto para vocês. Então, a premiação será uma bolsa de estágio, né, para a equipe vencedora. Então, se forem, as equipes são de até 3 pessoas, então, se forem 3 pessoas, serão 3 pessoas que vão ganhar a bolsa de estágio. A ideia é trazer aí uma experiência de mercado, né, com tudo isso que vocês viram que a gente trouxe aqui, toda essa experiência, tanto questão de cultura que a gente está falando, tanto com a questão do desenvolvimento das tecnologias, dos projetos. Então, trazer essa experiência aí para vocês, atrelado ao que vocês estão estudando, né, e, claro, quem sabe aí vir a crescer, como é o caso do nosso colega aí que está evoluindo agora para a vaga de desenvolvedor, né? Então, nosso objetivo é sempre esse, né? Que as pessoas comecem aqui e que elas tenham essa oportunidade de crescer e evoluir junto com a gente. Então, a premiação será essa, para início, daí provavelmente no início do ano, mas isso a gente pode organizar conforme também o calendário escolar, né, para ficar tudo bem confortável também para vocês. E é um estágio que a gente é bem flexível, então se aconteceu, né, da equipe que venceu no ano passado, não foram todos que conseguiram fazer 30 horas, a gente adaptou para 20, nós adaptamos os horários, como a gente trabalha de forma flexível, é bem tranquilo conciliar com as aulas, então é uma grande oportunidade aí para que vocês vivam isso no dia a dia, né, dentro do mercado.
Beleza. Perguntas, pessoal? Acho que o Garen ali está se posicionando. Não. Quem quiser fazer perguntas pode ser pelo chat, tanto aqui no Metaverso quanto no YouTube, tá? Eu estou com o YouTube aberto aqui também, quem está assistindo pelo YouTube. E pode fazer via chat ali, ou se posicionar naquele megafone laranja na frente do palco, dá para falar por áudio, né? a gente escuta também. O Guilherme vai fazer uma pergunta, eu acho.
Oi, está me ouvindo?
Sim.
Olá, Bárbara, Matheus, tudo bem? Mais uma vez, obrigado por participar de novo da DPVSA e por lançar esse desafio para o pessoal. Eu tenho uma pergunta relacionada mais ao funcionamento da Pix Force e sobre, até talvez seja mais para a Bárbara, relacionado à formação do pessoal que trabalha na Pix. Vocês mencionaram ali que vocês têm vagas, por exemplo, para mestres, para doutores. Eu queria que tu, se pudesse, discorrer um pouquinho, falar um pouquinho sobre como que vocês veem na Pix Force o papel da pós-graduação, se vocês valorizam que os alunos, depois da graduação, façam uma pós-graduação, se é importante para a Pix Force isso,
Com certeza.
ou se tanto faz o aluno ter pós-graduação ou não ter para trabalhar aí.
Obrigada, Guilherme, pela pergunta. Bom, acho que mostrando, né, que as nossas vagas têm já esse título, inclusive, a gente está mostrando que isso para nós é muito importante, né? Então, eu posso exemplificar de uma forma de quem está vendo o processo seletivo, de que, e o Bergman, inclusive, é a pessoa que faz a avaliação técnica dos processos seletivos e pode me ajudar nessa resposta. Quando a gente traz pessoas que não evoluíram muitos estudos, né, não seguiram adiante, ou às vezes não são da mesma área, né, são de outras áreas, fizeram transição de carreira, a gente enxerga uma diferença muito grande em questão de conhecimento da parte técnica, tá? Então, continuar vivendo isso, estudando, nossos projetos, eles são coisas totalmente novas, precisa de pesquisa, precisa desse viés de conhecimento, né, de se aprofundar no estudo. Então, sim, é muito importante. Essas vagas que eu falei, nós temos aí, são hoje 15 vagas, tá? 5 tem que ter graduação, 5 tem que ter mestrado e 5 tem que ter doutorado, tá? Não podemos fugir desses requisitos. E até o Bergman, acho que se tu quiser falar um pouquinho, Bergman, do teu mestrado, acho legal falar isso. Nós temos hoje o Bergman, temos mais 2 colegas fazendo, um está fazendo a tese do doutorado com um projeto da Pix Force, então ele está sendo pago como profissional para fazer o doutorado, né? E tem um outro colega também fazendo mestrado e o Bergman é um deles.
Isso aí. É uma oportunidade muito bacana. A gente trabalha bastante com projetos de P&D dentro da nossa empresa. Então, são projetos que, para o cliente, existe tanto a necessidade de desenvolver um produto, algo que vá gerar valor para ele, mas que também existe um meio de pesquisa que a gente mostre que tem inovação ali. Então, é muito comum a gente fazer esse tipo de coisa, de desenvolver, permitir que alguém faça um mestrado, um doutorado, durante um projeto de P&D, porque é algo que é positivo para os dois. É muito positivo para a pessoa que está tendo uma experiência de mercado, está tendo contato com um problema real, está tendo bastante dado disponível, porque a gente está constantemente capturando dados que a gente precisa para esse tipo de coisa. Então, é muito bom para o aluno e é muito bom para a empresa, porque, assim como a Bárbara disse, claro que não é a única forma da pessoa se desenvolver, mas é uma das formas muito boas da pessoa desenvolver. A gente precisa de pessoas que tenham esse cunho de estar buscando coisas novas, estarem se atualizando, porque as coisas em tecnologia andam muito rápido. Então, a gente precisa de pessoas que estejam constantemente acompanhando a evolução da tecnologia. E as pessoas que vêm na academia, geralmente, elas têm esse perfil de que elas sabem ir atrás, elas leem artigos, elas estão por dentro das últimas novidades que tem à disposição.
Só para complementar minha pergunta, então, obrigado pelas respostas. Eu imagino que haja também uma forma de compensação, diferença de salário para quem tem doutorado, mestrado e graduação, né? E existe também alguma facilitação, não sei se é bem a palavra certa, mas alguma forma de avançar na carreira dentro da empresa se a pessoa tem pós-graduação e não em comparação a quem não tem a pós-graduação? Quer dizer, se eu ingressar na Pix Force como graduado e depois de um tempo fizer mestrado e depois doutorado, isso vai facilitar a minha progressão na carreira dentro da empresa?
Então, nós temos hoje, bem importante eu falar, dar um contexto, uma introdução, na verdade. Nós estamos estruturando muita coisa, então tem políticas que ainda não são vigentes, né, mas que estão sendo criadas. Parte de descrição de cargos, plano de carreira é uma delas. Nós estamos estruturando, porque nós mudamos muito rápido de tamanho. Então, muda também o contexto, a forma com que a gente avalia isso. Mas o que eu posso te dizer é que hoje, o que a gente usa? Júnior, pleno, sênior, especialista. Eu não vou ter um cara sênior ou especialista se ele só tiver a graduação. É muito difícil, tá? Então, se torna um pré-requisito para a senioridade daquela pessoa. Então, atualmente, a gente vê muito dessa forma, tá? Mas é algo que, com certeza, vai se encaminhar para um processo, uma política interna de só vai ser uma pessoa especialista ou naquela tecnologia ou naquela função, se ela tiver uma escolaridade X, ou então ela tiver uma bagagem muito grande profissional, né? Então, tem que, até hoje, né, com o pessoal que a gente tem atualmente, tem muito disso. Quando a gente traz alguém do mercado, né, querendo ganhar um salário X, e aqui dentro eu tenho uma pessoa que já ganha esse salário e tem um doutorado, essa pessoa é comparada a ela. Então, se ela não tem o doutorado, já começa aí. Eu nem preciso levar para avaliação técnica para fazer essa equiparação, né? Eu já sei que aquela pessoa não está no nível de conhecimento daquela pessoa que está aqui dentro e que tem o doutorado. Então, sim, acaba sendo, sim, uma forma de evoluir profissionalmente.
Eu ia comentar, bem legal, assim, parabéns para a empresa por valorizar, né, essa questão acadêmica e absorver também pessoal da pós-graduação, porque isso realmente vocês conseguiram fazer essa leitura que é uma win-win situation, né, para os dois lados, tanto para a empresa que começa a inovar, vocês estão inovando, vocês estão, por isso então que vocês têm todos esses prêmios, né, e tem esse reconhecimento porque vocês estão inovando de verdade, e isso passa por um processo de, né, absorver pessoas que têm esse perfil de inovar, né, e para a pessoa também, né, ela consegue com a formação dela ter um resultado que vai para o mercado imediatamente, né, não é algo que eu tô na academia, às vezes a gente fica meio frustrado também como professor, que a gente publica um artigo, mas aquilo não vira um produto, não vira um serviço tão imediatamente assim, ou daqui a um tempo, né? Então, é muito legal isso, assim, essas via de mão dupla, assim, que está acontecendo aí, que vocês estão valorizando. Então, parabéns, né, pela...
Eu quero complementar mais uma coisa, né? É importante a gente avaliar dois outros pontos de vista. Primeiro, quando a pessoa só tem experiência acadêmica, pode ser que ela não tenha uma questão do ritmo do mercado. Então, isso a gente também precisa levar em consideração. Tá? Mas é muito comum nós temos bastante pessoas, né, Bergman, que vieram de uma área totalmente acadêmica, que nunca tiveram uma experiência profissional no mercado. Mas, normalmente, a adaptação, essa pessoa, ela é rápida, né? E em meses, a gente sempre faz ciclos de 6 meses para fazer uma avaliação, né? E ver se a pessoa ainda está aderente àquela função ou se ela já pode evoluir para um cargo melhor, para uma remuneração melhor. Então, é importante levar isso em conta também, porque é avaliado ali na avaliação técnica, né, que eu acho que é a forma mais justa que a gente tem de fazer, se essa pessoa tem a expertise para já chegar no mesmo nível dos demais, ou se ela vai demandar treinamento. E uma outra questão que é importante, hoje o mercado de tecnologia, ele está se tornando um mercado com menos formação, né? Então, a gente vê muitos profissionais se formando em cursos profissionalizantes, ou de forma autodidata, e não fazendo uma graduação, uma pós-graduação. O que eu vejo disso, né? Eu acho que, primeiro, a experiência do ensino, para qualquer pessoa, ela é muito rica, né? Começando por esse ponto. Então, eu incentivo muito e valorizo muito quando a pessoa busca estar sempre em formação, né, e buscando conhecimento. Então, acho que não ter essa experiência do acadêmico, não ter a experiência da graduação, não ter a experiência do mestrado ou doutorado, com o tempo isso vai ser algo bem prejudicial, né? Acho que vai se perder um pouco da teoria, que é muito importante para o ensino. Então, na Pix Force, a gente ainda prioriza muito isso. Então, as nossas vagas sempre sempre levam em consideração a formação da pessoa para que seja contratado, diferentemente do que o mercado aí tem apresentado, né, de forma geral. E visão computacional, principalmente. Visão computacional é muito, muito raro ter alguém que não tenha essa bagagem acadêmica.
Sim, vocês devem conviver com esses perfis até dentro da empresa, imagino, porque a visão computacional, imagino que já é gente que tem uma bagagem maior acadêmica, porque tem muita questão de estar no estado da arte e tudo mais, mas daqui a pouco tem áreas em que vocês conseguem contratar alguém que tem uma formação menos acadêmica, mas eu fiz um curso online, uma coisa assim, eu saí programando, coisa, né, essa parte web, enfim, a gente vê muito isso mesmo no mercado, assim, pessoal sem diploma, assim, né, que está trabalhando porque tem experiência naquela tecnologia, né, que é muito específica e, né, e isso realmente até melhor do que quem vem da academia, né, às vezes quem vem da academia tem que fazer também um curso online para entender aquela tecnologia.
Posso te dizer que hoje no time, quem não está formado é estagiário.
Uhum.
E talvez tenha, no máximo, eu consigo lembrar de cabeça apenas uma pessoa que não tenha formação superior e é um desenvolvedor júnior.
Uhum,
é realmente muito difícil. Não é da área de visão computacional, realmente. Mas é uma área que demanda... tem uma busca muito mais complexa, assim, tem muito mais vagas no mercado, então acaba que eu tenho que buscar muito mais essa pessoa, né?
Competição por contratar, né?
Exato, e aí é uma pessoa, inclusive essa pessoa é fora da curva, questão de autodidata, de ter aprendido desde cedo, sabe, ali na adolescência já trabalhar com isso, informalmente, então, mas são casos bem raros mesmo, né? Para nós, para a Pix Force, é muito importante a formação.
Uhum. Legal. O Guilherme quer falar de novo aí.
Desculpa estar falando várias vezes, mas é só para complementar isso que vocês estão falando, é que eu acho que visão computacional é um tópico que a gente até aborda nas graduações de ciência da computação, engenharia de computação, mas não com muita profundidade. A gente tem disciplinas de processamento de imagens, a gente tem disciplina de computação gráfica, mas não aborda a visão computacional com muita profundidade na graduação. Então, acho que por isso que eu acho que faz muito sentido valorizar bastante a pós-graduação, porque é na pós-graduação que uma pessoa vai se aprofundar mais nesses conceitos de visão computacional, se for esse o tópico de pesquisa dela no mestrado, dissertação de mestrado, na tese de doutorado, né? Na graduação realmente não dá tempo de ir a fundo nesses assuntos.
Exatamente, e até normalmente quem vem só da graduação, que não tem ainda, né, o mestrado, fez alguma iniciação científica durante a graduação, com o foco em visão computacional, tá? Então, normalmente são essas pessoas, quando é só a graduação, ela teve algum contato mais profundo, de uma forma mais prática, né, dentro da graduação, com a visão computacional.
Legal. Mais alguma pergunta, pessoal? Eu acho que até esses desafios, eles tentam, né, buscar, né, essas pessoas, até, por exemplo, quebrar um pouco essa barreira aí, né, de que eles estão falando, né, visão computacional é basicamente um nicho ali de alguém fez iniciação científica, ou fez um mestrado, fez um doutorado, né, então esses desafios é legal para todo mundo aí que tem interesse, né, tentar começar a pegar o dataset lá, tentar ver como é que funciona, se inscrever, tentar fazer, né.
Sim.
O máximo que vai acontecer é, não vou tirar primeiro lugar, né, né, mas tentei, aprendi um pouco ali com o desafio, gostei, né, daqui a pouco vou me aprofundar mais, daqui a pouco consigo sei lá, vou conseguir entrar na empresa, né? Por exemplo,
Sim.
ou vou entrar na área, né? Então é esse tipo de coisa aí que a gente tenta fazer, né? De atrair pessoas para as áreas, assim, né?
Exatamente.
E também é um objetivo desse evento.
A gente tem muito contato com universidades, tá? Eu tenho uma lista de contatos de professores, né, que são especializados nessa área, alguns mais de inteligência artificial, outros de visão computacional, mas a gente tem isso porque a gente valoriza muito esse contato. Esse desafio aqui é algo para nós muito, muito importante, é algo que a gente quer manter. Então, assim como esse, a gente quer pensar já em algo para o início do ano, fazer de novo, porque a gente entende, a gente tem exemplos reais dentro da Pix Force de pessoas que vieram ali, que começaram como estagiário, e aqui são, né, que é o Bergman, começou aqui como estagiário e hoje ocupa um cargo de head de engenharia, né, uma pessoa especialista na área. Então, a gente acredita muito nesse crescimento, acredita muito nesse contato com a universidade para criar esses caminhos, né, esses caminhos de crescimento, assim, profissional. Então, para nós é muito importante, sim, e eu tô louca para ver o resultado, né, do desafio. Tô curiosa.
Tá certo. Acho que se não temos mais perguntas aí, não sei se alguém mais tem alguma dúvida. Tá, então agradecer novamente a Bárbara e o Matheus. Na verdade, é muito legal que isso começou ano passado, né, com a DPVSA do ano passado, essa parceria, e a gente continuou esse ano, esperamos continuar aí, a gente espera continuar o evento nos próximos anos e espera continuar essa parceria aí com a Pix Force, de fazer esse desafio, né.
Legal.
E obrigado a todos aí que assistiram. Agora às 4, vou dar uns minutinhos, às 4 a gente vai começar a sessão de encerramento, então. Vamos divulgar também os trabalhos premiados aí.
Muito obrigada, pessoal. Boa tarde.
Obrigado, então. Boa tarde.
Valeu, muito obrigado, pessoal. Até mais.
Isso aí. Então, pessoal, boa tarde a todos. Obrigado aos que ficaram até agora, né? na nossa cerimônia de encerramento. Então, a gente está encerrando agora a 6ª DPVSA, né, a IEEE Seasonal School on Digital Processing of Visual Signals Applications. Primeiramente, né, a gente gostaria de agradecer novamente, né, os nossos apoiadores, né, que tornaram esse evento possível. Então, a FAPERGS, que nos deu um apoio financeiro aí, através do edital de auxílio à organização de eventos, né. A I3E, por meio das sociedades Circuits and System Society e Signal Processing Society, que nos deram também apoio financeiro aí para a realização dessa escola. Então, por isso é uma escola da casa e da SPS, né? A gente tem também um apoio técnico de 2 comitês técnicos da CAS, né, que nos ajudaram aí na busca de palestrantes, principalmente internacionais. Então, obrigado, né, Visual Signal Processing Communications e a Multimedia Systems and Applications. Obrigado também, né, às instituições organizadoras que então forneceram as pessoas, os recursos humanos, aí nós, né, que ajudaram aqui a tornar esse evento possível. Então, a Universidade Federal do Rio Grande do Sul, Universidade Federal do Pampa, Universidade Federal de Pelotas, Universidade Federal de Santa Catarina e o Instituto Federal do Rio Grande do Sul. E aí está o comitê organizador, né? Então, muito obrigado aí aos colegas, né? Então, começando aí pelo Fábio, né, que topou aí meu convite. A gente, na verdade, começou e foi convidando as outras pessoas, né? O Fábio acho que quer falar um pouco aí também, então vou deixar um espaço aí para o Fábio falar.
Assim, bom, primeiramente, boa tarde a todos, pessoal. Eu ri porque, claro, né, agora acho que é um momento um pouco mais lúdico, a gente pode começar a relaxar um pouco, né? A gente foi convidado a ser General Chair, né? Primeiro, né? Aí, a partir do convite de General Chair, a gente começou a cadeia, né, do nosso state, claro, né? A gente começou a cadeia de buscar os apoiadores, né, pessoal, que são todos os chairs, né? Então, eu só quero deixar um agradecimento, primeiramente, ao Claudio, novamente, né, que, digamos, foi o primeiro General Chair do evento, foi o primeiro que abraçou a causa, ao Guilherme, ao Matheus, nossos Program Chairs, ao Thiago, o Betemps, nossos Poster Chairs, o Daniel, o Publicity, o Felipe, Eduardo, Murilo, os nossos streamings, os nossos liaisons, né, o Zé, né, o Jacob, o Bruno Zatti e o Luciano Agostini, tá? Além disso, não posso deixar de esquecer, né, pessoal? Agradeço a todos os revisores, agradeço a todos os autores, agradeço a todos os chairs de sessão, né, pessoal, sejam de sessão de palestras ou de posters, tá? E agradeço a todos os participantes, né? Porque, digamos, esse é o motivo para a gente tentar...
também.
E os palestrantes, tá? Faltou isso, né? Faltou os palestrantes. Ainda bem que tu me lembrou, Claudio, o cara já começa no brain meltdown nessa hora, né?
Sim.
Tá? Mas é isso, tá, pessoal? Então, eu agradeço a todos vocês, agradeço a Pix Force, agradeço as sociedades que nos apoiaram, as nossas universidades de origem, né, que de alguma forma estão cedendo recursos aqui para o evento. E é isso, né? Bola para frente, estamos encerrando aí. Espero eu que tenha sido proveitoso para todos, da melhor forma possível, né? Eu achei bem bacana, assim, seja da experiência de General Chair aqui, ou mesmo novamente usando o metaverso, que já tínhamos utilizados no Chip-in, acho que foi lúdico, né? Foi divertido e deu para descontrair um pouco dentro do possível, tá? Falei demais já, Claudio, se quiser retomar à vontade. Obrigado para todo mundo, pessoal.
Tranquilo, Fábio. Também agradecer a todos, né, como Fábio, faço minhas as palavras do Fábio, né? Acho que todos fazem um evento possível, seja quem só assistiu e aprendeu aí com as palestras, esse é o objetivo final, né? A gente ter palestras que as pessoas aprendam, ou pelo menos saibam que existe, né, aquele tópico e vão buscar mais depois. Às vezes o evento a gente não vai aprender como uma aula de um curso, né, mas a gente vai saber que existe, vai correr atrás das informações que foram repassadas, né. Aqui tem os números novamente, então a gente teve 6 palestras, 4 em inglês e 2 em português. É bom salientar que a gente gravou a maioria todas as palestras foram gravadas. Uma delas não está autorizada para a gente divulgar, mas todas as outras que estão autorizadas vão estar no canal do YouTube do CAS Rio Grande do Sul Chapter, que muitos de vocês puderam acompanhar pelo YouTube, tá? Quem está acompanhando pelo YouTube já está usando. Quem está só no metaverso, saibam que a gente tem um canal do YouTube do capítulo CAS Rio Grande do Sul, tá? Que já tem mais de 2.000 inscritos e mais de, acho que 300 vídeos, né? De eventos e de palestras que são realizadas toda semana aí, as CAS Talks, tá? Então vejam o nosso canal lá, nosso, porque a gente também é parte do capítulo Rio Grande do Sul, da CAS, tá? E, então a gente organiza vários eventos aí no âmbito desse capítulo, e a DPVSA também é um deles, tá? Então esses vídeos a gente vai ter um tempo agora para editar e vai colocar os vídeos das palestras lá no canal também, tá? Então vocês vão ver que vai aparecer em algum momento no canal esses vídeos gravados. Então quem perdeu alguma palestra vai poder olhar de novo lá, quantas vezes quiser, tá? A gente teve também 3 sessões de posters, com 31 posters, tá? Alguns autores não puderam estar com a gente online, então a gente passou o vídeo, por isso que a gente pediu o vídeo antes, né? E a gente passou o vídeo, isso ficou disponível aí para as pessoas olharem. Os vídeos estão também no site, quem quiser ver os vídeos, então se o autor não retirar o vídeo, ele vai ficar lá, tá? E os posters também, os posters podem ser vistos lá no site, tá? A gente teve aí em torno de 275 participantes de 10 países, tá? A gente ainda está compilando quantos deles realmente assistiram às palestras, estiveram com a gente vai compilar isso através dos formulários de presença, tá? Quem preencheu, claro. Mas inscritos a gente tem em torno desse número aí, isso está aumentando porque a gente manteve as inscrições até o dia de hoje. A grande maioria do Brasil, né, porque é um evento que surgiu aqui, mas a gente tem pessoas de fora também assistindo a gente. Então, pessoas do Chile, Colômbia, França, México, Holanda, Peru, Portugal, Coreia do Sul e Estados Unidos. Então, é muito legal que a DPVSA no modo virtual, ela realmente virou um evento internacional, né, no sentido de que a gente é aberto a pessoas de todo mundo, assim. As sessões de pôster, a gente teve, então, só para retomar, né, 31 pôsteres aceitos, né, 15 revisores ajudaram, então, a revisar esses 31 pôsteres. Teve em torno aí de 2 revisões por pôster, e trabalhos de 6 diferentes tópicos foram enviados, né, com autores aí de 11 instituições de 3 países. Então teve trabalhos, grande parte do Brasil, mas teve um trabalho da França e um trabalho do México também, tá? E agora o momento bem esperado, que é o momento de divulgação dos prêmios, eu vou convidar aí o Carlos Betempes, né, que é um dos poster chairs, para divulgar os premiados. Eu vou passando os slides aqui, tá, Carlos? Obrigado aí por fazer isso para a gente.
Tá bem. Obrigado aí, Claudio. Me escutam bem? Ontem deu problema no...
Sim.
Então tá tranquilo. Então, enfim, né, gostaria de primeiro aí parabenizar todos que participaram do evento, né, o evento estava bem legal, parabenizar enfim, os palestrantes, a organização de forma geral, né, e, enfim, os autores também que enviaram, né, que confiaram, por assim dizer, no evento, trazendo, submetendo seus trabalhos, seus posters, né, para a nossa apreciação aqui, apresentaram, trouxeram seus resultados e discutiram isso com a comunidade. Isso é muito, muito legal, né. Também gostaria de agradecer, né, na realidade, o convite aí para fazer parte dessa comissão organizadora, né, para ser poster chair, junto com o Thiago, veio aí do Fábio, né, então agradeço o Fábio, agradeço o Claudio pelo convite, né, legal estar participando, eu não tinha feito essa atividade ainda, então foi legal essa primeira experiência, então agradeço muito. Acho que falo em nome aí também do Thiago, acho que ele estava por vir aqui, ele estava numa reunião.
Fala em nome de mim, sim.
Beleza, então, valeu, Thiago. Então, agradeço aí, né, em nome dos posters chair, né, o convite, foi legal fazer esse trabalho aí, e tá agora no momento especial, que é a questão aí dos prêmios, né, Então, só comentando um pouquinho, na realidade, os posters, né, eles foram revisados, né, como a gente foi apresentado antes, né, a gente teve ali um conjunto de revisores que fizeram essa primeira passada, né, essa primeira revisão, né, colocaram sugestões, enfim, enviaram sugestões para os autores, né, e aí teve então a gente usou essa avaliação, essas notas, vamos colocar dessa forma, né, a gente usou essa avaliação para fazer um ranqueamento, aí, uma ordenação e conseguir descobrir quais eram os best posters aí para o evento, tá? Então a gente usou essa avaliação, depois uma comissão interna, ou especificamente, né, eu e o Thiago, a gente fez uma avaliação dos vídeos, né, então eles foram usados também aqueles melhores classificados, então a gente fez uma avaliação também dos vídeos e fez meio que uma média aí, né, foi os critérios que a gente usou, essas duas avaliações, né, para gerar, então, uma colocação, classificando, então, os trabalhos, né, os posters entre alunos aí que já se graduaram, né, e os alunos que estão na graduação, né, o graduate e o undergraduate. Enfim, então eu acho que, não sei se o Thiago tem alguma coisa a acrescentar, mas eu posso começar a apresentar, então, aí os premiados.
Acho que antes de falar ali dos prêmios, né?
Isso. Bem lembrado. Então a gente tem essa premiação, né? Então temos verba aí para premiação. Os best posters, eles vão ser premiados de acordo com a categoria, como eu falei. Então, primeiro, segundo e terceira colocação, terceiro lugar aí para cada categoria. Então, primeiro lugar, tanto graduação quanto pós-graduação, né, $500 ali. Na segundo lugar, $300 e terceiro lugar, $200. Então são as premiações, né, para primeiro, segundo e terceiro colocados na categoria graduação e na categoria pós-graduação, tá? Acho que é hora de começar a avançar ali nos slides. Então a gente pode passar, então falar primeiro aqui dos graduate students, né, o pessoal que já se graduou, está numa pós-graduação. Então, fizemos toda essa análise, e o terceiro lugar, eu posso anunciar agora aí, Efficient Architecture for VVC Angular Intra-Prediction Based on Hardware-Friendly Heuristic, né, os autores são Vinícius Borges, Murilo Pellerberg, Marcelo Porto e Luciano Agostini, né, então, parabéns aí aos autores, parabéns pelo pôster, né, muito legal estar premiando os trabalhos, a gente teve trabalhos bem legais aí, então, terceiro lugar, parabenizo aí principalmente o Vinícius, né, que foi quem apresentou, então, legal a participação de vocês e legal essa premiação aí, né. Enfim, do terceiro, então, vamos para o segundo colocado, então, High Throughput Multi-Filter VLSI Design for the AV1 Fractional Motion Estimation, né, os autores são Daiane Freitas, Claudio Diniz, Matheus Greller e Guilherme Correia, né, parabenizo também aí os autores, né, principalmente a Daiane, que fez a apresentação, né, e por último, né, mas mais esperado aqui, a primeira colocação aí para os graduate students, né, a Hardware Friendly and Configurable Heuristic Targeting VVC Interframe Prediction, né, autores Marta Luz, Ramiro Viana, Fernando Sagrilo, Gustavo Sanches, Guilherme Correia e Luciano Agostini, né, parabéns, né, um parabéns especial aí para os autores, né, pelo trabalho, pelo post. Legal ter a participação de vocês, né, e esse reconhecimento no final acho que é muito merecido, acho que os trabalhos são legais, a gente tem que reconhecer aqueles que se destacaram, né, e foram esses aí dos trabalhos de graduados já, né. Então, parabéns aí para o pessoal. Enfim, não sei se podemos seguir adiante, Cláudio.
Acho que sim. Eu não sei se o pessoal está por aqui, eles querem...
Pois é, enfim, aqui a gente não fica até sem a visão ali, deixa eu mudar aqui, mas...
Os ganhadores estão por aí, acho que alguns estão, pelo que eu estou vendo.
Se quiser dar um oi ali no megafone laranja aí.
Dá um oi, ou dá um oi no chat, ou sei lá, alguém tá chegando.
O Vinícius está ali.
O Vinícius está ali.
Aí, Vinícius, parabéns aí.
Obrigado, Marta ali também.
Parabéns aí, Vinícius, aí, terceiro
Parabéns.
lugar.
Obrigado pelo evento também, muito bom evento.
Legal, Vinícius.
Valeu, obrigado.
Parabéns.
Parabéns, Vinícius.
Parabéns. Ó, a Marta aí, primeiro lugar. Parabéns aí, Marta.
Parabéns,
Obrigada.
Marta.
Parabéns.
Agradeço aos
Você-
orientadores e também o pessoal que ajudou aí no artigo. Obrigada. No pôster.
Parabéns.
Joia. A Daiane tá por aí? Não.
Acho que não.
Tá. Então vamos passar para o undergraduate.
Vamos passar. Thiago quer apresentar? Sigo apresentando.
Posso apresentar.
Então a gente divide essa. Nem chega a ser carga agora, né?
É a parte legal, né?
A parte legal da coisa.
Tá, vou passar aqui o slide.
Vai lá, vai lá. Então,
Terceiro
os critérios
lugar.
foram os mesmos e o terceiro lugar, então, vai para Accelerating the AV1 Global Warped Motion Compensation. O trabalho foi autorado por William Kolodziejski, Robson Domensky e Luciano Agostini. Então, parabéns aos autores aí pelo excelente trabalho.
Parabéns.
Vamos lá.
Bueno, movendo para o segundo. Então, segundo lugar vai para AV1 Arithmetic Decoder Landscape Analysis with Boolean Processing. Trabalho autorado por Giovana Gomes, Túlio Bittencourt, Sérgio Bamp e Fábio Ramos. Parabéns aos autores.
Parabéns, Giovana.
Parabéns, pessoal.
Parabéns. E o primeiro lugar vai para Near Data Speculative Motion Compensation, Compensation Processing em DVC. Trabalho de Garleno Souza, Sérgio Bamp, Bruno Zatti, Marco Zanata e Felipe Sampaio. Parabéns mais uma vez para todos os autores.
Parabéns.
E reforço as palavras do Betempes ali, né? Especialmente um parabéns aí para os primeiros autores, para os alunos de graduação, né? E eu acho que essa, se não foi a primeira, que tenha sido uma ótima primeira, ou melhor, se foi a primeira, que tenha sido uma ótima primeira experiência, né, nesse tipo de apresentação de trabalho, e se não foi, que seja a segunda, a terceira de várias outras, e esse é o nosso desejo, né, que isso se torne uma rotina para esse pessoal que está entrando agora nesse mundo de pesquisa. E, a gente fica feliz de certa forma, ter contribuído aí com esse processo de organização dos poster sessions, né, e do processo de revisão também. Tá, não sei, passo a palavra para o Betempes aí.
Os autores aí querem falar um pouco.
Quer falar alguma coisa?
Esses estão por aí.
Eu
queria destacar aí, né, que a gente teve vários trabalhos aí de graduação, trabalhos de qualidade e alunos, né, iniciando o curso, né, em semestres bem iniciais, já apresentando os trabalhos. Então foi bem legal ter essa participação aí do pessoal mais iniciante no curso e já participando de eventos como esse, né? Então isso é muito legal tá vendo isso acontecendo. Motiva a gente.
Sim, sim. Ó, o William entrou ali. Parabéns, William. Novamente, né? O William ganhou um prêmio no CASW também, há uns 2 semanas atrás ali.
Olha,
então, obrigado à organização do evento aí. Obrigado também ao Luciano Agostini, meu orientador. Valeu, pessoal.
Valeu.
Parabéns, William.
Bom, parabéns, William.
Parabéns.
Parabéns.
Giovana tá aí, ou Garemos?
A Giovana, acho que ela tá com o celular, ela tá sem computador, acho que não tá falando, pelo que eu entendi.
Bom.
Tranquilo, então.
Bom, de qualquer forma, a gente reforça os nossos parabéns, né, para os autores aí.
Sim. É isso, então, pessoal. Obrigado aí novamente por assistirem a 6ª escola de processamento digital de sinais visuais e aplicações, né? Foi uma honra aí ajudar um pouco mais o evento. Eu venho me envolvendo com o evento já desde 2020 ou 2019, não me lembro agora. Mas agora, como General Chair é a primeira vez, então foi legal aí abraçar isso e tornar possível a gente manter o evento anual, né? Então, essa mensagem final aí, a gente não tem ainda a definição do próximo ano, mas a gente, como comunidade, eu acho que todo mundo gostaria que fosse realizado, né? E até o Suzin botou ali, né? Quem são os candidatos para coordenar a próxima edição? A gente precisa aí de voluntários, a gente precisa de gente nova.
Fez a provocação aí, pessoal.
Fez a provocação.
Eu entendo que os futuros podem estar aqui pode estar na plateia aí, né? Vai saber.
Então
por aí.
Quem é professor novo aí, quem é professor antigo, tanto faz, assim,
ou
quem
esteve,
quiser abraçar, né?
Esteve durante o evento aí.
Quem esteve durante o evento, quem quiser ajudar aí, né? A gente está sempre à busca de voluntários, né? Senão fica sempre os mesmos, né? Eu já fui poster, eu comecei que nem o Tempos e o Thiago como poster chair, aí fui publicity chair, aí virei general chair, né? Então, a gente quer fazer uma boa renovação aí do time, né? E ter, né, mais gente ajudando aí a organizar. Todo mundo gosta de participar, né? E é bom a gente ter, todo mundo entende que o evento tem que continuar, então a gente tem que dar aí uma contribuição também nesse sentido, né? Sempre assim, enfim. Não sei, temos um tempo aí, quem quiser falar alguma coisa, né? Vou deixar a palavra aí à disposição.
Se quiser botar os bonequinhos para dançar, para celebrar, o Z, só apertar Z.
Z,
Pressing,
eu vou dançar também, vou começar
todo
a
mundo
dançar
aí
aqui.
celebrando aí, para ficar registrado lá no YouTube lá, que tá todo mundo celebrando.
De repente, o pessoal da organização quiser subir no palco, a gente botar as câmeras e tirar uma foto aí.
Eu tenho só uma coisa para falar.
Fala aí, Guilherme.
O evento foi muito legal, parabéns para a organização aí, para os coordenadores gerais. Muito legal. Esse evento no Metaverso, a gente já tinha, alguns de nós, né, já tínhamos testado no Chip do ano. É muito legal para interagir. Mas eu acho que ano que vem seria muito, muito legal se a gente tivesse um evento presencial para todo mundo se encontrar novamente, né? Faz muito tempo que a gente já não se vê presencialmente. Então, se ano que vem alguém se animasse a organizar um evento presencialmente, seria maravilhoso. Não estou me candidatando, só estou dizendo que seria muito bom.
Seria bom mesmo.
Eu acho bom, a gente acabou de fazer há 2 semanas atrás um evento híbrido, e a gente fez a micro híbrida também. Então, essa questão de fazer eventos híbridos também não é uma coisa impossível, tá? É difícil num evento que tem mais tracks, por exemplo, fazer um evento híbrido, né? Um evento que, tipo, um shipping de no ano híbrido seria meio insano, né? Ter coisa presencial e remota ao mesmo tempo. Ao mesmo tempo não, mas enfim. Conviver com essas questões, mas um evento single track, que nem esse que é o nosso, né? Que a gente coloca tudo...
Sim.
Só tem uma coisa acontecendo de cada vez, né? Só tem uma palestra, só tem uma sessão de pôster. Eu acho que é bem possível da gente fazer híbrido, a gente ter uma palestra presencial e daqui a pouco uma palestra virtual, ou transmitir a palestra também para quem não consegue vir, coisas do tipo. Tá, mas eu acho que essa discussão fica aí para a gente fazer nos próximos passos aí. Acho que a gente pode fazer uma foto, talvez, do Meeting View aqui, não sei como. Deixa eu ver se eu consigo fazer
Ia perguntar se a foto era dos avatares ou era da gente mesmo.
É da gente mesmo, das câmeras. Então, quem quiser subir aí no palco aí...
Não é a Matrix, agora é o...
Quem quiser abrir a câmera, eu consigo ver a câmera da plateia também, então...
Sim, quem quiser abrir a câmera aí na plateia,
todo mundo aí
consegue ver aqui, caso
eu acho que dá para ver, deixa eu ver aqui.
Preferência que sejam vestidos, né? E para poder
isso, sim,
aparecer,
por favor.
Né, pessoal?
Não sei se a gente bota, peraí, deixa eu ver. Eu vou tirar aqui, vou parar de
tira,
compartilhar aqui.
Aí já um slot a mais. Né?
E boto isso aqui, o Meeting View aqui, mas... Tá, não vai aparecer o logo, mas depois a gente edita, bota o logo do evento aqui, sei lá.
Sim.
Quem é que faz o print screen? Eu mesmo?
Achei que tu ia fazendo.
Vou fazer então. Tá? Não, nem todo mundo abriu a câmera aí, pessoal. Eu não sei se a gente consegue ver a câmera, peraí. Deixa eu ver uma coisa. O Matheus... É só quem tá no palco.
Não, todos que estão próximos aqui, eles aparecem com a câmera fechada, né?
Pois é. Porque eu tô vendo um monte de câmera fechada. Deixa eu ver uma coisa aqui.
O pessoal não tá com
O pessoal
coragem,
tá sem
cara.
câmera. Então deixa assim, eu vou
vamos,
fazer aqui.
Vai nós aí mesmo.
Tá bom. Vamos lá, então. 1, 2, 3 e X. Tá, deixa eu ver se foi certinho aqui. Uma fotinho. Se bem que tá no YouTube também, né? Então dá pra fazer do YouTube esse print screen depois.
A foto é para os alunos usarem para fazer figurinha dos professores depois.
Isso. Então,
então
tá, pessoal. Pontualmente aí, 16h29, na verdade. Tá? Agradecer novamente aí a participação de todos. E declaro encerrada aí a DPVSA 2022. Obrigado.
Obrigado, pessoal. Até a próxima, viu?
Até a próxima.
Boa tarde, boa semana a todos.
Até a próxima. Foi.